Around 252 million years ago, Earth experienced something that makes every other extinction event look mild by comparison. 96% of marine species vanished. 70% of land vertebrates disappeared. The planet became so hostile that scientists call this period the Great Dying. This wasn't a quick asteroid impact like the one that killed the dinosaurs. This was something far more terrifying because it was slow, relentless, and touched every corner of the globe. Before we dive into the catastrophe itself, you need to understand what Earth looked like when everything was still intact. The Permian period stretched from roughly 299 to 252 million years ago, and the planet during this time was almost unrecognizable compared to today. All the continents had fused together into a single massive landmass called Pangaea. Imagine taking every modern continent, smashing them together, and creating one enormous supercontinent that stretched from pole to pole. That was Earth's geography for millions of years. This configuration created extreme climates that most modern organisms would find impossible to survive. The interior of Pangaea, thousands of kilometers from any ocean, became a scorching desert. Without nearby water to moderate temperatures, these inland regions experienced brutal heat during summer and freezing cold in winter. Coastal areas remained more temperate, but the sheer size of Pangaea meant that vast stretches of land received almost no rainfall. Seasonal monsoons would arrive with devastating force, then disappear for months, leaving the landscape parched and cracked. The oceans surrounding Pangaea, collectively called Panthalassa, covered everything else. On the eastern side of the supercontinent, a large bay called the Tethys Sea cut inward, creating a somewhat more sheltered marine environment. But even the oceans weren't stable. Sea levels fluctuated dramatically throughout the Permian, exposing and then flooding continental shelves repeatedly. These changes stressed marine ecosystems that had evolved over millions of years to expect certain conditions. Life had adapted remarkably well to these harsh conditions, though. Synapsids dominated the land, and these weren't dinosaurs. They were the ancestors of mammals, though they looked nothing like the mammals we know today. Picture creatures like Dimetrodon, with its distinctive sail-like back, or the massive herbivore Moschops, built like a barrel with stubby legs. These animals had developed strategies to cope with Pangaea's extreme temperatures and limited resources. Some regulated their body temperature through behavioral adaptations. Others had developed more efficient metabolisms. In the oceans, life thrived despite the challenges. Coral reefs built by organisms called rugose and tabulate corals created complex ecosystems. Brachiopods, shelled creatures that look superficially like clams but are actually completely different animals, covered the seafloor in dense colonies. Trilobites, those iconic armored arthropods that had survived for hundreds of millions of years, still crawled along the bottom, though their diversity had declined from earlier peaks. Ammonoids, spiral-shelled relatives of modern squid, hunted through the water column. The climate itself was in a precarious state. Atmospheric oxygen levels during the Permian were lower than today, possibly around 15 to 19% compared to our current 21%. This meant that animals couldn't grow as large as they had during the Carboniferous period, when oxygen levels had soared to 35% and insects the size of eagles buzzed through ancient forests. Carbon dioxide levels fluctuated throughout the Permian, sometimes spiking high enough to warm the planet significantly, then dropping again. But underneath this seemingly stable world, pressure was building in ways that nothing alive could detect. Deep beneath what is now Siberia, magma was accumulating in enormous chambers. Tectonic forces were arranging the pieces for the largest volcanic event in the last half-billion years. The continents, locked together in Pangaea, had created stress points in Earth's crust that were reaching their breaking point. Ocean chemistry was balanced in a way that left little room for error. What I'm about to describe isn't speculation. The evidence is written in rock layers across the planet, in isotope ratios that tell us about ancient temperatures, in fossil beds where entire ecosystems are frozen in their final moments, in chemical signatures that reveal exactly what happened to the atmosphere and oceans. Scientists have spent decades piecing together this story from hundreds of sites worldwide, and what they've found is more disturbing than any disaster movie. The extinction didn't start with a bang, it started with a crack. Around 252 million years ago, the Siberian traps began to erupt. These weren't typical volcanoes forming cone-shaped mountains. This was flood basalt volcanism, where magma poured out of massive fissures in the ground and spread across the landscape like water from a broken dam. The lava flows eventually covered an area roughly the size of modern-day Europe, in some places piling up more than 3 kilometers thick. But here's what made this volcanic event uniquely catastrophic. The magma didn't just erupt onto the surface. It burned its way up through layers of sedimentary rock loaded with coal, oil shales, and limestone. Each rock type released different gases when heated. Coal combustion pumped out massive amounts of carbon dioxide and carbon monoxide. Oil shales released hydrocarbons and toxic organic compounds. Limestone, when heated past certain temperatures, breaks down and releases even more carbon dioxide. The atmosphere began changing in ways that life simply couldn't adapt to fast enough. Carbon dioxide levels skyrocketed, and this wasn't just a matter of a few hundred parts per million. Some estimates suggest CO2 concentrations may have increased by thousands of parts per million over a period of tens of thousands of years. That might sound slow, but in geological terms, it was catastrophically rapid. Ecosystems need time to adjust, to evolve, to migrate. They didn't get that time. Temperature reconstructions from this period show a warming pulse that raised global average temperatures by anywhere from 5 to 10 degrees Celsius. In the already hot interior of Pangaea, this meant temperatures regularly exceeded 50 degrees Celsius. Most large animals can't survive sustained exposure to temperatures much above 40 degrees. Their proteins literally begin to denature. Smaller organisms could burrow underground or hide in caves during the worst heat, but large synapsids had nowhere to go. The warming triggered a cascade of secondary effects that made everything worse. As temperatures rose, the oceans absorbed more heat. Warm water holds less dissolved oxygen than cold water, so oxygen levels in the ocean began to drop. Deep ocean circulation, which normally brings oxygen-rich water from the poles to the depths, weakened or stopped entirely. The ocean floor became anoxic, meaning it contained essentially no oxygen. Anaerobic bacteria that thrive in these conditions began producing hydrogen sulfide as a waste product. Hydrogen sulfide is viciously toxic. It's the compound that gives rotten eggs their smell, but in high concentrations, it attacks the respiratory systems of animals and can kill quickly. As anoxic zones expanded upward from the deep ocean, hydrogen sulfide began bubbling up into shallow waters and possibly even into the atmosphere. Imagine trying to breathe air that smells like rotten eggs and burns your lungs with every breath. That was becoming reality in many coastal regions. The ocean's chemistry was changing in another crucial way. As carbon dioxide levels in the atmosphere increased, more CO2 dissolved into the ocean, forming carbonic acid. This process, called ocean acidification, is happening today but at a much slower rate. During the Permian extinction, acidification happened so rapidly that organisms building calcium carbonate shells or skeletons couldn't keep up. The water was literally dissolving their protective structures faster than they could build them. Coral reefs, which had taken millions of years to establish, collapsed completely. The organisms that built them couldn't maintain their calcium carbonate skeletons in increasingly acidic water. When the reefs died, all the species that depended on them for shelter, food, and breeding grounds died too. This pattern repeated itself across every marine ecosystem. Brachiopods vanished in enormous numbers. Trilobites, which had survived multiple mass extinctions over 300 million years, finally met their end. Only a handful of species made it through. On land, the situation was equally dire but played out differently. As temperatures soared and rainfall patterns shifted dramatically, vegetation died back. Without plants to stabilize soil and maintain the water cycle, erosion increased. Rivers choked with sediment. Lakes dried up. The food chain collapsed from the bottom up. Herbivores starved first, then the carnivores that depended on them. Fossil evidence from this period shows a characteristic pattern. Diverse ecosystems with dozens of species suddenly give way to sparse assemblages dominated by just one or two hardy species, then even those disappear. The extinction wasn't instantaneous. Current evidence suggests the worst phase lasted somewhere between 60,000 and 200,000 years. That's a geological eye blink, but for the creatures living through it, it was generation after generation of decline, of watching their world become progressively more hostile. Some species might have survived for tens of thousands of years in isolated pockets where conditions remained barely tolerable, only to finally succumb as those last refuges failed. What I find most unsettling about the Permian extinction is how many different killing mechanisms were operating simultaneously. It wasn't just heat, or just acidification, or just oxygen depletion. It was all of them, plus factors we probably haven't even identified yet, all working together to make the planet nearly uninhabitable. Life was being squeezed from every direction at once, with no escape route. And yet, somehow, life survived. Not most life. Not even a significant fraction of life. But enough. In the aftermath of the extinction, Earth was left with a biological blank slate. The survivors were mostly small, tough organisms that could tolerate extreme conditions. They inherited a planet that had been emptied of competition. What happened next would determine the entire future trajectory of complex life on Earth, including eventually us. The survivors faced a world that barely resembled the one their ancestors had known. Imagine stepping outside and finding that 90% of everything familiar had vanished. The landscape was sparse, strange, eerily quiet. This was Earth in the earliest Triassic period, roughly 252 million years ago. The recovery wasn't immediate. For the first million years after the extinction, ecosystems remained incredibly simple. Fossil beds from this time show what scientists call disaster fauna, assemblages dominated by just a few opportunistic species that could tolerate harsh conditions. One organism in particular became absurdly common, a small shrimp-like creature called chlorea that appears in massive numbers in early Triassic rocks worldwide. Its abundance suggests oceans with very low oxygen and limited food sources, conditions where generalists that could survive on almost anything had a massive advantage. On land, a similar pattern emerged. Lystrosaurus, a stocky herbivorous synapsid about the size of a pig, became perhaps the most successful land vertebrate of all time in terms of sheer dominance. Some fossil sites from the early Triassic are composed almost entirely of Lystrosaurus remains. It's estimated that this single genus may have comprised 95% of all land vertebrates for a period. That level of dominance is unprecedented. It suggests an ecosystem so simplified that normal competitive dynamics had broken down completely. But Lystrosaurus had traits that made it perfect for the post-apocalyptic world. It was relatively small, which meant lower food requirements. Its teeth were adapted for eating tough, low-quality vegetation, the kind of scrubby plants that colonize disturbed ground. It could probably dig burrows to escape temperature extremes. And crucially, it had a sprawling posture and physiology that allowed it to function in low-oxygen conditions. While more active animals were suffocating, Lystrosaurus just kept plodding along. The early Triassic climate remained brutal. Global temperatures stayed elevated for millions of years. Some climate models suggest average temperatures were 6 to 8 degrees Celsius higher than today, with equatorial regions potentially reaching 50 degrees or more. At those temperatures, large animals physically cannot survive without sophisticated cooling mechanisms. Heat stroke becomes inevitable. This explains why the surviving animals were predominantly small. Large size, which had been an advantage in cooler Permian climates, became a death sentence. Recovery happened slowly, in pulses. The fossil record shows several false starts where biodiversity began increasing, only to crash again. These setbacks were likely caused by recurring environmental stress, volcanic eruptions that continued sporadically, or climate instability as Earth's systems struggled to reach a new equilibrium. Each setback reset the recovery process, eliminating newly evolved species and giving advantage once again to the hardy generalists. Around 5 million years into the Triassic, things finally began to stabilize. Oxygen levels crept back up. Ocean chemistry gradually normalized. Terrestrial ecosystems developed more complex soil structures as plants recolonized. And with stability came opportunity. The evolutionary experiments could begin. This is where the story gets interesting, because the survivors weren't just rebuilding what existed before. They were creating something entirely new. The dominant land animals of the Permian had been synapsids, the group that would eventually give rise to mammals. But synapsids had been devastated by the extinction. While some like Lystrosaurus survived, the group as a whole was greatly diminished. Another group saw their opportunity, the archosaurs. Archosaurs were reptiles, but a specific lineage distinct from the reptiles that would become lizards and snakes. In the Permian, archosaurs have been relatively minor players. After the extinction, they began diversifying rapidly. Early Triassic archosaurs were mostly small, quick carnivores that walked on all fours. They had certain advantages: a more efficient respiratory system than most other reptiles, an upright gait that was more energy efficient, and in some lineages, possibly even a form of warm-bloodedness. By the Middle Triassic, archosaurs had split into several distinct lineages. One branch would lead to crocodiles. Another would lead to pterosaurs, the flying reptiles. And one branch, the dinosauromorphs, would change everything. But we're not there yet. First, the world had to become strange. The Middle Triassic produced some of the weirdest creatures in vertebrate history. Without established ecological structures, evolution was experimenting wildly. Tanystropheus had a neck longer than its body and tail combined, possibly for snatching fish from the water while keeping its body safely on shore. Chaeravipteryx had enormous hind legs with flight membranes, a body plan never seen before or since. Longisquama had bizarre elongated scales along its back that some scientists think might have been precursors to feathers, though this remains controversial. The oceans weren't being left out of this evolutionary free-for-all. Ichthyosaurs appeared, reptiles that returned to the sea and evolved into forms remarkably similar to dolphins, complete with streamlined bodies and fish-like tails. Some species grew to enormous size, over 15 meters long. Nothosaurs developed, semi-aquatic predators that hunted in coastal waters. And in a twist nobody saw coming, some groups of marine reptiles developed live birth rather than laying eggs, a necessary adaptation for a fully aquatic lifestyle. Meanwhile, on land, the first true dinosaurs were emerging. They appeared around 230 million years ago, during the Carnian stage of the late Triassic. The earliest dinosaurs we know of, creatures like Heterosaurus and Eoraptor, were relatively small, between 1 and 3 meters long. They were bipedal, meaning they walked on 2 legs, which was unusual at the time. Most large animals were quadrupedal. This bipedal stance freed up their forelimbs for grasping prey and gave them speed advantages. But here's the thing that surprises most people. Early dinosaurs were not dominant. They were uncommon members of ecosystems still ruled by other archosaurs and various synapsid holdovers. For the first 15 to 20 million years of their existence, dinosaurs were minor players. The Triassic world belonged to different creatures. The true rulers of the late Triassic were the Rauisuchians, enormous predatory archosaurs that could reach lengths of 6 to 9 meters. They looked somewhat crocodile-like but walked upright on 4 legs and were purely terrestrial. Postosuchus and Saurosuchus were apex predators that would have made early dinosaurs look like snacks. Alongside them, Aetosaur, heavily armored herbivorous archosaurs, filled ecological roles similar to later armored dinosaurs, even though they weren't closely related. So why did dinosaurs eventually take over? The answer involves another catastrophe. Around 201 million years ago, at the boundary between the Triassic and Jurassic periods, Earth experienced another mass extinction. This one wasn't as severe as the Permian event. It wiped out perhaps 75% of species rather than 95%, but it was devastating enough to completely restructure ecosystems. The cause appears to have been massive volcanic eruptions associated with the breakup of Pangaea. As the supercontinent began splitting apart, enormous volumes of lava poured out across what's now the Atlantic Ocean. The Central Atlantic Magmatic Province, as it's called, was one of the largest volcanic events in Earth's history. Once again, carbon dioxide flooded the atmosphere. Temperatures spiked. Ocean chemistry went haywire. And once again, the survivors weren't necessarily the strongest or largest, but those with the right combination of traits for the new conditions. The Rauisuchians, those dominant Triassic predators, went extinct. The large herbivorous synapsids disappeared. Many of the weird experimental forms vanished. But dinosaurs made it through, and not just barely, they thrived. What gave dinosaurs the edge? Several factors probably contributed. Their efficient respiratory system, which involved air sacs that allowed continuous airflow through the lungs, similar to modern birds. This meant they could extract more oxygen from each breath, crucial in potentially low oxygen conditions. Their upright posture, which was more energy efficient for sustained activity than the sprawling gait of many competitors. And possibly their relatively fast growth rates, which allowed populations to recover quickly after disruptions. In the aftermath of the Triassic-Jurassic extinction, dinosaurs rapidly diversified and grew larger. The early Jurassic saw the emergence of the first giant sauropods, long-necked herbivores that would eventually become the largest land animals ever to exist. Theropods, the carnivorous dinosaurs, evolved into a spectacular array of forms. And a third major group, the Ornithischians, developed specialized herbivorous adaptations. Within 10 million years of the extinction, dinosaurs have become the dominant large animals on every continent. Their reign would last for 135 million years, an almost incomprehensibly long period of time. During that span, they would evolve into thousands of species, from chicken-sized hunters to 100-ton giants, from Arctic-dwelling forms to desert specialists. But their success was built on a foundation of catastrophe. Without the Permian extinction emptying the world, without the Triassic-Jurassic event eliminating their competitors, dinosaurs might have remained minor players forever. The history of life is written as much by what dies as by what survives. And so the age of dinosaurs began in earnest, not with a bang but with a quiet expansion into empty space. The early Jurassic world, roughly 201 to 174 million years ago, was dramatically different from what came before. Pangaea was still mostly intact but beginning to fracture. The climate was warm and humid across most of the supercontinent, with no polar ice caps. Sea levels were rising as the planet warmed, creating shallow inland seas that fragmented the land masses. In this greenhouse world, vegetation exploded. Ferns carpeted the ground. Conifers towered overhead. Cycads and ginkgos filled the middle layers. For herbivores, it was an all-you-can-eat buffet, and the sauropods took full advantage. These long-necked giants developed a body plan so successful it would persist, with variations, for the rest of the Mesozoic. Their small heads sat atop necks that could reach high into the canopy or sweep low across the ground. Their massive bodies housed enormous guts capable of processing huge quantities of low-quality plant material. And their pillar-like legs supported weights that would crush most other vertebrates. But here's what's fascinating about sauropod evolution. They didn't just get big. They got big in very specific ways that solved particular problems. Their necks contained numerous lightweight vertebrae with hollow spaces, air sacs that reduced weight while maintaining strength. Their respiratory systems were incredibly efficient, pulling oxygen through the lungs in one direction rather than in and out like mammals. And they laid eggs, which might seem trivial until you consider the alternative. A mammal giving live birth to a baby sauropod would be physically impossible. The mother would die. Eggs solved this problem elegantly, allowing even the largest dinosaurs to reproduce without the constraints that limited mammalian size. The theropods, meanwhile, were exploring different strategies. While sauropods went big and slow, theropods remained relatively agile. Early Jurassic forms like Dilophosaurus were already showing the basic theropod template: bipedal stance, grasping hands, sharp teeth. They weren't the apex predators yet, not the way later forms would be, but they were competent hunters filling various niches. Then something unexpected happened. Some theropods started shrinking. This seems counterintuitive in a world trending toward gigantism, but evolution doesn't follow our expectations. Smaller theropods could access different food sources, hide from larger predators, and reproduce more quickly. Some began developing feathers, probably first for insulation or display, only later for flight. This lineage would eventually lead to birds, but we're getting ahead of ourselves. The Middle Jurassic, from about 174 to 163 million years ago, is frustratingly poorly known. The fossil record from this period is patchy, leaving paleontologists with tantalizing glimpses rather than a complete picture. But what we can see suggests continued diversification. Sauropods were getting larger. The first stegosaurs appeared, those plated dinosaurs with tiny heads and huge bodies. And in the oceans, marine reptiles were reaching their own impressive sizes. It's worth pausing here to note what wasn't happening. Dinosaurs dominated the land, yes, but they never conquered the oceans or truly mastered the air during most of their reign. The seas belonged to ichthyosaurs, plesiosaurs, and later mosasaurs, none of which were dinosaurs. The skies were ruled by pterosaurs, flying reptiles that were cousins to dinosaurs but not dinosaurs themselves. This tells us something important about evolution. Dominance in one environment doesn't automatically translate to dominance everywhere. Each realm required its own specialized adaptations. The late Jurassic, 163 to 145 million years ago, is when dinosaurs really hit their stride. This is the period most people picture when they think dinosaur. Enormous sauropods like Brachiosaurus, Diplodocus, and Apatosaurus roamed what's now North America. Allosaurus stalked them, a 9-meter predator with huge jaws and slashing claws. Stegosaurus defended itself with its distinctive back plates and spiked tail. And in what's now Germany, a small feathered dinosaur called Archaeopteryx left fossils that would later help scientists understand the dinosaur-bird connection. The Morrison Formation in the American West preserves this world in exquisite detail. Picture a landscape of braided rivers and floodplains, dotted with conifer forests and fern prairies. Sauropods move through in herds, stripping vegetation. Theropods followed, looking for weak or isolated individuals. Smaller dinosaurs scurried through the undergrowth. And overhead, pterosaurs wheeled through skies that had never known a bird. But scale can be deceptive. When we see museum skeletons or movie reconstructions, we're seeing the success stories, the animals that grew large and left impressive fossils. We're not seeing the thousands of smaller species that left fragmentary remains for no fossils at all. For every Brachiosaurus, there were probably dozens of chicken-sized dinosaurs we'll never know existed. The fossil record is biased toward big animals with hard bones in the right environments. Everything else is mostly invisible to us. The Cretaceous period, from 145 to 66 million years ago, saw dinosaurs reach their peak diversity. This wasn't because they were getting better at being dinosaurs. It was because the world itself was fragmenting. Pangaea had fully broken apart. Sea levels were extraordinarily high, creating more coastline and shallow seas than at any other point in Earth's history. Continents were isolated from each other, allowing evolution to proceed independently on different land masses. This geographic separation led to spectacular diversity. In South America, massive carnivores like Giganotosaurus evolved, possibly even larger than Tyrannosaurus rex. In Africa, Spinosaurus developed a bizarre sail-backed body plan and semi-aquatic lifestyle. In Asia, the tyrannosaurs were beginning their rise to dominance. And in North America, the famous late Cretaceous fauna was assembling: Triceratops, Ankylosaurus, Pachycephalosaurus, and eventually T. Rex itself. The Cretaceous also saw the rise of flowering plants, angiosperms, which would fundamentally reshape terrestrial ecosystems. Before this, plant reproduction was slow and inefficient. Conifers, ferns, and cycads dominated. But flowering plants reproduced faster, grew more quickly, and formed more complex relationships with animals. They offered new food sources, fruits, nectar, and more nutritious leaves. Herbivorous dinosaurs adapted, developing sophisticated chewing mechanisms. Hadrosaurs, the duck-billed dinosaurs, had hundreds of teeth arranged in dental batteries that could grind through tough plant material. Ceratopsians had powerful beaks and shearing teeth. Ankylosaurs had fermentation chambers in their guts. These weren't simple animals mindlessly eating and reproducing. Evidence suggests complex behaviors, parental care in some species, possible migratory patterns, social structures, even potential territorial displays. We find bone beds with dozens of individuals of the same species, suggesting herding behavior. We find nests with carefully arranged eggs and evidence of adults returning to nesting sites. Some species show sexual dimorphism, different body features between males and females, hinting at complex mating rituals. By the late Cretaceous, roughly 80 to 66 million years ago, dinosaur ecosystems had reached a level of complexity comparable to modern ecosystems. There were small insectivores, medium-sized herbivores, giant browsers, pack hunters, and solitary apex predators. There were specialists and generalists, lowland forms and upland forms. In some environments, dinosaur diversity rivaled what we see in modern mammal communities. And they were still evolving, still adapting, still producing new forms. There's no evidence they were in decline before the asteroid hit. Some paleontologists have argued that dinosaur diversity was dropping in the final million years of the Cretaceous, but this is hotly debated and probably reflects biases in the fossil record rather than actual decline. The dinosaurs weren't old and tired. They weren't evolutionary dead ends waiting for extinction. They were thriving. Which makes what happened next even more shocking. An asteroid roughly 10 kilometers across, traveling at about 64,000 kilometers per hour, slammed into what's now Mexico's Yucatan Peninsula. The impact released energy equivalent to billions of nuclear bombs. It vaporized rock, created a crater almost 200 kilometers wide, and sent shockwaves around the planet. Within hours, debris was raining down globally, igniting fires across multiple continents. Within days, dust and sulfur compounds had blocked out the sun. Within months, photosynthesis had ceased almost everywhere. The dinosaurs, those magnificent animals that had dominated for 165 million years, died. Not all at once, and not all for the same reasons. Some starved when plants died. Others froze when temperatures plummeted. Many drowned in tsunamis or suffocated in toxic air. The large ones went first, unable to find enough food to maintain their massive bodies. The specialists followed, their narrow ecological niches collapsing. What survived were the small, the flexible, the generalists. Animals that could hide, that could eat almost anything, that could tolerate cold and darkness. And among the survivors, barely, were the birds. Birds are dinosaurs. Not descendants of dinosaurs, not related to dinosaurs. They are dinosaurs, the only lineage that made it through. Every sparrow, every pigeon, every eagle is a living theropod, carrying forward a heritage that stretches back to the Triassic. The asteroid didn't end the dinosaur story. It edited it down to a single surviving branch. But let's be precise about what survived. Not all bird groups made it. The Cretaceous sky was full of avian diversity, toothed birds, flightless diving birds, large terrestrial forms. Most died. What crossed the boundary were small, likely generalist species. Birds that could eat seeds, insects, maybe carrion. birds that didn't depend on specific forest types or particular prey animals. In the immediate aftermath, with forests burned and food chains shattered, flexibility was everything. The early Paleocene, the period right after the extinction, was a drastically simplified world. Fossil sites from this time show ecosystems with far fewer species, simpler structures, less specialization. The recovery wasn't instant. For the first million years or so, life struggled. Ferns exploded across the landscape, a classic disaster response. They're fast-growing, spore-based, and thrive in disturbed environments. Pollen records show what's called a fern spike right at the extinction boundary, a sudden overwhelming dominance of fern spores in the geological record. Slowly, ecosystems rebuilt. Flowering plants returned, though the composition changed. Some Cretaceous plant families vanished entirely. Others that had been minor players became dominant. Animal communities reassembled, but with completely different caste lists. The niches that dinosaurs once filled, gigantic herbivores, massive predators, were now empty. And into that vacuum stepped the mammals. Mammals have been around almost as long as dinosaurs, originating in the late Triassic around 225 million years ago. But for the entire Mesozoic, they'd been bit players. Small, mostly nocturnal, eating insects and seeds and staying out of the way. The largest known Mesozoic mammal, Repenomamus, was about the size of a badger and possibly 8 baby dinosaurs, but that was exceptional. Most were mouse-sized or smaller. Why were they so small? Probably because dinosaurs occupied all the larger ecological roles. There was simply no space. Any mammal that tried to get bigger would be competing directly with vastly more successful reptilian forms. So mammals stayed small, stayed hidden, and survived in the margins. Then the asteroid reset the board. Within 10 million years, an eye blink in geological terms, mammals exploded in size and diversity. By the early Eocene, roughly 56 million years ago, there were mammal predators as large as bears, herbivores the size of rhinos, and bizarre experimental forms that have no modern equivalents. Consider Androsarchus, known only from a massive skull found in Mongolia. It lived about 45 million years ago and may have been the largest mammalian land predator ever, possibly reaching a ton in weight. Or the Brontotheres, rhino-like herbivores with elaborate horns and head crests. Or the Entelodonts, sometimes called hell pigs, aggressive omnivores with bone-crushing jaws. The Paleocene and Eocene were periods of wild evolutionary experimentation. With so many niches empty, natural selection could explore options that would never have been viable in the Mesozoic. Some experiments worked. Most didn't. The fossil record from this time is full of short-lived lineages, creatures that appeared, diversified briefly, then vanished as better adapted groups replaced them. Primates emerged during this chaos. The earliest known primate fossils date to around 55 million years ago. They were small, arboreal, probably similar to modern tree shrews or small lemurs. Nothing about them suggested future dominance. They were one evolutionary experiment among thousands. But they had certain advantages. grasping hands with opposable digits, useful in trees. Forward-facing eyes providing depth perception, critical for judging distances when jumping between branches. Relatively large brains for their body size, though still tiny by modern standards. These weren't dramatic advantages. They didn't make primates dominant. They just made them viable in a particular ecological niche, the forest canopy. For tens of millions of years, that's where primates stayed. Up in the trees, eating fruits and insects, slowly diversifying. By the Oligocene, around 30 million years ago, there were monkeys and early apes. Still arboreal, still relatively small-brained, still just another group of mammals among many. The critical shift began much later, in Africa, probably around 7 to 6 million years ago. Climate change was driving it. Global temperatures were dropping, forests were fragmenting, and grasslands were expanding. Some primate populations found themselves spending more time on the ground, moving between scattered forest patches. Walking upright on two legs, bipedalism, offered advantages in this environment. It freed the hands for carrying food or tools. It allowed seeing over tall grass. It was more energy efficient for long-distance travel than quadrupedal knuckle walking. Natural selection began favoring individuals who were better at walking upright. This is where the human lineage begins to separate from other apes. Not with intelligence. Not with tool use. Those came later. The first defining characteristic of our lineage was simply the ability to walk efficiently on two legs. Fossils from this period are rare and fragmentary. We have Sahelanthropus, dated to about 7 million years ago, known from a partial skull. We have Ororan, about 6 million years old, known from a few bones suggesting upright walking. We have Ardipithecus, around 4.4 million years ago, definitely bipedal but still spending time in trees. These weren't humans. They were apes experimenting with a new way of moving. Their brains were still chimpanzee-sized, around 350 to 400 cubic centimeters. They probably didn't make complex tools. They lived in small groups in woodland environments. If you saw one, you wouldn't think, that's going to evolve into something that dominates the planet. You'd think, interesting ape. Around 4 million years ago, a new genus appeared, Australopithecus. These were the first hominins to really commit to terrestrial life. They walked upright habitually, though their arms were still relatively long and they probably still climbed trees for safety and food. Their brains were slightly larger than earlier forms, maybe 400 to 500 cubic centimeters, but still well within ape range. The most famous Australopithecus fossil is Lucy, discovered in Ethiopia in 1974. She lived about 3.2 million years ago, stood roughly 1.1 meters tall, and weighed perhaps 30 kilograms. Her skeleton shows clear adaptations for bipedalism, a bowl-shaped pelvis, a knee angle that kept her center of gravity over her feet, a forward-positioned foramen magnum where the spine connects to the skull. For over 1 million years, various Australopithecus species lived across eastern and southern Africa. They were successful animals, well adapted to their environments. But they were still fundamentally apes. They didn't build shelters, didn't control fire, didn't create complex tools. Then, around 2.8 million years ago, something shifted. We start finding stone tools in the archaeological record. Not sophisticated tools, just rocks deliberately chipped to create sharp edges. But this was new. This was technology, however primitive. The first species clearly associated with stone tool manufacture is Homo habilis, which appeared around 2.4 million years ago. Habilis means handy man, and it's an appropriate name. Their brains were larger than Australopithecus, around 600 cubic centimeters, and their hands show better precision grip. Still, Homo habilis wasn't dramatically different from earlier hominins. They were still small, probably around 1.3 meters tall. They probably still spent time in trees. Their tools, the so-called Oldowan industry, were simple, sharp flakes struck off larger rocks, useful for cutting meat or processing plant materials. What matters is the principle. Using tools isn't unique to humans, many animals use tools. But making tools, deliberately modifying objects to create something more useful, that's rarer. And passing that knowledge down through generations, that's rarer still. With stone tools, we see the first glimmers of culture, information transmission beyond genetics. Around 2 million years ago, a new species emerged, Homo erectus. This is where things get interesting. Erectus was taller, averaging around 1.8 meters. More importantly, their brains were substantially larger, ranging from 800 to over 1,000 cubic centimeters. They made more sophisticated tools, the Acheulean hand axes, carefully crafted teardrop-shaped implements that required planning and skill. And Homo erectus walked out of Africa. Fossils have been found in Georgia, China, Indonesia. This species, or closely related forms, spread across the Old World, adapting to environments from tropical forests to temperate grasslands. They likely controlled fire, though the evidence is debated. They hunted cooperatively. They may have had basic language. Homo erectus was successful. Incredibly successful. They lasted for over 1.5 million years, far longer than our species has existed so far. They were the first truly cosmopolitan hominin, the first to demonstrate that our lineage could adapt to wildly different environments. But they weren't modern humans. Their brains, while large, were still structured differently. Their skulls were thick-boned with prominent brow ridges. Their bodies were robust, built for strength rather than endurance running. They made the same basic tool types for hundreds of thousands of years with little innovation. What happens next is complicated. Between about 800,000 and 300,000 years ago, Homo erectus populations in different regions began diverging. In Africa, they evolved toward forms with more gracile skeletons and larger, rounder skulls. In Europe and Western Asia, they evolved into Neanderthals. In Eastern Asia, they became Denisovans and possibly other groups. The human family tree during this period wasn't a straight line. It was a bush, multiple species existing simultaneously, sometimes in the same regions. And they didn't stay isolated. Genetic evidence shows they interbred when they met. Neanderthals appeared around 400,000 years ago in Europe and Western Asia. They weren't brutish cavemen. That's Victorian mythology. Neanderthals had brains as large as or larger than modern humans, averaging around 1,400 cubic centimeters. They made sophisticated tools, controlled fire expertly, built shelters, buried their dead with apparent ritual. They survived ice ages in some of the harshest environments on Earth. They hunted mammoth and woolly rhinoceros. They may have made symbolic art, though the evidence is contested. They were formidable survivors. Denisovans are more mysterious. We know them primarily from DNA extracted from a few bone fragments found in a cave in Siberia. Genetic analysis shows they were distinct from both Neanderthals and modern humans, yet they interbred with both. Their genes persist in modern populations, particularly in Melanesia and Australia, suggesting they ranged across much of Asia. Meanwhile, in Africa, our direct ancestors were evolving. The earliest fossils that look anatomically modern, Homo sapiens, date to around 300,000 years ago. Sites in Morocco and Ethiopia show skulls with the rounded cranium, flat face, and small teeth characteristic of our species. But here's something crucial. Early Homo sapiens weren't behaviorally modern. For over 200,000 years, they made the same types of tools their ancestors did. They didn't create complex art. They didn't develop sophisticated symbolic culture. Anatomical modernity came first. Behavioral modernity took much longer. What changed? Around 70,000 years ago, something happens in the archaeological record. Suddenly we see evidence of symbolic thinking. Engraved ochre, shell beads used as ornaments, more complex tools made from bone and antler. This intensifies around 50,000 years ago. Cave paintings appear. Sculptures. Musical instruments. Elaborate burial practices. This is often called the Upper Paleolithic Revolution, though it's more of a gradual acceleration than a sudden shift. The key innovation was probably language. Not simple communication, but full syntactic language capable of expressing abstract concepts, discussing things not immediately present, telling stories about the past and planning for the future. Language transforms cognition. It allows information to accumulate across generations far more efficiently than imitation alone. It enables cooperation at scales impossible without it. Once language evolved, culture could evolve faster than biology. Around 60,000 years ago, modern humans began leaving Africa in significant numbers. They moved along coastlines into southern Asia, reaching Australia by around 50,000 years ago. They spread north into Europe, arriving around 45,000 years ago where they encountered Neanderthals. They pushed east across Asia, eventually crossing into the Americas, probably around 15 to 20,000 years ago. And everywhere they went, they replaced the existing hominin species. Neanderthals disappeared around 40,000 years ago. Denisovans vanished. Homo erectus, if any population still existed in remote areas, went extinct. Within a remarkably short time, geologically speaking, Homo sapiens became the only surviving human species on Earth. Why? What made us successful where other human species failed? It wasn't brain size. Neanderthals had brains as large as ours. It probably wasn't individual intelligence. A Neanderthal child raised in modern society would likely function normally. The advantage was social. Modern humans appear to have been better at cooperation in large groups, better at cultural transmission, better at innovation. Our tools became more sophisticated not because our brains suddenly got bigger, but because we shared information more efficiently. Each generation built on the previous one's knowledge. Neanderthals made essentially the same tools for 200,000 years. Modern humans went from stone tools to space stations in 50,000 years. That's not biological evolution. That's cultural evolution enabled by language and social structure. But here's the uncomfortable part. When modern humans and Neanderthals met, they didn't just peacefully coexist. Genetic evidence shows they interbred. Most non-African people today carry 1 to 2% Neanderthal DNA. Some carry Denisovan DNA as well. But those hybrids were absorbed into modern human populations, not the reverse. The Neanderthal genome essentially went extinct except for small fragments preserved in us. Whether this replacement was violent or not is debated. There's no clear evidence of warfare, no mass graves showing conflict. But absence of evidence isn't evidence of absence. What we know is this: when modern humans and Neanderthals occupied the same regions, Neanderthals disappeared within a few thousand years. Competition for resources probably played a role. If modern humans were even slightly more efficient hunters, slightly better at exploiting the environment, they would gradually outcompete other species. Disease might have been a factor. When previously isolated populations meet, pathogens can devastate the group with no immunity. Climate change probably contributed. The period between 50,000 and 40,000 years ago was climatically unstable, with rapid temperature swings. Species already stressed by environmental shifts would be more vulnerable to competition. Whatever the exact mechanism, the result was clear. By 30,000 years ago, we were alone. For the first time in millions of years, only one species of human walked the earth. That isolation is unusual in our lineage's history. For most of hominin evolution, multiple species coexisted. Australopithecus afarensis shared East Africa with Australopithecus ethiopicus and Kenyanthropus. Homo erectus lived alongside Homo habilis and Paranthropus. Neanderthals, Denisovans, and modern humans overlapped for tens of thousands of years. We're used to being the only humans, but it's a recent condition. Once alone, modern humans didn't stop evolving. Evolution never stops. Over the past 30,000 years, we've adapted to new diets, new climates, new diseases. Populations that adopted agriculture developed higher frequencies of genes for digesting lactose and processing starches. Populations in high altitudes evolved better oxygen utilization. Populations in different latitudes evolved varying levels of skin pigmentation to balance vitamin D production against UV radiation damage. These are minor changes, nothing approaching speciation. But they're real. The human species isn't static. We're still evolving, though cultural change now vastly outpaces biological change. And then something unprecedented happened. Around 12,000 years ago, humans began deliberately cultivating plants and domesticating animals. Agriculture emerged independently in multiple locations: the Fertile Crescent, China, Mesoamerica, the Andes, Sub-Saharan Africa. This wasn't progress in any moral sense. Early agriculture was hard work, probably harder than hunting and gathering. It led to worse nutrition, more disease, social inequality. But it allowed denser populations. Agricultural societies could support more people per square kilometer than hunter-gatherers. Numbers matter in competition. Agricultural populations grew and spread, absorbing or displacing hunter-gatherer groups. With agriculture came permanent settlements, then cities, then civilization with all its benefits and horrors. Writing appeared around 5,000 years ago, enabling information storage beyond individual memory. Suddenly knowledge could accumulate without loss between generations. Science became possible, systematic investigation and recording of natural phenomena. Technology accelerated. We went from bronze to iron to steel. From animal power to steam to electricity to nuclear energy. From signal fires to telegraph to internet. The pace of change became exponential. A human from 10,000 years ago, transported to 5,000 years ago, would find the world different but comprehensible. A human from 5,000 years ago transported to today would think they'd entered a realm of magic. Yet biologically, we're nearly identical to humans from 50,000 years ago. Our brains haven't changed significantly in size or structure. What's changed is culture, accumulated knowledge passed down and built upon. We're not smarter than our ancestors. We just know more. A Paleolithic human with their brain intact, raised in modern society, would function normally. They'd learn language, mathematics, technology just like anyone else. The hardware hasn't upgraded much. The software has exploded. This is why the human story is so strange. For most of our history, we evolved like every other species, through random mutation and natural selection, slowly adapting to changing environments. Then culture took over. We began shaping our environment rather than being shaped by it. We created new selection pressures. We moved into environments we weren't adapted for and invented technologies to survive there. We are now the primary force shaping Earth's biosphere, whether we intended that or not. And that brings us to now. 7.8 billion humans covering the planet, living in environments from Antarctic research stations to space stations orbiting above. We've eliminated smallpox. We've split the atom. We've walked on the moon. We've sequenced our own genome and begun editing it. The question becomes, what happens next? We're standing at a junction unlike any species has ever encountered. For the first time in Earth's history, one organism has the capacity to consciously direct its own evolution and reshape the planet's entire biological future. That's not metaphor. That's measurable reality. The last century alone has altered Earth more than the previous 10,000 years combined. We've moved more sediment than all natural erosion processes. We've changed atmospheric chemistry faster than any geological event except major asteroid impacts. We've created materials that will persist in the geological record for millions of years. Plastic, concrete, radioactive isotopes from nuclear testing. Future geologists will identify a distinct layer marking our presence, a boundary as clear as the one separating dinosaurs from mammals. Population growth has been exponential. It took all of human history until 1804 to reach 1 billion people. We hit 2 billion by 1927, 3 billion by 1960, 4 billion by 1974. The curve keeps climbing, though growth rates are finally slowing in developed nations. Current projections suggest we'll peak somewhere between 10 and 11 billion before stabilizing or declining. That's assuming current trends continue, which is never guaranteed. Resource consumption has grown even faster than population. The average person today uses more energy, more water, more materials than at any point in history. This creates obvious problems. Fossil fuels that took hundreds of millions of years to form are being burned in centuries. Aquifers that filled over millennia are being drained in decades. Topsoil that accumulated over thousands of years is eroding in generations. These aren't sustainable trajectories. Something has to change. Climate change is the most visible consequence. By burning fossil carbon and releasing it into the atmosphere, we've increased CO2 concentrations from about 280 parts per million before industrialization to over 420 today. That's higher than any point in the last 3 million years. The greenhouse effect is basic physics. More CO2 means more trapped heat. Global average temperatures have risen about 1.2 degrees Celsius since pre-industrial times. That sounds small until you realize it's an average across the entire planet, oceans included. Land temperatures have risen more. Arctic temperatures have risen much more. The effects cascade. Ice sheets melt. Sea levels rise. Weather patterns shift. Ecosystems that evolved under specific temperature ranges suddenly face conditions they're not adapted for. Species migrate toward the poles or higher altitudes, seeking familiar climates. Those that can't migrate fast enough face extinction. Current extinction rates are estimated at 100 to 1,000 times the background rate. We're in the opening phase of Earth's sixth mass extinction, and we're causing it. But here's what makes this different from previous extinctions. We know it's happening. We can measure it. We can model future scenarios. And we have the technological capacity to respond. Whether we actually will is a separate question, one that depends on economics, politics, human psychology, factors far outside the scope of geology or biology. The science is clear. The response is uncertain. Technology continues accelerating. Artificial intelligence is advancing faster than most predicted. Quantum computing is moving from theory to application. Genetic engineering has progressed from science fiction to routine laboratory procedure. CRISPR allows precise editing of DNA sequences. We've already used it to cure genetic diseases in individual patients. We're discussing using it for enhancement, not just therapy. The boundary between treating illness and improving capability is philosophically blurry and getting blurrier. Space exploration has resumed after decades of relative stagnation. Private companies are launching rockets that land themselves. Plans exist for permanent lunar bases and crewed missions to Mars within the next 2 decades. These aren't fantasies anymore. They're engineering projects with timelines and budgets. If humanity becomes multiplanetary, that changes the equation entirely. No single catastrophe could end our species. That's never been true before. Synthetic biology is creating organisms with no natural counterpart. Bacteria engineered to produce insulin. Yeast modified to generate spider silk proteins. Algae designed to capture carbon more efficiently than natural photosynthesis. We're not just modifying existing life anymore. We're designing new life from scratch. The implications are staggering and largely unexplored. Meanwhile, we still carry the legacy of our evolutionary past. Our brains evolved for small group dynamics, not global civilization. We're wired to respond to immediate threats, not slow-moving catastrophes like climate change. We form tribal identities easily, treating outsiders with suspicion or hostility. We're susceptible to cognitive biases that served us well in the Paleolithic but cause problems now. Confirmation bias. Availability heuristic. Tribalism. These aren't bugs in human psychology. They're features that increased survival in ancestral environments. They just don't match the challenges we face today. Social media has amplified these tendencies. Algorithms optimized for engagement end up promoting outrage and polarization because those emotions drive clicks. Information spreads faster than ever, but misinformation spreads just as fast. We have access to more knowledge than any previous generation, but also more noise. Distinguishing signal from noise requires skills our education systems haven't caught up with yet. The question of artificial intelligence deserves separate consideration. If we create machines that match or exceed human intelligence, what happens next? Do they remain tools we control? Do they become partners we collaborate with? Do they replace us entirely? Nobody knows. The trajectory is unclear because we're still debating what intelligence actually means and how consciousness emerges. These aren't just technical questions. They're philosophical ones with no obvious answers. Some argue we're approaching a technological singularity, a point where change happens so rapidly that prediction becomes impossible. Others think that's overblown speculation. What's certain is that the next century will differ from the last more than the last differed from the one before it. Extrapolating current trends is probably futile. surprises are guaranteed. Humanity's future branches into scenarios wildly different from each other. In optimistic projections, we solve climate change through renewable energy and carbon capture. We cure aging through genetic medicine and cellular repair. We spread throughout the solar system, then beyond. We merge with our technology, enhancing our capabilities far beyond biological limits. We become something new, something that would be unrecognizable to our ancestors but still carries forward the core of what we are. In pessimistic scenarios, we fail to address existential risks. Climate change triggers cascading ecosystem collapses. Resource wars destabilize global civilization. A pandemic worse than COVID-19 spreads before we can respond. Nuclear weapons are used in regional conflicts that spiral out of control. Artificial intelligence is developed without adequate safety measures. Any of these could dramatically reduce human population or technological capacity, potentially permanently. Most likely, the future lies somewhere between extremes. Muddy. Complicated. Neither utopia nor apocalypse, but a messy continuation of what we've always done, solving problems while creating new ones, advancing in some areas while regressing in others. That's been the human pattern for millennia. No reason to expect it to change now. What we can say with confidence is this: the story that began with single cells in ancient oceans, that continued through the Cambrian explosion and the colonization of land, that survived 5 mass extinctions and countless smaller catastrophes, that produced dinosaurs and mammals and eventually us, that story isn't over. It's still being written. We're writing it now, whether we realize it or not. Every choice we make, individual and collective, shapes what comes next. 4 billion years of evolution produced a species capable of understanding its own origins, of reconstructing the deep history of life on this planet, of recognizing its place in the vast sweep of biological time. That understanding changes nothing about the facts themselves. The rocks don't care if we study them. The fossils don't care if we interpret them correctly. But it changes us. Knowing where we came from affects how we think about where we're going. We are not separate from nature. We are nature, evolved through the same processes as every other organism, subject to the same physical and chemical laws. Our intelligence, our technology, our civilization, all of it emerged from natural processes operating over deep time. We're not above the system. We're part of it. An unusual part, granted, one with unprecedented impact. But still part of the same system that produced stromatolites and trilobites and Tyrannosaurus and every other form life has ever taken. The Earth will continue with or without us. Life survived worse than anything we can do short of physically destroying the planet. After we're gone, whether that's 1,000 years from now or 1,000,000, evolution will continue. New species will emerge. Ecosystems will reorganize. The biosphere will persist in some form until the sun expands and sterilizes the surface in about 1 billion years. That's the timeline we're working with. Our impact will be measurable in the geological record, a thin layer marking the Anthropocene, the age when one species briefly dominated the planet's systems. What that layer will show depends on what we do next. Whether it records a mass extinction followed by recovery, or marks a transition to something genuinely new, or represents a boundary after which the trajectory of life on Earth changed permanently, that's still being determined. The story continues. We're living in the latest chapter, writing it in real time. What happens next isn't predetermined. It depends on choices we haven't made yet, technologies we haven't invented, problems we haven't solved. The deep past teaches us that life adapts, persists, transforms. The future remains open. Looking back across this immense span of geological time reveals something unsettling. The Permian extinction wasn't an isolated anomaly. It was part of a pattern that's repeated throughout Earth's history. Life builds complexity over millions of years, ecosystems stabilize, species diversify, and then something shatters it all. The planet resets. What survives isn't necessarily what deserves to survive by any moral standard. It's what happens to have the right traits at the right moment. The survivors of the Permian weren't superior organisms. They were lucky. Small size, low metabolic rates, generalist diets, these traits meant nothing special in stable times. They became everything when conditions turned hostile. The same principle applies to every mass extinction. The traits that ensure survival during catastrophe are often useless or even disadvantageous during normal times. Evolution doesn't prepare for disasters. It can't. Natural selection optimizes for current conditions, not hypothetical future ones. This creates a fundamental vulnerability in complex ecosystems. The more specialized organisms become, the more efficient they are at exploiting their specific niches, the more fragile they become when those niches disappear. The Permian Ocean was full of highly specialized filter feeders, predators adapted to specific prey, organisms with complex life cycles requiring stable conditions. When the chemistry changed and oxygen vanished, that specialization became a death sentence. The generalists, the unspecialized, the organisms doing moderately well at many things rather than excelling at one thing, they persisted. We see echoes of this pattern in modern conservation biology. Species with narrow habitat requirements, specialized diets, small populations, those are the ones going extinct first as humans alter the planet. Generalist species, rats, crows, coyotes, cockroaches, they're thriving. Not because they're better in any absolute sense, but because they're flexible. When environments change rapidly, flexibility matters more than optimization. The Permian extinction also demonstrates how interconnected Earth's systems are. The volcanic eruptions didn't directly kill most organisms. They triggered cascading failures. Atmospheric changes led to ocean warming. Ocean warming caused oxygen depletion. Oxygen depletion enabled hydrogen sulfide production. Hydrogen sulfide poisoned the remaining life. Each step amplified the previous one. The system had feedback loops that, once triggered, became self-reinforcing. The planet wasn't just damaged. It was actively hostile, generating conditions that prevented recovery. Modern climate change shows similar dynamics. We're not just warming the atmosphere. We're acidifying oceans, disrupting circulation patterns, melting ice that reflects sunlight, thawing permafrost that releases more greenhouse gases. Each change triggers others. The system has tipping points where positive feedback loops take over and changes become self-sustaining regardless of what triggered them initially. The Permian shows what happens when those loops engage fully. It took millions of years for the planet to stabilize. But here's what the Permian extinction ultimately proves. Life doesn't give up easily. Even when 96% of species vanish, when the oceans turn toxic and the atmosphere becomes nearly unbreathable, when the planet seems utterly hostile to complex organisms, life finds a way. Not through any mystical force or intention. Through sheer probability. With enough individual organisms, enough genetic diversity, enough geographic spread, some will survive almost anything. And from those survivors, complexity eventually rebuilds. The recovery wasn't immediate or smooth. It took fits and starts, false recoveries followed by setbacks, millions of years of ecological simplicity before the biosphere regained its previous complexity. But it happened. The Triassic world that emerged was different from the Permian world that died, but it was just as complex, just as diverse. Different players, different rules, same fundamental processes. That's the pattern visible across all of Earth's history. Destruction, survival, recovery, diversification. The specific organisms change. The underlying dynamics don't. Life as a planetary phenomenon is remarkably resilient. Individual species, even entire families or orders, are expendable. The system continues. Which brings us back to our current situation. We're changing the planet faster than any species except possibly some ancient photosynthetic bacteria billions of years ago. We're driving extinction rates to levels comparable with the worst events in geological history. We're altering ocean chemistry, atmospheric composition, global temperatures. The parallels to the Permian are uncomfortable and increasingly obvious. The difference is awareness. The organisms dying in the Permian had no comprehension of what was happening. They just lived and died according to their biology while the world became increasingly hostile. We know. We can measure the changes in real time. We can model future trajectories. We can, in principle, alter our behavior to avoid the worst outcomes. Whether we actually will remains the defining question of our era. The Permian extinction teaches us that planetary systems have limits. Push them hard enough and they break in ways that are catastrophic, long-lasting, and affect everything alive. It also teaches us that recovery is possible but measured in geological timescales that are meaningless to individual organisms or even entire species. The planet will be fine eventually. The question is whether we'll be around to see it. The survivors of the Permian were small, unspecialized organisms hiding in refuges. That's probably not the future most humans envision for themselves. Earth's history is written in stone, in fossils, in chemical signatures left by organisms dead for hundreds of millions of years. Those records don't lie. They show a planet that cycles through periods of stability and catastrophe with reliable regularity. They show that dominance is temporary, that no group remains on top forever, that the traits ensuring success in one era become liabilities in the next. They show that life persists but individual lineages don't. Everything alive today descends from survivors of previous catastrophes. Everything alive today is temporary, including us. The Permian was Earth's deadliest catastrophe, but it wasn't the last. It won't be the last. The planet will experience future disruptions, whether from volcanic activity, asteroid impacts, or slower processes we haven't identified yet. Over geological timescales, catastrophe is normal. Stability is the anomaly. We evolved during an unusually stable period and built a civilization assuming that stability would continue indefinitely. The deep past suggests that's optimistic. What we do with this knowledge is up to us. We can recognize our place in Earth's long history, acknowledge that we're subject to the same rules as every other organism, and act accordingly. Or we can assume we're somehow exempt, that our technology makes us immune to planetary-scale disruptions, that the patterns visible across billions of years somehow don't apply to us. The rocks suggest otherwise. The fossils suggest otherwise. Every previous dominant group thought it would last forever. None did. We're not special in that regard. We're just the current experiment, playing out in real time, with an ending yet to be determined. Deep in the frozen vacuum of space, chunks of ancient ice and rock are hurtling toward Earth at speeds that would vaporize steel on contact. Inside them, locked within crystalline structures older than our sun, might be the answer to humanity's oldest question. Where did we come from? For decades, scientists dismissed comets as cosmic debris. Dirty snowballs with no real significance beyond their spectacular light shows. Then something changed. When we finally caught up to these objects, when our spacecraft touched them and tasted their chemistry, we found something nobody expected. The building blocks of life itself, fully formed, perfectly preserved, waiting. This isn't speculation anymore. It's data. Hard, repeatable, undeniable data that's forcing us to rewrite the story of life on Earth. Before we had telescopes, before we understood what comets were, they terrified us. Ancient civilizations saw them as omens. Disasters written in fire across the night sky. The Romans called them hairy stars because of their streaming tails. Chinese astronomers meticulously recorded their appearances, convinced they predicted the fall of dynasties. Nobody imagined these objects might be delivering something rather than threatening it. The modern scientific view wasn't much kinder. Through most of the 20th century, comets were considered interesting but irrelevant to the story of life. They were leftovers from the solar system's formation, frozen relics that occasionally swooped through the inner planets before vanishing back into the dark. Beautiful, yes. Important to biology, not a chance. That assumption held until we started catching them. In 2004, NASA's Stardust mission did something remarkable.
Guidance is internal. Roll program initiated.
It flew through the coma of Comet Wild 2, that glowing cloud of gas and dust surrounding the nucleus, and collected samples. Not much, just microscopic particles captured in a substance called aerogel, but enough. When those samples returned to Earth 2 years later, the results stopped people in their tracks. Glycine. A simple amino acid, one of the fundamental building blocks that cells use to construct proteins. It was sitting right there in the comet dust, formed in the freezing darkness of space long before Earth even existed. That discovery opened a door. If glycine could form in comets, what else might be hiding in them? The answer came from an unlikely source. In 2014, the European Space Agency's Rosetta mission arrived at Comet 67P, a rubber duck-shaped chunk of ice about 4 kilometers across. Instead of just flying past, Rosetta stayed. It orbited for 2 years, watching the comet wake up as it approached the sun, measuring everything it could. What Rosetta found wasn't just interesting, it was revolutionary. The comet was outgassing 16 different organic compounds, not simple molecules, but complex carbon-based structures. Formaldehyde, methanol, ethanol, amino acids, and something else. Something that made biologists sit up and pay attention. Phosphorus. An element absolutely essential for life as we know it. It forms the backbone of DNA. It's in every cell membrane. Without phosphorus, Earth-style biology simply cannot function. And here it was, streaming off a comet billions of miles from the nearest living thing. The implications were staggering. These weren't random chemicals. They were the exact ingredients you'd need to start building the machinery of life. But finding ingredients isn't the same as proving they created something. You can have flour, eggs, and sugar sitting on a counter, and they won't spontaneously become a cake. Something has to bring them together under the right conditions. Something has to do the mixing. That's where Earth's early history becomes critical. 4.5 billion years ago, our planet was a molten nightmare. Volcanic hellscape, no stable crust, certainly no oceans. Not exactly a promising environment for delicate organic chemistry. Yet somehow, within a few 100 million years, life appeared. Not gradually, not tentatively, but explosively. By 3.8 billion years ago, we have clear evidence of cellular life already thriving. That timeline has always bothered scientists. It's too fast. Earth barely had time to cool down before biology showed up. Where did all the necessary building blocks come from? How did they organize themselves so quickly? The traditional answer was that Earth made them itself. Lightning strikes in a primordial atmosphere, volcanic vents pumping out chemicals, ultraviolet radiation breaking apart simple molecules and recombining them into complex ones. The famous Miller-Urey experiment in 1953 seemed to prove this was possible. Put some basic gases in a flask, add electricity to simulate lightning, and amino acids appear. Except there's a problem. We got the atmosphere wrong. The Miller-Urey experiment used methane, ammonia, and hydrogen, a strongly reducing mixture that favors organic chemistry. But geological evidence now suggests early Earth's atmosphere was mostly carbon dioxide and nitrogen. Run the experiment with those gases and you get almost nothing. The chemistry doesn't work. So if Earth wasn't making its own organic molecules efficiently, where were they coming from? Look up. Every year, Earth sweeps through debris left behind by comets. We see it as meteor showers, beautiful streaks of light as tiny particles burn up in the atmosphere. But not everything burns. Some material makes it through, settling gently onto the surface. Modern estimates suggest Earth gains about 40,000 tons of cosmic dust annually. That's now, in a relatively clean solar system. 4 billion years ago, during the period we call the Late Heavy Bombardment, the rate was millions of times higher. Picture it. Young Earth, still cooling, oceans just beginning to condense from steam. And it's being absolutely pelted by comets and asteroids, hundreds of impacts every year, each one delivering its cargo of organic molecules. Not just simple stuff, but complex, ready-made building blocks for biochemistry. The entire planet becomes a chemistry lab being constantly restocked with new ingredients. This is where the math gets interesting. Calculate the total mass of cometary material that hit Earth during the first billion years. Factor in the concentration of organic compounds we've measured on real comets. Run the numbers and you get something shocking. Comets could have delivered more organic carbon to early Earth than the planet could possibly have made on its own. By a lot. Maybe by factors of thousands or millions. But quantity isn't everything. You also need the right delivery mechanism. Drop complex organic molecules onto a planet from space and they face a problem. They're moving at cosmic speeds, tens of kilometers per second. That kind of impact generates heat. Lots of heat. Enough to break apart most chemical bonds and destroy exactly the compounds you're trying to deliver. Except comets have a trick. They're not solid rock. They're mostly ice, mixed with dust and organics. When a comet hits an atmosphere, or even a primordial ocean, that ice acts like a cushion. It absorbs energy, vaporizes, creates a shock buffer. Calculations show that organic molecules buried inside cometary ice can survive impacts that would obliterate anything else. The ice protects its cargo all the way down. Even better, that ice itself is valuable. Early Earth needed water. Lots of water. Our planet formed close to the sun, in a region too hot for ice to condense. The water in our oceans had to come from somewhere colder. Comets fit perfectly. They're essentially giant ice cubes that formed in the outer solar system and then migrated inward. Each impact was a water delivery, bringing not just H2O but also everything dissolved in it. We can test this idea chemically. Water molecules come in different isotopes, variations with extra neutrons. The ratio of regular hydrogen to deuterium, heavy hydrogen, works like a fingerprint. Measure it in Earth's oceans and compare it to measurements from comets. If the ratios match, you've found your source. The results are messy. Some comets match Earth's ratio almost perfectly. Others are way off. What this tells us is that Earth's water probably came from multiple sources. Some comets, yes, but also asteroids, and possibly some water that was trapped in the rocks that originally formed our planet. It's a mixture, which actually makes sense. 4 billion years of bombardment meant Earth was sampling everything the solar system had to offer. But we're getting ahead of ourselves. Delivering organic molecules is one thing. Getting them to organize into something alive is something else entirely. The molecules are here. They're scattered across the early Earth's surface, dissolved in the oceans, maybe concentrated in tidal pools or around hydrothermal vents. But molecules don't spontaneously decide to become alive. They need to do something first. They need to replicate. This is the central mystery. Life, at its core, is information that copies itself. DNA holds instructions. Those instructions get read, executed, and then copied to make more DNA. But DNA can't copy itself alone. It needs proteins. Enzymes that unzip the double helix, read the code, assemble new strands. Proteins are molecular machines, and they're incredibly good at their jobs. Except proteins can't make themselves either. They need DNA to encode their blueprints. You see the problem. DNA needs proteins. Proteins need DNA. It's a chicken and egg paradox, except both the chicken and the egg are microscopically small and made of carbon chains. For decades, this looked unsolvable. Then, in the 1980s, scientists discovered something that changed everything. RNA, ribonucleic acid, DNA's simpler cousin, and RNA could do something nobody expected. It could act as both information storage and enzyme. Some RNA molecules, called ribozymes, could catalyze chemical reactions, including, critically, making copies of other RNA molecules. Suddenly there's a way out of the paradox. Forget DNA and proteins for now. Start with RNA, one molecule playing both roles. An RNA world, where these versatile chains are doing all the heavy lifting. Storing information, copying themselves, maybe even catalyzing the reactions needed to build their own components. It's elegant. Almost too elegant. But does it actually work? Test it. Take RNA molecules and put them under conditions that might have existed on early Earth. See if they can evolve, adapt, replicate without any help from modern biology. Researchers have done exactly this. They've created RNA molecules that can copy other RNA strands with reasonable accuracy. They've shown that random RNA sequences, given the right environment, can develop catalytic activity through pure trial and error. The chemistry works. RNA can bootstrap itself. But there's still a massive gap between one self-replicating RNA molecule and anything we'd recognize as alive. That molecule needs protection. It needs to separate itself from the environment, create an inside and an outside. Otherwise, every molecule it makes just diffuses away into the ocean. No concentration, no organization, no evolution. This is where membranes come in. Lipids, fatty molecules with one end that loves water and another that hates it, can spontaneously form bubbles. Vesicles. Little spheres with a double-layered skin that keeps the inside separate from the outside. We see this in test tubes. Mix lipids and water and they self-assemble into something that looks startlingly like a cell membrane. No instructions needed. Just physics and chemistry doing their thing. Now imagine an RNA molecule that happens to be inside one of these lipid bubbles. It's replicating, making copies of itself. Those copies are trapped inside with it. The concentration builds. Maybe some of those RNA molecules catalyze reactions that help make more lipids, growing the membrane. The bubble gets bigger. Eventually it might split, dividing into two bubbles, each carrying RNA. You've just invented cellular division without involving a single protein or DNA molecule. This isn't life yet. Not quite, but it's something that can evolve. Bubbles with better RNA, RNA that replicates faster or makes useful products, will outcompete bubbles with worse RNA. Selection pressure exists even at this primitive level. And once you have selection, evolution is inevitable. The timeline here is staggering. We're talking about processes that might have taken tens of millions of years. Maybe 100 million. The early Earth had time. Lots of it. And it had variety. Thousands of different environments, each running its own chemical experiments. Shallow pools heated by the sun. Deep ocean vents with their chemical gradients. Underground water systems percolating through mineral-rich rock. Ice formations with liquid pockets. Every one of these is a potential laboratory. What's fascinating is that you don't need everything to happen in one place. Maybe RNA replication gets figured out in one environment, membrane formation in another. Then geological processes, volcanic eruptions, tidal movements, mix everything together. Combine the solutions. Evolution doesn't follow a neat, linear path. It's messy, parallel, full of dead ends and lucky accidents. But here's what really matters. Once you have something that can replicate and evolve, even if it's incredibly primitive, you've crossed a threshold. Because evolution is brutally good at solving problems. Give it enough time and enough variation, and it will find solutions to challenges that seem impossible. Like replacing fragile RNA with more stable DNA, or developing protein synthesis to build better enzymes than ribozymes could ever be. The transition from an RNA world to the DNA protein world we have now probably happened gradually. Maybe DNA started as just a more stable way to store backup copies of important RNA sequences. Then it got better at the job. Eventually it took over information storage completely, while proteins specialized in doing the actual work. RNA got relegated to the role it plays today, messenger, translator between DNA and proteins. We can see echoes of this ancient RNA world in modern cells. Ribosomes, the molecular machines that build proteins, are made mostly of RNA. The energy currency of the cell, ATP, is basically an RNA building block with some extra phosphate groups attached. Even DNA synthesis requires RNA primers to get started. These are fossils, chemical fossils, remnants of a time when RNA did everything. But proving this all happened is hard. RNA doesn't fossilize. It's too fragile. The oldest actual fossils we have are from about 3.5 billion years ago. Stromatolites, layered rock structures built by bacterial mats. By that point, life was already sophisticated. DNA, proteins, cell walls, photosynthesis. The really interesting stuff, the origin itself, happened earlier. Maybe 4 billion years ago, maybe even older, and it left almost no direct evidence. So we're forced to reconstruct it from clues, chemical signatures in ancient rocks, isotope ratios that suggest biological activity, computer simulations of prebiotic chemistry, lab experiments trying to recreate the conditions. Every piece of evidence is indirect, circumstantial. But they all point in the same direction. Life emerged from chemistry, not through some mysterious vital force, but through processes we can understand, replicate, and test. There's one more piece to this puzzle. One that makes the whole thing even stranger. The genetic code. The way DNA sequences get translated into amino acids, which then fold into proteins. This code is nearly universal. Bacteria use it. Plants use it. Animals use it. With tiny variations, every living thing on Earth reads DNA the same way. Which means the code was established early, probably before the last common ancestor of all life. And once it was set, it was locked in. Changing your genetic code would be like rewriting the operating system on a computer while it's running. Possible in theory, but catastrophically difficult in practice. Why this particular code? Is it optimal? Or just a frozen accident, the first solution that worked well enough? Some researchers argue it's actually pretty good at minimizing the damage from mutations. Similar codons often code for chemically similar amino acids. So if a mutation changes one letter in a codon, there's a decent chance the resulting protein still works. That's not random. That's error correction built into the system, but it's also consistent with evolution. An early, Slightly error-prone genetic code that worked well enough to get life started. Then, over time, selection pressure refined it. Lineages with codes that handled errors better survived. Those with worse codes died out. What we're left with is the optimized version. Not perfect, but good enough to support the incredible diversity of life we see today. Step back and look at the full picture. 4 billion years ago, maybe earlier, Earth was a planet covered in organic chemistry experiments. Molecules delivered by comets and asteroids, synthesized in the atmosphere, cooked up around volcanic vents. RNA figuring out how to replicate. Lipids forming membranes. Everything mixing, reacting, competing. And somewhere in that chaos, a combination of molecules found a way to persist, to improve, to evolve. That combination was the first life. Not a single moment of creation, but a gradual transition from complex chemistry to simple biology. The boundary between non-living and living wasn't a line. It was a gradient. And we're still not entirely sure where exactly to draw it. Once life existed, even in its most primitive form, the rules changed. Natural selection kicked in. Not as a guiding force, but as an automatic filter. Anything that replicated more efficiently than its competitors spread. Anything less efficient vanished. No intention required. Just math playing out over deep time. The first cells were probably nothing like modern bacteria. Simpler, messier. Their membranes leaked. Their metabolism was inefficient. But they worked well enough to persist. And that's all evolution needs. A starting point. Once you have replication, variation, and selection, improvement becomes inevitable. Not planned, just statistically certain. Early Earth was divided into two broad domains. Bacteria and archaea. They look superficially similar under a microscope. Single cells, no nucleus, circular DNA. But genetically, they're as different from each other as either is from us. Different membrane chemistry, different metabolic pathways, different cellular machinery. This split happened early, probably before 3.5 billion years ago. Why it happened is still debated. Maybe different environments selected for different solutions. Maybe it was just chance, two lineages drifting apart. Either way, both domains survived. Both thrived. Both are still here today. For the next 2 billion years, life stayed small. Microbial. Single cells doing their thing in the oceans, in sediments, around vents. It doesn't sound exciting, but this period was crucial. Because microbes invented almost everything. Photosynthesis, respiration, nitrogen fixation, fermentation. Every major metabolic pathway we see in complex life today was pioneered by bacteria or archaea. They figured out how to extract energy from sunlight, from minerals, from organic molecules. They built the biochemical toolkit that all later life would inherit. Then, around 2.5 billion years ago, something dramatic happened. Cyanobacteria, a group of photosynthetic bacteria, started producing oxygen as a waste product. Not a little oxygen, industrial quantities, enough to fundamentally alter the planet's chemistry. This wasn't planned. Oxygen was toxic to most organisms at the time. But cyanobacteria had evolved a way to deal with it, and they thrived. Everyone else had to adapt or die. The buildup was slow at first. Oxygen reacted with dissolved iron in the oceans, forming rust that settled to the seafloor. Those deposits, called banded iron formations, are some of the richest iron ore reserves we have today. For hundreds of millions of years, the oceans soaked up the oxygen. But eventually, the iron ran out. Oxygen started accumulating in the atmosphere. This is called the Great Oxidation Event. It fundamentally restructured the biosphere. Most anaerobic organisms retreated to oxygen-free environments. Deep sediments, guts of animals, anywhere they could avoid the toxic gas. But other lineages adapted. They evolved ways to use oxygen for respiration, extracting far more energy from the same nutrients. Aerobic respiration is about 15 times more efficient than anaerobic metabolism. That's a game changer. It opened the door to larger, more complex organisms. But complexity didn't arrive immediately. For another billion years, life stayed stubbornly simple. Bacteria and archaea dominated. No multicellular organisms. No complex cells. Just microbes. Why the delay? We're not entirely sure. Maybe oxygen levels weren't high enough yet. Maybe nutrients were limiting. Maybe it just took that long for the right innovations to evolve. Evolution doesn't optimize for speed. It optimizes for survival. And single-celled life was surviving just fine. Then, around 1.5 to 2 billion years ago, something unprecedented happened. A bacterial cell got engulfed by an archaeal cell. Normally, that's dinner. But this time, the bacterial cell survived inside. It kept its own genome, its own membrane, and it started providing a service. It processed oxygen, generating energy for the host. In return, it got protection and nutrients. This wasn't cooperation. Not at first. More like a hostage situation that gradually became mutually beneficial. Over time, the bacterial cell lost most of its independence. Its genome shrank. Many of its genes migrated to the host's nucleus. But it kept its essential function: energy production. Today, we call these structures mitochondria. Every complex cell on Earth, every plant, every animal, every fungus, has them. They're the descendants of that ancient symbiotic event. Without mitochondria, complex life as we know it wouldn't exist. This wasn't a one-time fluke. It happened again with photosynthesis. An archaeal cell engulfed a cyanobacterium. Same deal. The cyanobacterium survived inside, kept photosynthesizing, became a permanent resident. Today, we call these chloroplasts. Every plant and algae has them. Two separate endosymbiotic events. Two different bacterial lineages incorporated into archaeal hosts. Both absolutely critical for the evolution of complex life. These hybrid cells are called eukaryotes. They're fundamentally different from bacteria and archaea. They have a nucleus, complex internal structures, linear chromosomes, sexual reproduction, the ability to grow large and differentiate into specialized cell types. Every organism you can see without a microscope is a eukaryote. Every tree, every insect, every fish, every human. We're all descendants of those ancient mergers. But even with eukaryotic cells, life stayed mostly single-celled for a long time. Maybe another billion years. Single eukaryotes floating around, eating bacteria, photosynthesizing. Then, gradually, some lineages started sticking together. Colonies formed. Simple at first. Just clusters of identical cells. But over time, cells within colonies began specializing. Some handled reproduction. Others handled feeding. Others provided structure. This is the origin of multicellularity. Not a sudden leap, but a gradual transition from independent cells to cooperative groups. Multicellularity evolved multiple times independently. Plants did it. Animals did it. Fungi did it. Even some bacteria and algae pulled it off. Each time, the pattern was similar. Cells stuck together, started dividing labor, became interdependent. Why? Because in certain environments, being big has advantages. You're harder to eat. You can capture more resources. You can differentiate into specialized structures. Roots, leaves, muscles, nerves. Suddenly, evolution had a whole new playground. By about 600 million years ago, the first complex multicellular organisms appeared in the fossil record. Weird, soft-bodied creatures called the Ediacaran biota. Some looked like quilted fronds. Others like segmented discs. They don't resemble anything alive today. Most of them went extinct without leaving descendants. But they proved that large, complex life was possible. They set the stage for what came next. Then, around 540 million years ago, the Cambrian explosion happened. Not an explosion in the literal sense. More like a sudden diversification. Within about 20 million years, most major animal body plans appeared. Arthropods, mollusks, chordates, echinoderms. Animals with hard shells, jointed legs, segmented bodies, eyes. The fossil record goes from sparse and strange to abundant and recognizable. What triggered the Cambrian explosion? Probably multiple factors. Oxygen levels rising to a critical threshold. Predator-prey dynamics creating evolutionary arms races. The evolution of developmental genes that allowed for complex body plans. Ecological feedback loops where one innovation triggered others. It wasn't a single cause. It was a cascade. Once it started, it accelerated. One of the most important innovations was eyes. The ability to see opened up entirely new survival strategies. Predators could hunt more effectively. Prey could escape more efficiently. Vision created selection pressure for faster movement, better armor, more sophisticated nervous systems. Suddenly, being smart mattered. Brains got bigger. Behavior got more complex. Another key innovation was hard body parts. Shells, exoskeletons, bones. Before the Cambrian, almost everything was soft-bodied. Hard structures provided protection, but also structural support. They allowed animals to grow larger, move faster, dig deeper. And crucially, they fossilized. Which is why the Cambrian fossil record is so much richer than anything before it. Not necessarily because life suddenly became more diverse, but because it became more preservable. From the Cambrian onward, evolution proceeded in recognizable patterns. Animals colonized the oceans, then the land. Plants followed, turning barren continents into forests. Insects evolved, then amphibians, then reptiles, then mammals and birds. Each group building on the innovations of the ones before. Each adapting to new environments, filling new niches. But here's the thing. Every step in this story, from the first self-replicating molecules to the Cambrian explosion, was contingent. Not inevitable. If any number of things had gone differently, life might not exist. Or it might exist in forms completely unrecognizable. The fact that we're here, examining our own origins, is the result of billions of years of accidents, near misses, and unlikely events. Earth could have stayed frozen during snowball Earth periods. Life might never have survived. The Great Oxidation Event could have poisoned everything without any lineages adapting. Endosymbiosis might never have happened. Multicellularity might never have evolved. Any of these failures would have left Earth as a microbial planet indefinitely. Interesting, sure. But not capable of producing anything like us. Yet it didn't fail. Every bottleneck, every crisis, every random event lined up just right. Not because of destiny, just because of probability playing out over unimaginable timescales. Given enough planets, enough time, improbable things become statistically likely. We're the outcome of one very long, very unlikely chain of events. And that chain is still unfolding. The story of life on Earth isn't just about what survived. It's about what almost didn't. About 5 times in the past 540 million years, mass extinction events wiped out most species on the planet. Not small die-offs. Catastrophic collapses where 70 to 95% of all species disappeared. These weren't gradual declines. They were biological apocalypses that reset evolution and forced life to rebuild from whatever happened to make it through. The first major extinction happened at the end of the Ordovician period, about 445 million years ago. At the time, most life still lived in the oceans. Trilobites, brachiopods, burly fish. The continents were barren rock. Then the climate destabilized. A rapid ice age locked up vast amounts of water as glaciers. Sea levels dropped dramatically. Shallow marine habitats, where most life existed, simply disappeared. Organisms adapted to warm, stable conditions suddenly faced freezing temperatures and habitat loss. About 85% of marine species went extinct. But here's what's interesting. The extinction happened in two pulses. First, when the Ice Age began. Second, when it ended and oceans warmed rapidly again. Life couldn't adapt to the cold. Then it couldn't adapt when things warmed back up. Whichever way the climate swung, something died. The survivors were generalists. Species that could tolerate wider ranges of temperature, salinity, oxygen levels. Specialists, finely tuned to specific conditions, were wiped out. This pattern repeats in every mass extinction. Adaptability beats optimization when the environment becomes unpredictable. The second major extinction came at the end of the Devonian period, around 375 million years ago. This one unfolded over several million years. Not a single catastrophic event, but a prolonged crisis. The leading hypothesis involves ocean anoxia. Large areas of the ocean losing oxygen. Fish, invertebrates, coral reefs, all suffocating. What caused the anoxia? Possibly massive algae blooms triggered by nutrient runoff from the newly forested continents. Plants had just colonized land. Their roots broke down rock, releasing nutrients into rivers that flowed into the ocean. Too many nutrients caused explosive algae growth. When the algae died and decomposed, they consumed oxygen. The oceans became dead zones. About 75% of species disappeared. Reef ecosystems collapsed. Armored fish, which had dominated for millions of years, were devastated. Sharks, more adaptable, survived. This extinction reshaped marine life. It cleared space for new groups to evolve. But it took millions of years for biodiversity to recover. The third extinction is the big one. The Permian-Triassic event, 252 million years ago. The worst mass extinction in Earth's history. About 96% of marine species and 70% of terrestrial vertebrate species went extinct. Life came closer to complete annihilation than at any other time. The cause? Massive volcanic eruptions in what's now Siberia. Not a single volcano. An entire region erupting for hundreds of thousands of years. Lava flows covering an area larger than Europe. The eruptions released enormous amounts of carbon dioxide, sulfur dioxide, and other gases. Global temperatures spiked. Oceans acidified. Oxygen levels plummeted. On land, acid rain and greenhouse heating devastated ecosystems. In the oceans, warming and acidification killed off calcifying organisms. Coral reefs vanished. Food chains collapsed from the bottom up. Some researchers think the warming triggered the release of methane from ocean floor deposits. Methane is a far more potent greenhouse gas than CO2. If enough was released, it would have created a runaway warming effect. Temperatures potentially rose 10 degrees Celsius or more. The planet became a hothouse. Only the most resilient organisms survived. Small body size helped. Lower metabolic demands. Ability to hide underground or underwater. Generalist diets. Life that could eat almost anything had an advantage over specialists. The recovery took 10 million years. Longer than any other extinction. For millions of years after the Permian extinction, ecosystems remained impoverished. Low diversity. Simplified food webs. But eventually, life rebounded. And the groups that survived went on to dominate the Mesozoic. Including the Archosaurs, the lineage that would produce dinosaurs. The fourth major extinction happened at the end of the Triassic period, about 201 million years ago. Another round of massive volcanism. This time in the central Atlantic, as the supercontinent Pangaea began to break apart. Rifting continents triggered volcanic eruptions that lasted for hundreds of thousands of years. Again, CO2 levels spiked. Oceans acidified. Temperatures soared. About 80% of species went extinct. But this extinction had an unusual outcome. It cleared the way for dinosaurs. Before the Triassic extinction, dinosaurs were relatively minor players. They existed, but so did many other reptile groups. Crocodile relatives, large amphibians, burly mammal ancestors. All competing for the same resources. The extinction removed most of those competitors. Dinosaurs, for whatever reason, were better at surviving the crisis. Maybe their upright stance. Maybe their respiratory systems. Maybe just luck. But in the aftermath, they diversified rapidly and became the dominant land animals for the next 135 million years. Which brings us to the fifth extinction. The one everyone knows. The End Cretaceous event, 66 million years ago. The asteroid impact that killed the dinosaurs. This one was different. Not a slow burn like the others. Not volcanism or climate shifts playing out over millennia. This was sudden. Catastrophic. A 10-kilometer wide asteroid slammed into what's now the Yucatan Peninsula at 20 kilometers per second. The impact released energy equivalent to billions of nuclear bombs. It vaporized rock. Triggered earthquakes. Generated tsunamis. Ignited global wildfires. But the real killer was the aftermath. The impact threw trillions of tons of dust and aerosols into the atmosphere. Sunlight was blocked. Photosynthesis stopped. Temperatures plummeted. Plants died. Herbivores starved. Carnivores followed. Within months, ecosystems collapsed. About 75% of all species went extinct, including all non-avian dinosaurs. Not because they were weak. Not because they were poorly adapted. But because the rules changed instantly and completely. No amount of evolutionary success mattered when the sun disappeared. The survivors were small, burrowing animals, scavengers, anything that could hide underground or underwater, anything with low energy requirements. Birds made it through, though most species didn't. Mammals survived, but only the small ones. Crocodiles and turtles, with slow metabolisms, endured. In the aftermath, the planet was dark, cold, and nearly lifeless for years. Then, slowly, life returned. Plants regrow from seeds and roots. Survivors emerged and began to spread. Ecological niches, empty for the first time in millions of years, were filled by whatever happened to be around. Mammals, previously limited to small nocturnal roles, suddenly had opportunities. No more dinosaurs to compete with. No more giant predators. Within 10 million years, mammals had diversified into dozens of new forms. Browsers, grazers, predators, climbers, swimmers. The age of mammals had begun. Not because mammals were superior, but because dinosaurs were gone. Each of these 5 mass extinctions reset the clock. They didn't erase life, but they reorganized it. Groups that had dominated for millions of years vanished. New groups, previously marginal, took over. Evolution doesn't have a direction. It doesn't move toward complexity or intelligence. It just responds to whatever pressures exist at the time. And when those pressures are catastrophic, the response is equally extreme. Survival in a mass extinction isn't about being the best. It's about being lucky enough to have the right traits at the right moment. Small size when food is scarce. Generalist diet when ecosystems collapse. Burrowing behavior when the surface becomes uninhabitable. These aren't strengths in normal times. They're insurance policies for disasters. And here's the uncomfortable part. We're living in the 6th mass extinction right now. Species are disappearing at rates comparable to the Big Five. Not from asteroid impacts or volcanic eruptions. From us. Habitat destruction. Climate change. Overhunting. Pollution. We're not just witnesses to extinction. We're the cause. And unlike previous extinctions, this one is happening in real time. Fast enough to observe. Fast enough to measure. But possibly too fast to stop. The difference is, we know it's happening. We can see the patterns. We understand the mechanisms. Previous mass extinctions were blind cosmic accidents. This one is optional. Which makes it either more tragic or more hopeful, depending on what we do next. The question isn't whether Earth will survive. It will. Life has endured worse. The question is what form that life will take. Weather will be part of it. and what we're willing to do to change the trajectory. Earth's history isn't just a record of extinctions. It's a record of recoveries. And those recoveries follow patterns. Predictable, repeatable patterns that play out over millions of years. Understanding them reveals something crucial about how life actually works when everything falls apart. After each mass extinction, the planet enters what scientists call a dead zone. Not literally dead, but functionally empty. Food webs are shattered. Ecosystems lack structure. Energy flows are disrupted. The survivors exist, but they're not thriving. They're just hanging on in a world that doesn't work properly yet. This phase lasts anywhere from hundreds of thousands to millions of years. During this time, diversity remains low. A few generalist species spread widely, filling multiple roles because specialists haven't evolved yet. Think of it as ecological simplicity. Not because life can't be complex, but because complexity requires time to build. Then something shifts. Resources accumulate. Populations grow. Competition increases. And suddenly, evolution accelerates. New species branch off. Specialists emerge. Food webs gain layers. This is the recovery phase, where diversity explodes and ecosystems regain their structure. But here's what matters. The new ecosystems don't look like the old ones. They're built from different parts, organized around different principles, dominated by different groups. Recovery doesn't mean restoration. It means reinvention. After the end Permian extinction, the worst in Earth's history, recovery took roughly 10 million years. Longer than any other mass extinction. Why? Because the damage was deeper. Ocean chemistry was disrupted. Carbon cycles were broken. Climate remained unstable for millions of years. Life had to wait for the planet itself to stabilize before it could rebuild. The Triassic period that followed looked nothing like the Permian. Synapsids, which had dominated before, were reduced to minor roles. Reptiles, particularly archosaurs, took over. These were the ancestors of dinosaurs and crocodiles. They succeeded not because they were superior, but because they happened to have traits that worked in new conditions. After the end Cretaceous extinction that killed the dinosaurs, recovery was faster. About 2 to 3 million years before ecosystems regained complexity. Why quicker this time? The planet wasn't as severely damaged. Ocean chemistry recovered faster. Climate stabilized sooner. And crucially, more lineages survived, providing more raw material for evolution to work with. Mammals filled the empty niches left by dinosaurs. But they didn't just become small versions of what came before. They evolved entirely new body plans. New feeding strategies. New ways of moving and reproducing and interacting. Within 10 million years, mammals had diversified into forms ranging from tiny shrews to early whales. This reveals a fundamental truth about evolution. It's not progressive. It doesn't aim toward improvement. It's opportunistic. Whatever works in the current environment spreads. Whatever doesn't, disappears. The best organism is simply the one that survives long enough to reproduce. And survival depends heavily on luck. Being in the right place when disaster strikes. Having the right traits when conditions change. Being part of a lineage that happens to persist. Intelligence doesn't guarantee survival. Size doesn't. Strength doesn't. Adaptation to current conditions definitely doesn't, because those conditions can change overnight. This is why predicting recovery is so difficult. We can identify general patterns, but the specifics depend on which groups survive and what opportunities they find. After the dinosaurs, it could have been something other than mammals. If a few key lineages had gone extinct, Earth's history would look completely different. Now consider our current situation. We're in the early stages of a mass extinction. Species are vanishing rapidly. Ecosystems are degrading. But we're not yet in the dead zone. That comes later, if current trends continue. Which means we're at a decision point. We can still influence the outcome. What would recovery look like after a human-caused mass extinction? Hard to say. It depends on what survives. If large mammals disappear, something else will eventually fill those roles. Maybe birds. Maybe reptiles. Maybe something unexpected. Evolution doesn't care about our preferences. If humans disappeared tomorrow, Earth would recover. It might take millions of years, but diversity would return. New species would evolve. Ecosystems would rebuild. The planet has done this before, multiple times. It's resilient in ways that individual species aren't. But that's not a comforting thought. Because from our perspective, recovery after our extinction wouldn't include us. We'd be a thin layer in the fossil record. Evidence of a species that emerged, dominated briefly, then vanished. Just like the dinosaurs. Just like the trilobites. Just like thousands of other lineages that once seemed permanent. The real question isn't whether Earth will recover. It's whether we want to be part of that recovery. Whether we're willing to change our behavior to remain part of the story. Because unlike previous mass extinctions, this one comes with awareness. We understand what's happening. We can measure it. We can model future scenarios. We have knowledge that no species has ever possessed before. That knowledge creates responsibility. Not moral responsibility in some abstract sense, but practical responsibility. We're causing changes that will determine which species persist and which don't. Including possibly our own. And unlike an asteroid impact, these changes are gradual enough that we can respond. If we choose to. But here's the hard part. Responding effectively requires acting against immediate self-interest. Preserving habitat means not developing land. Reducing emissions means changing energy systems. Limiting consumption means accepting less material wealth. These aren't easy choices. They're not even obviously rational from an individual perspective. Yet they're necessary from a species perspective. From an ecosystem perspective. From a long-term survival perspective. The same perspective that matters when you're looking at geological timescales and extinction patterns. Because on those timescales, short-term gains vanish. Only persistence matters. Only what survives long enough to leave descendants. This is where human intelligence becomes either our greatest asset or our fatal flaw. We can understand long-term consequences in ways other species can't. We can plan beyond our own lifetimes. We can coordinate globally. But we can also rationalize inaction. Prioritize immediate comfort. Assume someone else will solve the problem. Other species don't face this dilemma. They can't choose to prevent extinction. They simply respond to immediate pressures, and either their traits work or they don't. Humans are the first species capable of consciously deciding whether to alter our trajectory, whether to use our intelligence to ensure our persistence. The fossil record shows that dominance is temporary. Every group that once ruled eventually declined. Trilobites dominated for 270 million years, then vanished. Dinosaurs lasted 165 million years, then disappeared. Humans have existed for maybe 300,000 years. We've been technologically advanced for less than 10,000. We're newcomers. And newcomers don't have track records of stability. What we do have is unprecedented power. Power to reshape ecosystems. Power to drive climate change. Power to cause extinctions at rates comparable to asteroid impacts. That power doesn't make us immune to extinction. It makes us capable of causing our own. The patterns from previous mass extinctions suggest what might happen next. If we continue current trends, diversity will decline. Ecosystems will simplify. Specialist species will disappear first. Then larger species. Then anything requiring stable conditions. Eventually, we reach a threshold where ecosystems can't provide the services we depend on. Clean water. Stable climate. Pollination. Soil formation. Food production. At that point, human civilization becomes unsustainable. Not because we lack technology, but because the biological foundation collapses. We can't engineer our way out of ecosystem failure. We depend on functional ecosystems the same way every other species does. Remove enough pieces, and the whole structure falls apart. This isn't speculation. It's pattern recognition. Every mass extinction followed similar trajectories. Stress accumulates. Systems become fragile. A final trigger causes collapse. The only difference now is we can see it coming. We have data, models, projections, We know which actions accelerate the problem and which might slow it. Whether we act on that knowledge determines what the next few million years look like. Whether the Anthropocene becomes a brief anomaly or a major extinction event. Whether humans persist or become another fossil layer. Whether intelligence, our defining trait, proves adaptive or maladaptive on evolutionary timescales. The answer isn't predetermined. Evolution doesn't script outcomes. It responds to conditions. And conditions, for the first time in Earth's history, are partially under the control of one species. That's never happened before. We don't have precedent for a species consciously shaping its own evolutionary future. Which makes this moment unique. Not just in human history, but in planetary history. We're the first species capable of understanding mass extinctions while potentially causing one. The first that can choose whether to continue down that path. The first with enough knowledge to know better and enough power to do something about it. What we do next matters. Not because the universe cares. Not because Earth cares. But because we care. Because we're capable of caring about things beyond our immediate survival. About other species. About future generations. About whether the story continues or ends with us. That capacity for long-term thinking is either our salvation or our epitaph. And we're in the process of finding out which. Looking back at the fossil record reveals something unsettling. Intelligence rarely appears as a survival trait. Most successful lineages, the ones lasting tens or hundreds of millions of years, rely on simplicity. Bacteria, jellyfish, crocodiles. They don't solve problems. They persist through durability. Intelligence is expensive. It requires large brains, extended development periods, high energy intake. For most of Earth's history, those costs outweighed the benefits. Only in specific circumstances, environments demanding flexibility and learning, did intelligence become advantageous. And even then, it remained rare. Out of billions of species across 4 billion years, only one developed technology. That's not a sign of inevitability. It's statistical noise. Which raises a question. If intelligence is so rare and so costly, what happens when it creates problems faster than it solves them? When the very trait that enabled survival becomes the mechanism of decline? We're testing that now. Human intelligence produced agriculture, medicine, technology. It extended lifespans, reduced infant mortality, enabled population growth beyond any precedent. But it also produced weapons capable of ending civilization in hours. Pollution that persists for millennia. Climate disruption that compounds across decades. We're intelligent enough to create these problems. Whether we're intelligent enough to solve them remains unproven. And the clock is running. Not in human time, where decades feel long. In geological time, where our entire civilization is a blink. If we disappeared tomorrow, future geologists would find a thin layer marking our existence. Plastics. concrete. Radioisotopes. A brief spike in carbon isotopes. Then silence. The planet would continue. Life would recover. It always does. Not the same life, not the same ecosystems, but something. Earth doesn't need humans. We need Earth. That asymmetry matters. We talk about saving the planet, but that's backwards. The planet will be fine. It survived 5 mass extinctions, supervolcano eruptions, asteroid impacts, ice ages, hothouse climates. It'll survive us. What we're actually trying to save is ourselves. Our way of life. The stable conditions we evolved to exploit. Those conditions aren't guaranteed. They're contingent on systems we're actively destabilizing. And once those systems cross certain thresholds, they don't snap back. They reorganize around new equilibria. Equilibria that might not include industrial civilization or large human populations or humans at all. That possibility should focus attention. Because unlike previous species facing extinction, we can see it coming. We have data showing ocean acidification rates, temperature projections, biodiversity decline curves, ecosystem collapse timelines. We know where current trajectories lead. And yet, knowing doesn't guarantee action. Information alone never changes behavior. If it did, everyone would exercise, save money, avoid processed food. But knowing what's good for us and doing it are different things. The gap between knowledge and action defines the human condition. And right now, that gap is widening. We know fossil fuels drive climate change. We keep burning them. We know industrial agriculture depletes soil. We keep expanding it. We know overfishing collapses stocks. We keep fishing. Not because we're stupid. Because short-term incentives override long-term consequences. Because individual rationality produces collective irrationality. Because the benefits of harmful actions accrue to individuals while the costs distribute across everyone. That's not a moral failing. It's a structural problem. And structural problems require structural solutions. Individual action matters, but it's insufficient. Recycling, reducing consumption, changing diet, all positive steps. But they don't address the underlying systems driving ecosystem collapse. Those systems, energy infrastructure, agricultural practices, economic incentives, require coordinated policy changes. Which requires political will. Which requires public pressure. Which requires enough people caring enough to demand change. And that's where we are. In a narrow window where the trajectory is set but not locked. Where the momentum is strong but not irreversible. Where outcomes remain uncertain because they depend on choices not yet made. This moment won't last. Windows close. Systems reach tipping points. momentum becomes irreversible. The question is whether we recognize the moment while we're in it. Whether we understand that what feels like normal is actually unprecedented. That the stability we take for granted is historically anomalous. That the future isn't guaranteed to resemble the past. Because it won't. The planet we're creating will be fundamentally different from the one we inherited. Hotter. Less biodiverse. Less stable. Whether it remains habitable for billions of humans depends entirely on how much hotter, how much less diverse, how much less stable. Those aren't abstract variables. They're outcomes of specific decisions. Energy policy. Land use. Consumption patterns. Trade agreements. Infrastructure investments. Decisions being made now, today, by governments, corporations, individuals. Each decision moves the needle. Slightly. Incrementally. But cumulatively, they determine trajectory. And trajectory determines destination. We like to think we're separate from nature. That technology insulates us from ecological limits. That intelligence exempts us from evolutionary pressures. But we're not separate. We're embedded. We breathe the same air. Drink the same water. Depend on the same ecosystem services as every other organism. Our cities, our technology, our entire civilization rests on a foundation of functional ecosystems. Remove that foundation and everything collapses. Not might collapse. Will collapse. It's physics. You can't support a structure after removing its base. And we're systematically removing the base. Deforestation. Ocean acidification. Soil depletion. Aquifer exhaustion. Pollinator decline. Each one weakens the foundation. Each one moves us closer to structural failure. We're not facing one problem. We're facing interconnected system failures happening simultaneously. Climate change amplifies species extinction. Species extinction reduces ecosystem resilience. Reduced resilience accelerates climate impacts. Feedback loops compound. Tipping points cascade. And suddenly, gradual change becomes rapid collapse. That's how complex systems fail. Slowly, then all at once. The challenge is acting during the slow phase. When problems seem manageable. When denial remains plausible. When short-term costs feel more real than long-term consequences. Acting requires overriding our evolutionary programming. We evolved for immediate threats. Predators. Starvation. Injury. Our brains are wired for rapid response to visible danger. But climate change isn't a predator. It's a statistical shift. A gradual accumulation. A probability distribution changing shape. Our brains aren't built to process that. We don't feel threatened by parts per million, by decimal point temperature increases, by percentage changes in biodiversity. We feel threatened by things with teeth, by things that can hurt us now. Which is why this is hard. Why knowing isn't enough. Why information doesn't automatically translate to action. We're asking people to respond emotionally to spreadsheets, to feel urgency about graphs, to sacrifice immediate comfort for abstract future benefits. That's not how humans work. But it's what the situation requires. Which means we need to change how we work. Not our biology, that's too slow. But our systems, our institutions, our decision-making frameworks. We need structures that account for long-term consequences, that price in externalities, that prioritize sustainability over quarterly profits, that value ecosystem health over GDP growth. Those structures don't exist by default. They require intentional design, political will, social pressure, cultural shifts. They require enough people demanding something different. Enough people recognizing that current systems are driving us toward collapse. Enough people willing to support changes that might be personally inconvenient but collectively necessary. And that's the real test. Not whether we can develop solutions. We have solutions. Renewable energy, regenerative agriculture, circular economies, ecosystem restoration. The technology exists. The knowledge exists. What's missing is implementation at scale. What's missing is political and economic systems that prioritize long-term survival over short-term extraction. What's missing is collective willingness to accept that infinite growth on a finite planet is mathematically impossible. That's the hard part. Not the science. Not the engineering. The acceptance that our current trajectory is unsustainable. That something has to change. That we can't keep doing what we're doing and expect different results. And we're running out of time to figure this out. Not in a dramatic, countdown clock way, but in the sense that every year of delay makes the problem harder. Every ton of carbon emitted stays in the atmosphere for decades. Every species lost is gone permanently. Every ecosystem threshold crossed is effectively irreversible on human timescales. We're making decisions now that will echo for thousands of years. Decisions about what kind of planet we leave behind, what kind of future we're creating. Whether intelligence, our defining characteristic, proves adaptive or catastrophic. The answer isn't written yet. We're writing it. Right now. Through choices large and small. Through policies and purchases. Through what we demand and what we accept. Through whether we treat this as an emergency or a distant concern. Evolution doesn't care which we choose. It'll respond to whatever conditions we create. It'll favor whatever traits prove adaptive in the world we're building. Maybe that world includes humans. Maybe it doesn't. Maybe intelligence remains advantageous. Maybe it becomes a liability. Maybe we're the ancestors of something extraordinary. Maybe we're just another failed experiment. Another branch that couldn't adapt fast enough. Another fossil layer marking a brief moment when one species thought it could outsmart 4 billion years of planetary processes. We won't know the answer for millions of years. But we're determining it now. Part 6 of 6. The story we've been told about comets, the one where they're just icy debris wandering through space, needs updating. Because the data keeps pointing in one direction. These objects aren't random. They're delivery systems. Packages sent from the outer solar system carrying exactly what early Earth needed but couldn't make efficiently on its own. Think about the timing. Earth forms hot. Too hot for organic chemistry. It needs to cool, needs water, needs the building blocks for biochemistry. And right on schedule, here come the comets. Billions of them during the late heavy bombardment. Each one carrying ice, organics, amino acids, phosphorus. Each impact a delivery. Not violent destruction, but violent creation. We've spent decades assuming life started here through local chemistry. Lightning strikes. Volcanic vents. Tidal pools. And maybe some of it did. But the numbers don't work. Early Earth's atmosphere wasn't right for making complex organics in quantity. The Miller-Urey experiment, elegant as it was, used the wrong gases. When you correct for that, the yield drops dramatically. Local production wasn't enough. But comets? They're making organics constantly. In the cold dark between stars. No atmosphere to worry about. No oxygen to interfere. Just carbon, hydrogen, nitrogen, oxygen, and time. Lots of time. These molecules form, accumulate, get locked into ice matrices that protect them. Then they wait. Sometimes for billions of years. Until gravity pulls them inward. Until they slam into young planets. Until they deliver their cargo. What we found on Wild 2 and 67P isn't an accident. It's a pattern. Comets everywhere are doing this. Making the same molecules. Carrying the same building blocks. It's chemistry operating at solar system scale. And Earth was in the path of that delivery route for hundreds of millions of years. The ice itself mattered just as much as what was in it. Early Earth needed water. Vast amounts. Our oceans didn't condense from the primordial atmosphere. They came from outside. From objects that formed in colder regions and then migrated inward. Some from asteroids, yes. But comets contributed. Isotope ratios prove it. Not all our water is cometary, but some is. Enough to matter. So now picture the actual scenario. 4 billion years ago. Earth with thin oceans, no continents yet, active volcanism everywhere. And it's being bombarded constantly. Not planet-killing impacts, but steady, relentless delivery. Each comet brings water, organics, minerals. The ice cushions the impact, protects the cargo. The organics survive, dissolve into the ocean, accumulate. The minerals settle. The carbon compounds concentrate in tidal zones, around vents, in shallow pools. You're not starting with nothing. You're starting with a planet being continuously restocked with prebiotic chemistry, with molecules that already have some complexity, with building blocks ready to assemble into something more sophisticated. The local chemistry, the lightning and vents and UV radiation, they're still happening. But now they're working with better raw materials. They're not creating from scratch. They're refining what's already there. And here's what makes this profound. It means life's origin isn't purely local. It's not Earth solving the problem alone. It's Earth benefiting from processes that happened across the entire solar system. From chemistry in molecular clouds, from reactions in the outer solar system, from delivery mechanisms that operated for hundreds of millions of years. Life's origin is a collaboration between a planet and its cosmic environment. Which raises an obvious question. If this happened here, did it happen elsewhere? Are there other planets, right now, being seeded by comets? Other oceans accumulating organic molecules? Other worlds where chemistry is transitioning toward biology? We don't know. But the statistics suggest yes. Our solar system isn't unique. Comets form around other stars. Planets get bombarded everywhere. The same physical processes, the same chemistry, the same delivery mechanisms. If it worked once, it can work again. Maybe it's working right now on planets we haven't discovered yet. Maybe it's worked countless times on worlds that existed billions of years ago. Maybe we're not the first. Maybe we won't be the last. That doesn't make life inevitable. Chemistry alone doesn't guarantee biology. You need the right conditions, the right timing, the right sequence of events. But it makes life less miraculous, less impossibly unlikely. It shifts the question from, how did life beat astronomical odds? To, given favorable conditions and enough time, how often does chemistry become biology? And that's a different question. One with potentially different answers. Because chemistry is patient. It doesn't care about timescales. It just keeps trying combinations. Keep mixing molecules for 1 billion years and eventually something interesting happens. Not guaranteed, but probable. And probability, given enough opportunities, approaches certainty. We're still missing pieces. We don't know exactly how RNA formed, how membranes and replication combined, how the genetic code got established. Those are hard problems. but they're becoming tractable. Every year, lab experiments get closer to recreating conditions that produce self-replicating systems. Every year, we understand more about what early Earth was actually like. Every year, the gap between non-life and life gets smaller. Comets didn't solve the origin of life. They solved the supply problem. They provided raw materials that early Earth couldn't efficiently produce. They turned an improbable event into something merely unlikely. And on planetary timescales, unlikely events happen constantly. You just need to wait. The evidence keeps accumulating. Not just from comets we've visited, but from meteorites, from interstellar chemistry, from laboratory experiments. All of it pointing toward the same conclusion. The building blocks of life aren't rare. They're common. They form naturally in cold environments. They survive delivery to planetary surfaces. They accumulate. They react. They experiment. What's rare isn't the chemistry. It's the conditions that let chemistry become biology. Stable liquid water. Energy sources. Mineral surfaces for catalysis. Protection from radiation. Enough time without catastrophic disruption. Those conditions are specific. Not impossible, but requiring a particular combination of planetary characteristics. Earth had those characteristics. Maybe other planets do too. Maybe they're common. Maybe they're rare. We're only beginning to survey the possibilities. Only beginning to understand how many Earth-like worlds exist. Only beginning to look for biosignatures, chemical signs that biology is happening somewhere else. The search is underway. Telescopes scanning exoplanet atmospheres for oxygen, methane, combinations that suggest life. Probes examining Europa and Enceladus, moons with subsurface oceans that might harbor biology. Future missions to Venus, Mars, Titan, looking for current life or fossil evidence of past life. Each mission refines our understanding. Each discovery adjusts the probabilities. And those probabilities matter. Because they determine whether we're alone or part of something larger. Whether life's origin was a singular miracle or a common occurrence. Whether intelligence is unique to Earth or inevitable given enough time. Whether we're the only species capable of asking these questions or one of many scattered across the galaxy. We don't have those answers yet. But we're closer than we've ever been. Closer to understanding our origins. Closer to knowing whether life elsewhere exists. Closer to determining our place in the universe. Not through philosophy or speculation, but through data. Through chemistry. Through missions that touch these ancient objects and read their composition. Comets are messengers. Not from gods or fate, but from the early solar system. They carry information about conditions 4.5 billion years ago. About chemistry in the outer regions. About what was available when Earth formed. That information is still readable, still preserved in ice that hasn't melted since the solar system's beginning. Every comet we study refines the picture. Every measurement adds detail. Every discovery adjusts our understanding. We're not guessing anymore about what these objects contain. We're measuring it directly. And what we're measuring consistently shows organic complexity. Amino acids, nucleobases, phosphorus, water, everything life needs. That doesn't prove comets created life. Proof would require showing the mechanism, demonstrating that delivered organics actually assembled into something living. We can't do that. We weren't there. We don't have recordings. We have only evidence, circumstantial but compelling, pointing toward cometary delivery as a crucial part of life's origin. The alternative is that all of this is coincidence. That comets happen to carry exactly the molecules life uses, but contributed nothing. That early Earth independently synthesized everything despite having the wrong atmospheric chemistry. That the timing of heavy bombardment and life's appearance is unrelated. Possible, but increasingly implausible. Science works by eliminating alternatives until only one explanation fits the data. We're not there yet. But we're moving in that direction. Each study, each mission, each experiment narrows the possibilities. And what's emerging is a story where life's origin wasn't purely terrestrial. Where Earth's chemistry was supplemented by cosmic delivery. Where our existence depended on objects formed in a cold dark carrying cargo across billions of kilometers. It's a strange story. Not the one we expected. But data doesn't care about expectations. It cares about what actually happened. And what appears to have happened is that life's ingredients came from space. Not all of them, but enough to matter. Enough to tip the balance from impossible to merely improbable. Enough to give chemistry the raw materials it needed to begin experimenting with biology. We're the result of that experiment. Not the only possible result, but one that worked. One that survived. One that eventually became capable of looking back and asking where it came from. And now we have an answer, partial but growing more complete. We came from Earth, yes. But Earth came from the solar system. And the solar system provided, through comets, the chemical foundation that made us possible. That foundation is still out there. Still orbiting. Still carrying the same molecules. Still waiting to be studied. Each comet is a time capsule from the solar system's formation. Each one holds clues about conditions back then. About chemistry. About the processes that led to us. We've only examined a handful. Thousands more are accessible. Each one potentially holding new information, new insights, new pieces of the puzzle. The work continues. Missions are being planned to return samples from comets. To land on their surfaces. To drill into their cores and retrieve pristine material that's been frozen since the beginning. Each sample will be analyzed in laboratories with instruments far more sensitive than what existed even a decade ago. Each analysis will reveal more about what comets contain and how those contents relate to biology. We're at the beginning of understanding this connection, not the end. The evidence so far is suggestive, compelling, but incomplete. We need more data, more samples, more experiments, more missions. The story of how comets contributed to life's origin is still being written. But the outline is visible, the general shape is clear. And it's changing how we think about our place in the universe. Because if comets seeded Earth, they're seeding other planets too. If organic delivery is common, then the building blocks of life are widespread. If chemistry can transition to biology given the right conditions, then those conditions might exist elsewhere. The universe might be full of experiments similar to the one that produced us. Some failing, some succeeding, some just beginning, some already billions of years old. We don't know yet, but we're looking. And every year, our tools get better. Our understanding deepens. Our search expands. The question of whether we're alone is becoming answerable. Not through speculation, but through observation. Through detecting biosignatures on distant worlds. Through finding life in our own solar system beyond Earth. Through understanding how common the processes that created us actually are. That understanding starts with comets. With these frozen archives carrying evidence from our beginning. With missions that brave enough to catch up to them, touch them, taste their chemistry. With scientists patient enough to analyze the data, piece together the story, follow wherever the evidence leads. And where it's leading is toward a cosmos more interconnected than we imagined. Where life's origin isn't isolated to individual planets, but involves solar system-wide processes. Where chemistry in one region affects biology in another. Where what happens in the cold outer darkness eventually influences what emerges in the warm inner light. We're part of that story. Products of processes that began before Earth existed. Beneficiaries of delivery systems that operated for hundreds of millions of years. Descendants of chemistry that started in molecular clouds and ended in living cells. The path from there to here was long, improbable, contingent on countless specific events. But it happened. And understanding how it happened changes everything about how we see ourselves and our origins.
Right now, somewhere in the constellation Orion, a star 16 times more massive than our Sun is burning through the final chapters of its life. It could explode tomorrow. It could explode in 1,000 years. Or it might have already exploded, and the light from that catastrophic event is racing toward Earth at 186,000 miles per second, closing the distance between destruction and discovery. Betelgeuse isn't just dying. It's preparing for one of the most spectacular shows the universe can produce, and when it happens, you'll be able to see it in broad daylight. 4 months. This is the story of a star on borrowed time and what happens when something that massive runs out of fuel. Every clear winter night, Betelgeuse marks the shoulder of Orion the Hunter, glowing with that distinctive red-orange color that sets it apart from nearly every other point of light in the sky. You've probably looked at it 100 times without knowing what you were seeing. A star so enormous that if you replaced our Sun with it, its surface would extend past Jupiter's orbit. Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter itself, all vaporized inside a single stellar atmosphere. The numbers barely make sense. More than 400 million suns could fit inside Betelgeuse's volume. Its radius stretches somewhere between 640 and 764 times larger than our Sun, though pinning down exact measurements proves frustratingly difficult for reasons we'll get into. The star sits roughly 650 light-years from Earth, which means the light hitting your eyes tonight left Betelgeuse around the year 1374. The Black Death was ravaging Europe. The Ming Dynasty was just beginning in China. And Betelgeuse was already ancient. But here's what makes this star genuinely unsettling. That light we're seeing, those photons that traveled for 6.5 centuries to reach us, they're showing us a star that might not exist anymore. Betelgeuse could have exploded last Tuesday, and we wouldn't know until the year 2674. The star could have detonated during the Renaissance, and the light from that explosion is still crossing the void between us, carrying news of a death that happened before anyone alive today was born. Scientists estimate Betelgeuse is less than 10 million years old. That sounds old until you remember our Sun is 4.6 billion years old and has another 5 billion years left. Massive stars burn fast and die young. They consume their nuclear fuel at rates that smaller stars can't match, racing through evolutionary stages that take ordinary stars billions of years to complete. Betelgeuse has already burned through its hydrogen, its helium, and is now working through increasingly heavy elements in its core. Carbon, neon, oxygen, silicon. Each fusion stage happens faster than the last. The star varies in brightness constantly, pulsing and dimming according to multiple overlapping cycles. A major cycle every 420 days. Others at 185 days, 230 days, even 2,200 days. Then sudden changes that break the pattern entirely. Astronomers have tracked these fluctuations since 1836, when Sir John Herschel first noticed them. For nearly 2 centuries, Betelgeuse has been getting brighter and dimmer like a cosmic heartbeat, each pulse a reminder of the chaos happening beneath that vast photosphere. Then came late 2019, and something unprecedented happened. Betelgeuse started dimming. Not the usual variation, but a dramatic, sustained drop in brightness that caught everyone off guard. By February 2020, the star had faded by a factor of 3, dropping from magnitude 0.5 to 1.7. The dimmest anyone had ever recorded it. Social media exploded with speculation. Was this it? Was Betelgeuse about to go supernova? Astronomers around the world redirected their instruments, watching, measuring, waiting. The Great Dimming, as it came to be called, wasn't the death throes of a star. It was something equally fascinating but far less terminal. NASA's Hubble Space Telescope eventually revealed what had happened. Betelgeuse had burped. Not the polite kind. A surface mass ejection, an event so violent it makes our Sun's coronal mass ejections look like gentle breezes. A massive convection cell on the star's surface had erupted, curling superhot plasma into space. As this material moved away from the star and cooled, it formed dust grains. Billions upon billions of them, creating a cloud more than 100 million miles wide that simply blocked our view of part of the star's surface. The dust cloud's mass equaled roughly a year's worth of Betelgeuse's normal stellar wind, except it got ejected all at once. The event left lasting scars on the star itself. The surface cooled. Density dropped. Even years later, Betelgeuse hasn't fully recovered. It's still in an altered state, its southern hemisphere fundamentally changed by whatever triggered that enormous eruption. What causes these surface mass ejections? The answer involves convection on a scale that defies easy comprehension. Our Sun has convection cells too, granules of rising hot plasma and sinking cool plasma that give the solar surface its mottled appearance. Each granule is roughly the size of Texas. Betelgeuse's convection cells are as large as the orbit of Mars. Maybe larger. These massive bubbles of superheated gas rise and fall, creating turbulent, chaotic patterns across the star's surface. Sometimes they erupt, flinging material into space with enough violence to temporarily obscure the star from 650 light-years away. But the Great Dimming revealed something else, something that fundamentally changed our understanding of what Betelgeuse actually is. The star isn't alone. In early 2024, astronomers confirmed what they'd long suspected. Betelgeuse has a companion. A smaller star called Sawara, meaning her bracelet in Arabic, orbiting the red giant every 5.7 to 6 years at a distance of about 4 astronomical units. If this system were centered on our Sun, Sawara would orbit somewhere between Mars and Jupiter. This companion star is roughly 1.5 times the mass of our Sun, and it's plowing through Betelgeuse's enormous extended atmosphere like a speedboat through water. The wake it creates, a dense stream of gas trailing behind it as it orbits, produces observable effects that astronomers can detect from Earth. Changes in Betelgeuse's spectrum. Variations in the speed and direction of gases in the outer atmosphere. A pattern that repeats every 6 years, every 2,100 days, matching the companion's orbital period exactly. The discovery of Sawara helps explain many of Betelgeuse's mysterious behaviors. Those long-period brightness variations. The asymmetries in the star's atmosphere. The complex structures visible in high-resolution images. All influenced by this hidden companion carving channels through the red giant's outer layers. But the discovery also raises new questions about Betelgeuse's ultimate fate. Tidal interactions are pulling Sawara inward. Slowly, inexorably, gravity is dragging the companion closer to its massive partner. Within about 10,000 years, maybe as few as 9,000, Sawara might be engulfed entirely. The two stars could merge long before Betelgeuse goes supernova, and that merger would change everything. It would splash out gas, spin up Betelgeuse's rotation, potentially alter the properties of the eventual supernova itself. The physics of stellar mergers this massive remains largely theoretical because we've never actually watched one happen. Understanding what Betelgeuse is requires understanding what it was. This star didn't start as a red supergiant. It began life as an O-type main sequence star, one of the massive blue-white giants that dominate young stellar populations. Hot, bright, burning hydrogen in its core at prodigious rates. For several million years, Betelgeuse was nothing like the bloated red giant we see today. It was compact, dense, radiating primarily in ultraviolet wavelengths that would have made it appear brilliant blue to any observer. Then the hydrogen ran out. Not everywhere at once, but in the core where temperatures and pressures were highest. When that happened, the core contracted, heating up until it reached temperatures sufficient to fuse helium. The star's outer layers, no longer supported by hydrogen fusion, expanded dramatically. Betelgeuse briefly became a blue supergiant before expanding further and cooling, settling into its current configuration as a red supergiant. The transformation took perhaps a few thousand years. A cosmic eye blink. One moment, a compact blue star. The next, a red giant whose surface extends past Jupiter's orbit. This is where things get truly interesting, because the nuclear processes happening inside Betelgeuse right now are writing the script for one of the most energetic events in the universe. Deep in the core, beneath layers of hydrogen and helium, carbon and oxygen nuclei are slamming together at temperatures exceeding 600 million Kelvin. The fusion produces neon and magnesium, releasing energy that helps support the star against its own crushing gravity. But carbon burning doesn't last forever. For a star like Betelgeuse, this phase continues for roughly 1,000 years before the carbon runs out and the core contracts again, triggering the next burning stage. After carbon comes neon burning, then oxygen, then silicon. Each stage happens faster than the one before because each fusion reaction releases less energy per nuclei fused, requiring higher and higher reaction rates just to maintain pressure support against gravity. Silicon burning produces iron, and iron is where everything stops. Not slows down. Stops completely. Iron is the end of the line for fusion-powered energy generation. Fusing iron nuclei doesn't release energy. It requires energy input. Every fusion reaction up to this point has been an energy source, converting mass to energy according to Einstein's equations. But iron sits at the peak of the binding energy curve. Fuse it, and you're climbing uphill energetically. The star would have to invest energy to force iron nuclei together, which defeats the entire purpose of fusion as a power source. So when silicon burning produces iron in Betelgeuse's core, that iron just accumulates. No further fusion. No energy generation. Just an inert mass growing larger with each passing day. For a while, this doesn't matter. The layers above the iron core are still burning silicon, oxygen, neon, carbon, helium, hydrogen. Each shell producing energy, each contributing to the outward pressure that holds the star up against gravity. The star continues functioning normally from the outside even as its core transforms into a ticking time bomb. But that iron core keeps growing. More silicon burns. More iron accumulates. The core's mass increases steadily toward a critical threshold that physics won't allow it to cross while remaining stable. That threshold is the Chandrasekhar limit, approximately 1.4 solar masses. Below this mass, the core can support itself through electron degeneracy pressure, a quantum mechanical effect where electrons resist being squeezed too close together. Above this mass, not even electron degeneracy pressure can hold back gravity. When Betelgeuse's iron core reaches the Chandrasekhar limit, everything changes in less than a second. The collapse doesn't happen gradually. There's no slow compression giving the star time to adjust. The core implodes catastrophically, falling inward at velocities approaching a quarter of light speed. In roughly 0.25 seconds, a sphere the size of Earth compresses to a sphere about 20 kilometers across. During this collapse, the extreme conditions trigger processes that would be impossible anywhere else in the universe under normal circumstances. Protons and electrons, squeeze together under unimaginable pressure, combine to form neutrons and neutrinos. The neutrinos, nearly massless particles that barely interact with normal matter, flood outward carrying away enormous amounts of energy. The neutron core that forms is so dense that a teaspoon of its material would weigh more than Mount Everest. When the collapsing outer layers hit this incompressibly dense core, they rebound. Like a rubber ball hitting concrete, the infalling matter bounces back outward, generating a shockwave that propagates through the star's outer layers at supersonic speeds. This is the supernova. The shockwave racing outward, heating material to billions of degrees, blowing apart a star that has stood for millions of years. The explosion releases more energy in a few seconds than our sun will produce in its entire 10 billion year lifetime. And we'll see it. Eventually. Maybe. Here's where the uncertainty becomes maddening. The 2023 analysis suggesting Betelgeuse might explode within tens of years was based on modeling the star's pulsation periods and inferring its current evolutionary stage. The researchers noted that Betelgeuse's pulsation behavior matches theoretical predictions for a star in late-stage carbon burning, possibly approaching carbon exhaustion. Carbon burning, as mentioned, lasts about 1,000 years for a star of Betelgeuse's mass. If the star is near the end of this phase, then neon burning, oxygen burning, and silicon burning would follow in rapid succession. Neon burning takes perhaps a few years. Oxygen burning, maybe a year. Silicon burning, a few weeks at most. Add it up, and you get a timeline measured in years or decades rather than millennia. But other models aren't so certain. Surface observations alone can't definitively reveal what's happening in the core. The star's outer layers are so vast, so opaque, that they hide the nuclear furnace deep within. Different assumptions about the star's mass, rotation, mixing processes, and mass loss history produce different evolutionary timelines. Some models suggest Betelgeuse could continue in its current state for another 100,000 years. Others agree with the shorter timeline. Without being able to probe the core directly, we're making educated guesses based on surface symptoms. What we do know is that Betelgeuse is somewhere in the final stages of its life. Carbon burning at minimum, possibly further along. The iron core is growing. The supernova is coming. The only question is when. And there's another wrinkle. Betelgeuse is 650 light-years away. The light we're seeing right now left the star around the year 1374, during the late Middle Ages. If Betelgeuse exploded yesterday, we wouldn't know for another 649 years, 364 days. It's entirely possible the star has already exploded. The shockwave could be racing through space right now, carrying the light and neutrinos that will announce Betelgeuse's death to Earth. We just haven't received the message yet because information can't travel faster than light. This creates a strange temporal uncertainty. When astronomers talk about Betelgeuse exploding in tens of years, they mean tens of years from now as observed from Earth. But the actual explosion could be happening now, or could have happened centuries ago, or might not happen for thousands of years. We're observing the past, making predictions about the future, while the present state of the star remains fundamentally unknowable. What would that explosion actually look like from Earth? The predictions are spectacular. Peak brightness is expected to reach apparent magnitude -8 to -12, making Betelgeuse roughly as bright as the half-moon. Not as an extended disk like the moon, but as an intensely brilliant point of light. For several months, Betelgeuse would be clearly visible during daylight. You'd be able to point it out in the afternoon sky, a star bright enough to see while the sun is up. At night, it would dominate the constellation Orion, outshining everything except the moon itself. The brightness would peak about 2 weeks after the initial explosion, then fade gradually over months. After about 30 days, it would dim to roughly half-moon brightness. After 3 months, it would begin fading more rapidly, though it would remain visible to the naked eye for years as the supernova remnant expanded and cooled. But the first signal wouldn't be light at all. It would be neutrinos. During the core collapse, roughly 99% of the explosion's energy is carried away by neutrinos rather than light or kinetic energy. These neutrinos, produced in staggering quantities during the collapse, would reach Earth hours before the visible light. Neutrino detectors scattered around the world would suddenly register millions of events as this neutrino pulse washed over Earth. Scientists would have perhaps 12 to 24 hours of advance warning before the light arrived, time to alert observatories worldwide and prepare for one of the most significant astronomical events in recorded history. That's assuming the detection networks are working properly. Assuming someone's monitoring the data. Assuming the alerts go out correctly. The neutrino warning would be brief and easy to miss if nobody's watching. Then the light would arrive, and Betelgeuse would transform from a red giant star into something no human has ever witnessed at this brightness level. Not dangerous to Earth, our distance ensures that, but visually overwhelming. A supernova in our cosmic backyard, close enough to see in detail but far enough to be perfectly safe. The physics of what we'd actually be seeing is worth understanding. The first light reaching Earth wouldn't actually come from the explosion itself. It would come from radioactive decay. When the core collapses and rebounds, the shockwave rips through the star's outer layers at thousands of kilometers per second, heating them to billions of degrees. This extreme temperature triggers a cascade of nuclear reactions in the expanding debris, creating massive quantities of radioactive isotopes. Nickel-56 is the primary product, which decays to cobalt-56, which then decays to stable iron-56. Each decay step releases gamma rays that heat the expanding gas cloud, causing it to glow. This radioactive glow is what we'd actually be seeing during those first weeks and months. The supernova wouldn't be showing us the explosion directly, but rather its radioactive afterglow. Think about that for a moment. The brightest astronomical event most people will ever witness isn't even the event itself. It's nuclear decay happening in an expanding cloud of stellar debris traveling through space at a significant fraction of light speed. The energy numbers involved are genuinely difficult to comprehend. A supernova releases about 10 to the 44 joules of energy in the first few seconds. That's more energy than our sun will produce over its entire 10 billion year lifetime, released in less time than it takes to read this sentence. Most of that energy, roughly 99%, escapes as neutrinos that barely interact with normal matter. The remaining 1%, split between kinetic energy of the explosion and electromagnetic radiation, is still enough to outshine billions of stars. But here's what makes Betelgeuse particularly fascinating beyond just its eventual explosion. The star isn't waiting quietly for its demise. It's actively reshaping itself right now through processes we're only beginning to understand. Recent observations reveal that Betelgeuse isn't a simple sphere but a churning, asymmetric mass of convection cells, each larger than the entire orbit of Mars. These massive bubbles of plasma rise from deep within the star, cool at the surface, and sink back down in a continuous cycle. The scale is absurd. One convection cell on Betelgeuse could swallow our entire inner solar system. These convective motions drive another critical process: mass loss. Betelgeuse is hemorrhaging material into space at a rate millions of times greater than the sun's solar wind. Every year, the star loses roughly the mass of Earth through this continuous outflow. Over thousands of years, this creates a complex circumstellar envelope roughly 250 times the size of the star itself, filled with gas and dust that's been shed from Betelgeuse's outer layers. The 2019 to 2020 Great Dimming event gave us an unprecedented look at this mass loss in action. What happened wasn't a sign of imminent explosion, but something potentially more interesting. Hubble observations showed that a massive convection cell carried superhot plasma from deep within the star up through its atmosphere and into space. As this material moved away from the star and cooled, it condensed into dust grains that formed a cloud more than 100 million miles wide. This dust cloud passed between us and Betelgeuse, blocking a significant fraction of the star's light and causing the dramatic dimming we observed. Scientists call this a surface mass ejection, analogous to the sun's coronal mass ejections but scaled up to match Betelgeuse's enormous size. The ejected material had a mass comparable to an entire year's worth of the star's normal stellar wind, all released in one discrete event. And here's the remarkable part: this single ejection left lasting effects on the star. Even years later, Betelgeuse's surface remains cooler and less dense than before the dimming, suggesting the star's structure was fundamentally altered by this event. What triggered that massive ejection? We don't know. The convection cells that drive Betelgeuse's surface activity are chaotic and unpredictable. They rise and fall on timescales of months to years, driven by the immense energy flowing outward from the fusion reactions deep in the core. Sometimes they apparently cooperate to produce extraordinary events like the Great Dimming. Sometimes they don't. Then there's the companion star. For years, astronomers suspected Betelgeuse might not be alone, but the evidence was indirect and ambiguous. Recent observations finally confirmed it. A companion star named Suwarrow, about 1.5 times the Sun's mass, orbits Betelgeuse every 5.7 to 6 years at a distance roughly equivalent to the orbit of Jupiter. This might not sound particularly close, but remember Betelgeuse's size. If you placed Betelgeuse at the center of our solar system, its surface would extend beyond Jupiter's orbit. Suwarrow is orbiting through the outer layers of Betelgeuse's extended atmosphere. As Suwarrow plows through this tenuous material, it creates a wake, a dense stream of gas trailing behind the companion star like the wake of a boat moving through water. This wake affects Betelgeuse's spectrum, creating observable changes in the speed and direction of gases in the outer atmosphere. The pattern repeats every 6 years or about 2,100 days, providing clear evidence of the companion's presence and orbital period. Suwarrow's fate is sealed. Tidal interactions are gradually pulling it closer to Betelgeuse. Within about 10,000 years, perhaps as soon as 9,000 years, the companion will be engulfed entirely. When that happens, several things might occur. The merger would release energy, ejecting some of Betelgeuse's outer envelope into space. The angular momentum transfer would spin up Betelgeuse, potentially affecting its internal structure and rotation. Most intriguingly, this merger could alter the properties of Betelgeuse's eventual supernova, changing the explosion's energy, the composition of the ejected material, or the characteristics of whatever compact remnant is left behind. Or the merger might happen after the supernova. The timeline is genuinely uncertain. Betelgeuse could explode tomorrow, astronomically speaking, or it could survive for another 100,000 years. The companion merger could happen before the explosion or never happen at all if Betelgeuse explodes first. We're watching multiple cosmic timelines unfold simultaneously, unable to predict which will complete first. What happens to Suwarrow if Betelgeuse explodes while the companion is still orbiting? The supernova shockwave would hit the smaller star like a wall traveling at thousands of kilometers per second. Depending on Suwarrow's position in its orbit, it might be obliterated, stripped of its outer layers, or potentially flung out of the system entirely. If it survives, it would suddenly find itself orbiting not a red supergiant but a neutron star or possibly a black hole, depending on the collapse dynamics. And that brings us to the final act. What remains after Betelgeuse explodes? The star's core will collapse to nuclear density, creating either a neutron star or a black hole. Current estimates suggest Betelgeuse's mass is right on the boundary between these outcomes, somewhere around 16 to 19 solar masses today. That's close to the theoretical dividing line, though the exact threshold depends on details of the collapse physics that we can't predict precisely. A neutron star would be roughly 20 kilometers across but contain more mass than the Sun, compressed to densities where a teaspoon of material would weigh as much as a mountain. The surface gravity would be billions of times stronger than Earth's. The magnetic field would be trillions of times stronger than any field we can produce in laboratories. It would be spinning rapidly, potentially completing dozens of rotations per second, and if the magnetic axis is misaligned with the rotation axis, it would produce beamed radiation that sweeps across space like a lighthouse. We might detect it as a pulsar. Or the collapse might not stop at neutron star densities. If the core mass exceeds roughly 3 solar masses at the moment of collapse, nothing can halt the gravitational implosion. The core would collapse past neutron star density, past any conceivable form of matter pressure, until it forms an event horizon. Betelgeuse would leave behind a stellar mass black hole, an object from which not even light can escape. Either outcome represents one of the most extreme environments in the universe, where our everyday understanding of physics breaks down completely and general relativity dominates the behavior of matter and energy. The neutron star scenario presents a cosmos-defying object. 20 kilometers across. Mass exceeding the Sun. Density so extreme that atomic structure ceases to exist as we understand it. At neutron star densities, protons and electrons merge into neutrons through a process called neutronization. The matter enters a state called degenerate matter, where quantum mechanical effects dominate and normal chemical bonds become meaningless. A sugar cube-sized chunk would weigh roughly 1 billion tons. The gravitational field at the surface would be so intense that light itself bends noticeably, allowing you to theoretically see the back of the neutron star by looking forward as photons curve around it. But here's what makes neutron stars genuinely bizarre. They spin fast. When Betelgeuse's massive core collapses from stellar dimensions down to city-sized proportions, conservation of angular momentum kicks in with brutal efficiency. Like an ice skater pulling in their arms, the collapse dramatically increases rotation rate. Young neutron stars can rotate hundreds of times per second. The fastest known pulsar spins 716 times every second. At those rotation rates, the surface moves at a significant fraction of light speed. The magnetic fields defy comprehension. Betelgeuse already possesses a magnetic field, but when that field gets compressed into neutron star dimensions, it intensifies by factors of trillions. The resulting field can reach 1 trillion Tesla, compared to Earth's puny half-Gauss field or the strongest laboratory magnets at around 50 Tesla. These fields reorganize matter at the atomic level, stretching atoms into needle-like shapes aligned with field lines. They accelerate charged particles to near light speed, generating beams of radiation that sweep across space. If the magnetic axis differs from the rotation axis, we get a pulsar. Those beams sweep past Earth once per rotation, creating regular pulses we can detect. Betelgeuse could become one of the nearest and brightest pulsars in the sky, a cosmic lighthouse visible to radio telescopes for potentially millions of years. Each pulse would carry information about the neutron star's internal structure, its magnetic field configuration, how it's slowing down, and what's happening in its immediate environment. The black hole alternative presents an entirely different reality. If collapse proceeds past neutron degeneracy pressure, nothing stops it. The core contracts through neutron star density, past any theoretical limit, until it forms a singularity surrounded by an event horizon. The mathematics suggest the singularity has infinite density and zero volume, though most physicists suspect quantum gravity effects we don't yet understand prevent true infinities. Regardless, the event horizon forms a boundary beyond which classical physics becomes inadequate and general relativity takes complete control. For a stellar mass black hole from Betelgeuse, the event horizon would measure roughly 50 to 60 kilometers in radius, depending on the final collapsed mass. Small by cosmic standards. Enormous by human comprehension. Nothing that crosses that boundary can return, not matter, not light, not information in any classical sense. The escape velocity at the event horizon exactly equals light speed. 1 millimeter inside, light itself cannot escape the gravitational pull. Black holes are not cosmic vacuum cleaners, despite popular misconception. They don't suck material in from vast distances. Their gravitational influence extends no farther than any other object of equivalent mass. If the Sun suddenly became a black hole of the same mass, Earth's orbit wouldn't change. But anything that ventures too close faces tidal forces that increase dramatically near the event horizon. The difference in gravitational pull between your head and feet would stretch you into a long, thin stream of atoms, a process astronomers cheerfully call spaghettification. Which outcome occurs? Current models suggest Betelgeuse sits right on the boundary. Stars with iron cores below roughly 2.5 solar masses produce neutron stars. Above roughly 3 solar masses, collapse continues to black hole formation. Between those values lies uncertainty, where the equation of state for ultradense matter becomes critical. We don't fully understand how matter behaves at nuclear densities under extreme conditions. Laboratory experiments can't replicate those environments. Theoretical models make predictions, but they rely on assumptions about physics we cannot directly test. Betelgeuse's current mass appears to be around 16 to 19 solar masses, but most of that mass resides in the envelope that will be ejected during the supernova. The core mass determines the outcome, and measuring that precisely from 650 light-years away presents formidable challenges. Different models of the star's structure and different assumptions about mass loss rates yield different core mass estimates. Some calculations suggest the core might barely exceed the neutron star threshold, producing a black hole. Others suggest it might fall just short, creating a massive neutron star instead. The supernova itself will provide clues. The amount of material ejected, the energy of the explosion, the composition of the remnant, and the light curve characteristics all depend partly on whether the core forms a neutron star or continues collapsing. But interpreting those observations in real time will be difficult. Supernova physics involves complex interactions between nuclear fusion, shock waves, neutrino transport, and stellar structure. Multiple factors influence what we see, and disentangling them requires sophisticated modeling. Then there's the neutrino signal. When the core collapses, it releases roughly 99% of the explosion's energy as neutrinos in just a few seconds. These neutrinos flood outward at nearly light speed, carrying information about the collapse itself. Neutrino detectors on Earth would register this burst hours before the visible light arrives, since neutrinos escape immediately while light takes time to diffuse through the star's outer layers. The characteristics of that neutrino burst, its duration, energy spectrum, and flavor composition, would reveal whether the core successfully forms a neutron star or continues collapsing into a black hole. But detecting and interpreting that signal presents challenges. Neutrinos interact weakly with matter. Billions pass through your body every second from the sun, and you never notice. Detecting a supernova neutrino burst requires massive detectors containing thousands of tons of ultra-pure water or other target materials, surrounded by photomultiplier tubes watching for the faint flashes that occur when neutrinos occasionally interact with atomic nuclei. Current detectors like Super Kamiokande in Japan, Ice Cube at the South Pole, and others would all register Betelgeuse's neutrino burst, but extracting detailed physics from that data remains complex. What happens in the seconds after core collapse determines whether we get a neutron star or black hole. The initial collapse creates a protoneutron star, incredibly hot and dense, still contracting. Neutrinos stream outward, carrying away thermal energy and allowing further contraction. The question becomes whether this protoneutron star stabilizes or whether its mass exceeds the maximum that neutron degeneracy pressure can support. That maximum, called the Tolman-Oppenheimer-Fokoff limit, depends on the equation of state for neutron star matter, which we don't know precisely. Current estimates place it somewhere between 2 and 3 solar masses, but the uncertainty is significant. If the protoneutron star stabilizes, it cools over thousands of years as neutrinos carry away internal heat. The temperature drops from billions of degrees to millions, then eventually to hundreds of thousands as the star settles into its long-term configuration. The crust solidifies into exotic crystalline structures of neutron-rich nuclei. The interior may contain superfluid neutrons and superconducting protons, quantum states of matter that exist nowhere else in the universe. Deeper still, the core might contain strange quark matter or other exotic phases we can only speculate about. If collapse continues past the neutron star limit, the protoneutron star's surface shrinks inward, approaching the Schwarzschild radius where the event horizon forms. Once that boundary appears, no information about the interior can escape. The matter continues falling inward toward the central singularity, but external observers see the surface freeze at the event horizon due to extreme gravitational time dilation. Light from the surface becomes infinitely redshifted and dimmed. The black hole has formed. Either outcome represents the ultimate fate of Betelgeuse's core, but the observable universe will continue around it. The expanding supernova remnant will collide with the circumstellar material Betelgeuse shed over millennia, creating spectacular shock waves and potentially triggering new star formation in surrounding molecular clouds. The compact remnant, whether neutron star or black hole, will orbit through the galaxy carrying its history encoded in its properties. And 650 light-years away, we'll watch it all unfold, knowing that whatever we see happened during the Middle Ages, when Betelgeuse's light began its journey toward Earth. The supernova remnant itself becomes a physics laboratory unlike anything we can create on Earth. As the ejected material expands outward at thousands of kilometers per second, it slams into the circumstellar medium that Betelgeuse spent millennia depositing around itself. That collision generates shock waves that heat the gas to millions of degrees, creating X-ray emission and accelerating particles to near-light speeds. These cosmic ray particles carry energy throughout the galaxy, potentially influencing star formation in distant molecular clouds. The shock fronts also compress surrounding gas, which might trigger gravitational collapse and the birth of new stars. In this sense, Betelgeuse's death could seed the next generation of stellar systems. But here's what makes this even more remarkable. The expanding debris doesn't move uniformly. Instabilities in the shock front create turbulent mixing, folding heavy elements from the star's interior into the outer layers. Fingers of nickel and iron pierce through shells of oxygen and carbon. The remnant becomes a chaotic sculpture of elements, each layer telling part of the story about what burned where inside Betelgeuse's core. Observing this structure reveals the architecture of a dying star's interior, information we can't obtain any other way. The optical display would evolve dramatically over months and years. Initially, we'd see a brilliant point source, painfully bright to look at directly despite being 650 light-years away. That light comes primarily from radioactive decay, specifically nickel-56 decaying to cobalt-56, which then decays to stable iron-56. Each decay releases gamma rays that scatter through the expanding material, gradually degrading to visible light. This process powers the light curve, the graph of brightness versus time that characterizes how supernovae fade. After several weeks, the expanding shell becomes transparent enough that we can see deeper into the ejecta. The supernova enters what astronomers call the nebular phase. Now we're looking at a glowing cloud, not a point source. Spectroscopy reveals emission lines from different elements at different velocities, mapping the three-dimensional structure of the explosion. Oxygen moves at one speed, silicon at another. The pattern reveals asymmetries in the explosion itself, whether material was ejected more strongly in certain directions, whether the core collapse was perfectly symmetric or tilted. And here's something that doesn't get mentioned enough. The supernova won't just be bright. It'll be beautiful. False color images combining different wavelengths will show intricate structures, filaments, and knots where density variations create instabilities. The Hubble Space Telescope and James Webb Space Telescope will capture details impossible to see from ground-based observatories. We'll watch the remnant expand in real time over years, actually seeing it grow larger in angular size as the debris races outward. That growth rate tells us the explosion energy. If the remnant expands faster than models predict, Betelgeuse released more energy than we thought. If slower, perhaps some energy went into creating the compact remnant instead of driving the expansion. Either way, we learn something fundamental about how massive stars die. The data from Betelgeuse's supernova will refine every model we have about stellar evolution and explosion mechanisms. Now think about the companion star, Sivora. What happens to it when Betelgeuse explodes? The blast wave will reach Sivora's position within hours, slamming into it with energy that makes hurricanes look gentle. If Sivora has already been engulfed by Betelgeuse's expansion, it's destroyed completely, vaporized in the explosion. But if it's still orbiting independently when the supernova occurs, it faces a different fate. The shock wave strips away its outer atmosphere, potentially exposing deeper layers or even the core. The radiation flash heats its surface to extreme temperatures. But Sivora might survive, continuing to orbit the remnant, now a runaway star blasted by the explosion that destroyed its companion. That scenario creates something called a binary pulsar system if the remnant is a neutron star. Sivora orbits the neutron star, which spins rapidly and emits beams of radiation like a lighthouse. Every time a beam sweeps past Earth, we detect a pulse. The orbital motion causes periodic Doppler shifts in the pulse timing, and analyzing those shifts reveals the orbit's properties with incredible precision. Binary pulsars have provided some of the strongest tests of general relativity, measuring gravitational wave emission and confirming Einstein's predictions to extraordinary accuracy. If Betelgeuse forms a black hole instead, the system becomes even more exotic. Sivora orbits an invisible companion, detectable only through its gravitational influence. As Sivora's stellar wind falls toward the black hole, it forms an accretion disk, spiraling inward and heating to millions of degrees before crossing the event horizon. That disk emits X-rays, creating what we call an X-ray binary system. These systems let us measure black hole masses and study how matter behaves in extreme gravitational fields. But there's another possibility that doesn't involve Sivora surviving at all. The explosion might be asymmetric enough to give the neutron star or black hole a kick, sending it flying through space at hundreds of kilometers per second. Observations of other supernovae show that compact remnants often receive these kicks, probably from asymmetries in neutrino emission during core collapse. If Betelgeuse's remnant gets kicked, it becomes a runaway object, eventually leaving the region entirely and wandering the galaxy alone. The debris field itself persists for tens of thousands of years, gradually mixing with the interstellar medium. Elements forged in Betelgeuse's core, carbon and oxygen from helium burning, neon and magnesium from carbon burning, silicon and sulfur from oxygen burning, iron from silicon burning, spread through space. Those elements eventually become incorporated into new molecular clouds. Stars form from those clouds. Planets form around those stars. And on at least one of those planets, beings might eventually look up at their night sky and wonder about the origins of the atoms in their bodies. You're made of star stuff, as Carl Sagan famously said. But more specifically, you're made of supernova stuff. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now, all of it was forged inside stars and scattered by explosions like the one Betelgeuse will eventually undergo. Every atom heavier than helium in your body came from stellar nucleosynthesis or supernova processes. When Betelgeuse explodes, it'll be creating the raw materials for future life, continuing the cycle that produced us. The observation campaign for Betelgeuse's supernova would be the most coordinated in astronomical history. Every major telescope on Earth and in space would turn toward Orion. Radio dishes would track the expanding shell. X-ray satellites would monitor the high-energy emission. Neutrino detectors would capture the burst from core collapse. Gravitational wave observatories would search for signals from the explosion asymmetry or the forming compact object. The sheer volume of data would dwarf anything we've collected from previous supernovae. And we'd have something unprecedented, warning time. Unlike supernovae in distant galaxies that we discover only after they've already exploded, Betelgeuse sits close enough that we might detect precursor signals. Changes in its oscillation patterns. Variations in mass loss rate. Alterations in its spectrum indicating shifts in surface temperature or composition. If we're lucky, these changes might give us days, weeks, or even months of advance notice that the explosion is imminent. That warning would let us prepare. Telescopes could be pre-positioned. Observation schedules cleared. Amateur astronomers worldwide could be alerted to watch for the sudden brightening. The discovery wouldn't be a surprise finding on some automated sky survey, but a predicted event with thousands of eyes ready to witness it. We'd see the neutrino burst, know the explosion had occurred, and then wait hours for the light to arrive, building anticipation for what would become the most documented astronomical event ever. Human response. None needed, script complete at exactly 1666 words. Betelgeuse occupies a unique position in human consciousness that extends far beyond its astronomical significance. For thousands of years, humans have looked up and seen this red-orange point of light marking Orion's shoulder. Ancient Egyptians associated it with Osiris. Aboriginal Australians wove it into their creation stories. Medieval Arab astronomers gave it the name we still use today. The star has been a constant companion throughout human history, unchanged in its basic appearance across all those millennia. But we're living in the era when that constancy might end. Think about that for a moment. Every human who has ever lived, from the first Homo sapiens in Africa to people born yesterday, has looked up at essentially the same night sky. The same constellations. The same patterns. Yes, stars move slightly over thousands of years due to proper motion, and a few supernovae have appeared and faded. But the fundamental structure of the night sky has remained stable throughout all of human existence. Betelgeuse's explosion would change that. Suddenly, dramatically, in a way that would be impossible to miss. Orion would be transformed. Instead of the familiar pattern we've known forever, there would be an intensely bright new star blazing where Betelgeuse used to be. The constellation would become unrecognizable. And unlike previous historical supernovae, which appeared in regions of the sky not associated with prominent constellations, this one would fundamentally alter one of the most recognizable patterns in the heavens. Every culture on Earth would notice. Every person with functioning eyesight would see it. The psychological impact would be profound. We take the night sky for granted. It's stable, predictable, essentially eternal from a human perspective. Seeing it change so dramatically would remind us that we live in a dynamic universe where even things that seem permanent are temporary. Stars are born, evolve, and die, just on timescales that usually exceed human comprehension. Betelgeuse would compress that timescale into a single human lifetime, giving us a visceral understanding of stellar mortality. The scientific legacy would extend far beyond the immediate observations. The data collected from Betelgeuse's supernova would inform stellar models for generations. We'd finally have ground truth for red supergiant evolution, core collapse dynamics, nucleosynthesis yields, and remnant formation. Every theoretical model could be tested against real observations of a nearby supernova of known distance and well-studied progenitor. The uncertainties that currently plague supernova physics would shrink dramatically. Future students would study the Betelgeuse supernova the way current students study the 1987 A supernova in the Large Magellanic Cloud. But Betelgeuse would provide far more detailed data because of its proximity and the advanced instrumentation we now have. It would become the benchmark event, the standard against which all other supernovae are measured. Textbooks would feature before and after images. Research papers would reference the observations for decades or centuries to come. The remnant itself would become a target of intense ongoing study. Assuming a neutron star forms rather than a black hole directly, we'd watch it cool and spin down over years and decades. We'd track pulsar emission if the neutron star's magnetic field is properly aligned. We'd measure its motion through space, determining whether it received a natal kick and how strong that kick was. We'd study the surrounding nebula as it expands and interacts with the interstellar medium, watching in real time as the enriched material spreads outward. X-ray observations would reveal the shock-heated gas. Radio observations would track the expanding shell and any pulsar wind nebula that forms. Optical observations would monitor the fading supernova and the evolving nebular spectra as different elements become visible. Infrared observations would detect dust formation in the ejecta, watching as newly synthesized elements condense into solid grains that will eventually become incorporated into new stars and planets. The cultural impact would manifest in unpredictable ways. Art, music, literature, all would respond to this cosmic event. We'd see paintings, compositions, novels, films inspired by the supernova. It would enter our cultural lexicon the way the moon landing or other historic events have. Children born during the supernova's visibility would grow up with stories about the year the new star appeared. It would become a temporal marker, a way of dating events. That was 2 years before Betelgeuse exploded, or I was born the year Betelgeuse went supernova. Religious and philosophical interpretations would inevitably arise. Some would see divine significance in the event. Others would view it as affirmation of scientific understanding. Doomsday predictions would circulate despite astronomers' assurances of Earth's safety. The explosion would become a Rorschach test, with different groups projecting their own meanings onto it. But underneath all the interpretation, the raw fact would remain: we witnessed the death of a star. Education systems would seize the opportunity. Planetariums would create special programs. Teachers would use the event to engage students with astronomy. Science centers would host viewing events. Amateur astronomy clubs would see membership surges as people wanted to understand what they were seeing. The supernova would inspire a generation of young scientists the way the Apollo program or Hubble's deep field images have inspired others. The economic impact would be non-trivial. Tourism to dark sky locations would spike as people sought optimal viewing conditions. Telescope sales would surge. Astronomy apps would see massive download numbers as people tried to locate and identify the supernova. Universities with astronomy programs would see increased enrollment. The event would generate economic activity in ways that purely scientific events rarely do, simply because of its visibility and accessibility to the general public. There's something profound about a cosmic event that everyone can witness simultaneously. Most astronomical discoveries require specialized equipment or technical knowledge to appreciate. Gravitational waves, exoplanet transits, distant galaxy observations, these are real and important but not viscerally accessible to most people. A bright supernova is different. It requires no equipment, no expertise. Just eyes and a clear sky. Everyone from professional astronomers to young children would be looking at the same thing, experiencing the same wonder. The timing uncertainty adds a strange tension to our relationship with Betelgeuse. It could happen tomorrow. It could happen in 100,000 years. We know it's coming, but we don't know when. This creates a unique situation where professional astronomers maintain constant vigilance on a star that might not do anything dramatic for millennia. But the payoff, if it happens during our lifetimes, would be extraordinary. So we watch. We measure. We wait. Every observation adds to our understanding. Every spectrum reveals details about the star's current state. Every brightness measurement contributes to models of its variability. Even if Betelgeuse doesn't explode for thousands of years, the data we're collecting now will help future astronomers understand what happened when it finally does. We're building a comprehensive archive of the star's behavior in its final stages, creating a baseline against which the explosion can be compared. The discovery of Sawara adds narrative complexity. Now we're not just watching a star, we're watching a binary system approaching its dramatic conclusion. We're witnessing tidal interactions, atmospheric disturbances, and gravitational dynamics playing out in real time. The companion star transforms Betelgeuse from a solitary giant into part of a cosmic dance, one that will end with either merger or violent separation. Previous generations looked at Betelgeuse and saw only a red star. We look at it and see an entire stellar ecosystem. A massive primary star in its death throes. A sun-like companion being slowly pulled inward. A vast circumstellar envelope shaped by stellar winds and convective ejections. Giant convection cells churning across the surface. A complex atmosphere with shock waves and density variations. All of this detail invisible to the naked eye but revealed through modern instruments. The contrast between what we see and what we know creates cognitive dissonance. That faint red point of light is actually a stellar monster hundreds of times wider than the Sun's orbit. It's so far away that its light takes 650 years to reach us, meaning we see it as it was in the Middle Ages. It might have already exploded, and we simply don't know yet because the light hasn't arrived. The apparent simplicity of a point of light masks extraordinary complexity and distance. When Betelgeuse does explode, assuming it happens within observable human timescales, it will be the ultimate validation of astrophysical theory. We predicted this would happen. We understand why it happens. We can describe the physics in detail. And then nature would demonstrate that our understanding is fundamentally correct by performing the exact process we predicted. That moment of validation, when theory meets observation on such a dramatic scale, represents science at its most powerful. The atoms in your body came from stars like Betelgeuse. That's not metaphor or poetry. It's literal fact. The carbon in your cells, the calcium in your bones, the iron in your blood, all forged in stellar cores and scattered by supernova explosions. You are physically made of material that once existed inside dying stars. Betelgeuse will create more of that material, continuing the cycle that produced us. We're watching our own cosmic origin story play out in the present tense. That red star in Orion's shoulder contains your past and someone else's future. The atoms it will scatter might someday form planets. Life might arise on those planets. Beings might evolve who look up at their own night sky and wonder about the stars. And they'll be made of Betelgeuse, just as you're made of earlier stellar generations. The chain continues, unbroken, from the first stars until the last. We exist in a strange moment of cosmic anticipation. Somewhere above us, visible every clear winter night, a star is ending. We just don't know if that ending has already occurred, is occurring right now, or won't occur for another 100,000 years. The light traveling toward us carries information, but that information is always 650 years old by the time it arrives. We're perpetually looking at Betelgeuse's past, never its present. This creates an unusual relationship between observer and observed. Betelgeuse might be gone. The star we see tonight might be a ghost, an afterimage of something that no longer exists. Or it might continue shining for millennia beyond our own lifetimes, outlasting human civilization itself. We don't know. Can't know. The uncertainty is fundamental, built into the structure of space-time itself. What we do know is that the explosion is inevitable. Physics doesn't offer escape clauses for dying stars. The iron core will grow. The Chandrasekhar limit will be reached. Collapse will occur. Everything else is details and timing. The when remains uncertain, but the what is essentially guaranteed. That guarantee makes Betelgeuse unique among astronomical objects. We're not speculating about whether it might do something interesting. We know it will. The question is purely temporal. This isn't like searching for hypothetical phenomena or hoping to detect rare events. This is watching a confirmed future event, waiting for it to manifest in our observable present. The neutrino detectors sit ready. The telescope networks are in place. The observation protocols exist. The scientific community has prepared for this event more thoroughly than perhaps any other astronomical occurrence in history. We've done everything possible except control when it happens. That remains entirely up to physics and chance. And maybe that's appropriate. Maybe it's fitting that the universe doesn't operate on our schedule. We've predicted what will happen, understood the mechanisms, built the instruments to observe it, but we can't dictate the timing. Nature proceeds at its own pace, indifferent to human impatience for curiosity. Betelgeuse will explode when the iron core reaches critical mass, not before, not after, regardless of how eagerly we're watching. If it happens tomorrow, we'll witness the most spectacular astronomical event in recorded history. A supernova visible in daylight for months. A transformation of one of the most recognizable constellations. A flood of scientific data that will revolutionize our understanding of stellar death. Every telescope on Earth and in space turning toward Orion, capturing details impossible to obtain from more distant supernovae. If it happens in 1,000 years, none of us will see it, but someone will. Future generations with instruments we can barely imagine will observe the explosion with capabilities that make our current technology look primitive. They'll answer questions we haven't thought to ask yet. The data will be different, but the fundamental physics will remain the same. Betelgeuse will still collapse, explode, scatter its elements, and leave behind a compact remnant. The timeline changes. The outcome doesn't. The atoms created in that explosion will drift through space for millions of years. They'll mix with the interstellar medium, become incorporated into molecular clouds, and eventually collapse to form new stars. Planets will coalesce from the debris. And maybe, on one of those planets, life will emerge. Beings will evolve. They'll develop technology, build telescopes, and look outward at the universe. They'll be made of Betelgeuse. They won't know it, probably won't even be able to trace their atomic ancestry back to a specific supernova. But the connection will exist regardless. That's the real legacy of stellar explosions. Not the brief light show, spectacular as it might be. Not even the scientific data, valuable as that is. The legacy is material. Elements. Building blocks. The periodic table entries that make chemistry possible, life feasible, and consciousness achievable. Every supernova is a forge, transmuting lighter elements into heavier ones and distributing them across space. Without supernovae, the universe would contain only hydrogen and helium. No carbon. No oxygen. No iron. None of the elements necessary for planets or people. Betelgeuse represents this process on a human timescale. We can watch it approach the moment of transformation. We can understand what's happening inside the core, predict what will emerge from the explosion, and anticipate how the remnant will evolve. The star bridges the gap between the abstract and the observable, between theoretical physics and visible reality. Look at Betelgeuse tonight if the sky is clear. That red-orange point of light in Orion's shoulder. That's not just a star. It's a massive stellar furnace 650 light-years away, churning through its final nuclear fuel, supported against gravity by fusion reactions that won't last much longer. It's a cosmic time bomb with a fuse we can't quite see. It's the future birthplace of atoms that might someday form planets, life, and consciousness. It's a reminder that the universe operates on scales that dwarf human concerns while simultaneously creating the very conditions that make those concerns possible. The star you're looking at might not exist anymore. The light might be traveling toward us from an explosion that already happened. Or the star might shine for another 100 millennia, long after our civilization has risen, peaked, and faded. Either way, Betelgeuse connects us to the larger cosmic story. We're not separate from the universe, observing it from outside. We're part of it, made from it, shaped by the same processes that create and destroy stars. When Betelgeuse explodes, whether we see it or not, it will continue the cycle that produced us. New elements will scatter. New stars will form. New worlds will emerge. And somewhere in that distant future, beings we cannot imagine might look up at their sky and wonder about the origins of their existence, never knowing they're made from the remnants of a red supergiant that humans once called Betelgeuse, that we watched and studied and waited for, hoping to witness the moment when a star becomes a supernova, becomes stardust, becomes the raw material for everything that follows. That's what's really happening in Orion's shoulder. Not just the death of a star, but the continuation of the only process we know that creates the chemical diversity necessary for complexity, for planets, for life, for minds capable of understanding what they're made of and where those materials came from. Betelgeuse is ending. Something else is beginning. The atoms don't care about the distinction. They'll continue existing, recombining, forming new structures, participating in the ongoing evolution of matter from simple to complex and back again. The star will explode. The remnant will cool. The elements will disperse. New generations will form. And the universe will continue its relentless process of transformation, converting energy to matter, matter to structure, structure to complexity, and complexity to consciousness. Betelgeuse is one step in that process. An ending that enables countless beginnings. A death that seeds innumerable futures. We're watching it happen in slow motion, stretched across the vast distances between stars, compressed into the narrow window of human observation. The red giant in Orion's shoulder is more than just an astronomical object. It's a preview of our own cosmic future, a reminder of our atomic past, and a demonstration that the universe creates and destroys with equal facility. Stars die so that new stars can form. Elements scatter so that planets can coalesce. Supernovae explode so that life becomes possible. The cycle continues, indifferent to observers but creating the conditions for observation itself. Betelgeuse will explode. That's not prediction. That's physics. When it happens, the sky will change. Our understanding will deepen. The periodic table will gain new members courtesy of nucleosynthesis in the expanding debris. And somewhere, perhaps on a world that doesn't exist yet, formed from atoms that are currently locked inside Betelgeuse's core, future beings might look up and see the remnant of this explosion, never knowing they're observing their own origin story written in light that's traveled across space for eons. That's the real meaning of Betelgeuse. Not a star waiting to die, but a star preparing to transform. Not an ending, but a transition. Not death, but metamorphosis. The elements locked in that red giant's core will scatter, drift, and eventually become part of something new. The universe doesn't waste material. It recycles everything, transforming endings into beginnings with the same indifferent efficiency it applies to all physical processes. So when you look at Betelgeuse, you're not just seeing a star. You're seeing your past and someone else's future. You're seeing the forge that created the atoms you're made of, preparing to create more. You're seeing physics in action on scales that make human concerns seem trivial while simultaneously creating the conditions that make those concerns possible. You're seeing a star that might have already exploded, or might explode tomorrow, or might shine for another 100,000 years. The uncertainty doesn't matter. The outcome is guaranteed. Betelgeuse will end. Something new will begin. The cycle continues.
Beneath a frozen shell thicker than Mount Everest is tall, an ocean larger than all of Earth's seas combined sits in complete darkness. You're probably picturing some distant exoplanet, maybe something thousands of light years away. Wrong. This ocean exists right here in our solar system, orbiting Jupiter every 3.5 days. Europa holds more liquid water than our entire planet, and NASA just launched a $5 billion mission to find out if anything is swimming in it. The numbers don't make sense at first. Europa is slightly smaller than our moon, yet somehow contains double the water volume of Earth. Where did it all come from? More importantly, how does it stay liquid when surface temperatures drop to -220 degrees Celsius? The answer involves one of the most violent gravitational relationships in the solar system, and it's the same force that might be creating the conditions for life to exist right now, roughly 390 million miles from the Sun. Jupiter's gravity doesn't just pull on Europa. It squeezes the moon like a stress ball, over and over, every orbit. The result is tidal heating, a process so intense that it generates enough warmth to maintain a liquid ocean beneath an ice shell that would otherwise be frozen solid. But here's what makes this truly remarkable. The same gravitational torture that keeps the water liquid also cracks the ice above it, creating a dynamic surface that might be exchanging material between the frozen exterior and the hidden ocean below. Scientists discovered something strange when the Galileo spacecraft flew past Europa in the late 1990s. Jupiter's powerful magnetic field, which normally behaves in predictable ways, was getting disrupted near the moon. Not scattered randomly, but in a pattern that suggested something conductive existed beneath the surface. The only substance that made sense was salt water, lots of it, creating its own induced magnetic field through interaction with Jupiter's magnetosphere. This wasn't speculation based on models. It was a direct measurement of something happening right then. The surface told its own story. Europa's ice shows almost no impact craters, which seems impossible for an object that's been orbiting Jupiter for billions of years. The solar system is full of debris, rocks, and ice chunks that should have been pounding this moon relentlessly. Yet Europa's surface is remarkably smooth, the smoothest solid object we've ever found. The only explanation that fits is resurfacing, ice that gets recycled and renewed, erasing old scars. Something beneath that crust is mobile enough to erase geological history. Look closer at Europa's surface and you'll see something that resembles pack ice on Earth's Arctic Ocean, except the pieces are the size of cities. These ice rafts have rotated, shifted, and refrozen in new positions. Some regions show what scientists call chaos terrain, areas where the surface has completely broken apart and reassembled into jumbled landscapes. The ice isn't just sitting there. It's moving, breaking, reforming. Underneath all that activity, an ocean is pushing upward. Then there are the streaks. Long linear features, reddish-brown in color, crisscross Europa's pale surface like veins. For years, scientists debated what these could be. Radiation damage? Mineral deposits? The answer turned out to be salt, specifically magnesium sulfate, left behind when briny water from below erupted onto the surface and evaporated. The ocean isn't just sitting quietly in the dark. It's interacting with the ice shell above it, possibly in ways that could bring nutrients down and waste products up, exactly the kind of exchange that life would need. Water alone doesn't make a habitable world. You need the right chemistry, the right energy sources, the right conditions maintained over geological timescales. Europa's ocean started out wrong for life, too acidic, loaded with sulfates and carbon dioxide. But something changed. Over 4.5 billion years, chemical reactions transformed that harsh environment into something that resembles Earth's oceans. The water became chloride-rich, with dissolved magnesium, sodium, potassium, and chlorine floating in concentrations similar to our seas. The ocean evolved. In 2024, the James Webb Space Telescope detected carbon dioxide on Europa's surface, specifically in a region called Terra Regio. This wasn't just any carbon dioxide. Analysis showed it came from below, from the subsurface ocean, deposited recently in geological terms. Carbon is fundamental to life as we know it. Finding it concentrated in an area where the ice has clearly been disrupted, where material from the ocean appears to have reached the surface, isn't proof of life. But it's exactly what you'd want to see if you were looking for habitable conditions. Then came the ammonia discovery. Scientists re-examining old Galileo data found faint signals of ammonia-bearing compounds near fractures in the ice. Ammonia matters for two reasons. First, it's a nitrogen-bearing molecule, and nitrogen is essential for amino acids, DNA, proteins, all the molecular machinery that biology runs on. Second, ammonia acts as antifreeze, lowering water's freezing point. In Europa's environment, where temperatures hover around freezing even in the ocean, ammonia could create pockets of liquid water that would otherwise freeze solid. Life, if it exists, might be clustering around these ammonia-rich zones. The energy question looms over everything. On Earth, most life ultimately depends on sunlight, either directly through photosynthesis or indirectly through food chains built on photosynthetic organisms. Europa receives 25 times less sunlight than Earth, and none of that reaches the ocean anyway. So where would the energy come from? Tidal heating provides warmth, but life needs chemical energy, electrons moving from one molecule to another, reactions that release usable power. One possibility involves the same process that supports life at hydrothermal vents on Earth's ocean floor. Hot water, heated by geological activity, erupts from cracks in the seafloor, carrying dissolved minerals and chemicals. When this hot, chemically rich water meets cold ocean water, reactions occur spontaneously. Microbes harvest the energy from these reactions, building entire ecosystems in complete darkness. Europa might have similar vents if its seafloor remains geologically active. That's where the debate gets contentious. Recent calculations from Washington University in St. Louis suggest Europa's seafloor might be cold and geologically quiet. The tidal heating that keeps the ocean liquid might not penetrate deep enough to warm the rocky core below. Without volcanic activity, without fracturing and faulting that exposes fresh rock to water, the chemical reactions that microbes could feed on become much harder to sustain. Europa's core likely cooled billions of years ago, and unlike Earth's interior, which still churns with heat from radioactive decay, Europa might not have enough internal energy to power active geology at the seafloor. But other researchers aren't convinced the story ends there. Even without volcanic hydrothermal vents, chemical energy could come from different sources. Radiation from Jupiter constantly bombards Europa's surface, breaking apart water molecules and creating hydrogen peroxide, oxygen, and other oxidants. These chemicals could work their way down through the ice, eventually reaching the ocean. Meanwhile, the seafloor, even if cold, still contains minerals that can react with water through a process called serpentinization. Mix oxidants from above with reduced minerals from below, and you've got potential energy for life. There's another pathway that nobody predicted until recently. The ice shell itself might be producing nutrients. Jupiter's radiation doesn't just create oxidants, it also generates complex organic molecules from simpler compounds on the surface. Normally, these would just accumulate in the ice, chemically isolated from the ocean. But a process called crustal delamination could change that. As denser, salt-rich ice forms near the surface, it could sink through the lighter ice below, carrying those surface nutrients down into the ocean like a conveyor belt. The ice shell wouldn't just be a barrier. It would be a chemical factory and delivery system. The plume question adds another layer of mystery. In 2012, the Hubble Space Telescope captured what appeared to be water vapor erupting from Europa's south polar region, shooting 200 kilometers into space, more than 20 times the height of Mount Everest. If real, these plumes would be a gift to future missions. Instead of drilling through miles of ice, a spacecraft could simply fly through a plume and collect samples of ocean water directly. But proving the plumes exist has been surprisingly difficult. Hubble saw the plume signature once, maybe twice. The Galileo spacecraft might have flown through one in 1997, though that interpretation came decades after the fact from reanalysis of magnetic field data. The James Webb Space Telescope looked for plumes in 2023 and found nothing. Other observations using radio telescopes searched for the molecules that should be present in plumes and came up empty. Either the plumes are rare, episodic events that only happen under specific conditions, or they're much weaker than initially thought, or some of those early detections were misinterpretations of noisy data. The uncertainty doesn't diminish Europa's potential. Plumes or no plumes, the ocean exists. The chemistry appears favorable. The energy sources, while debated, seem sufficient for at least microbial life. What Europa needs now is not more speculation from a distance, but direct investigation up close. That's exactly what NASA launched on October 14, 2024. Europa Clipper is the largest spacecraft NASA has ever built for a planetary mission. With its solar arrays deployed, it stretches over 100 feet, roughly the length of a basketball court. Those enormous solar panels are necessary because Jupiter sits 5 times farther from the Sun than Earth, meaning sunlight there is 25 times weaker. Clipper will spend 6 years traveling 1.8 billion miles, using gravity assists from Mars and Earth to slingshot itself toward Jupiter, arriving in April 2030. The mission design is clever out of necessity. Jupiter's radiation environment is brutal, intense enough to fry electronics in a matter of hours if a spacecraft stayed near Europa continuously. Instead, Clipper will orbit Jupiter itself, swooping past Europa for close flybys, then retreating to safer distances. Over 4 years, it will complete 49 of these flybys, each one bringing it within 16 miles of the surface in some cases. During each pass, the 9 instruments on board will have just minutes to gather data before radiation levels become dangerous again. Those instruments represent the cutting edge of planetary science. Radar will peer through the ice, measuring its thickness and looking for water pockets within the shell. Magnetometers will map Europa's induced magnetic field in far greater detail than Galileo could, potentially revealing the ocean's depth and salinity. Spectrometers will analyze the surface composition, identifying organic molecules, salts, and other chemicals that might have come from below. Cameras will image the surface at resolutions high enough to see features the size of a car. One instrument stands out for its potential to make history. The Surface Dust Analyzer will collect ice grains and dust particles as Clipper flies through the space just above Europa's surface. By analyzing the composition and trajectories of these particles, scientists can determine where they came from and what they're made of. If plumes exist, SUDA will fly right through them, collecting samples of ocean water without the spacecraft ever touching the surface. Laboratory tests have shown something remarkable about instruments like SUDA. Scientists fired ice grains containing tiny amounts of bacterial cell material at a prototype mass spectrometer under conditions simulating a Europa flyby. Even when only 1% of a grain consisted of biological material, the instrument detected it. Clipper carries similar technology. If microbial life exists in Europa's ocean, and if that life gets ejected into space through plumes or surface fractures, and if SUDA happens to sample those particles, the instrument could detect alien biology directly. Nobody on the mission is publicly betting on that outcome. The odds of all those conditions aligning seem astronomical. But the fact that it's even possible, that we've built a spacecraft capable of detecting extraterrestrial life if it's there, represents a profound shift in space exploration. For perspective, we've never attempted anything quite like this before. Every previous mission to detect extraterrestrial life required landing, drilling, or direct sampling. Clipper could find it simply by flying through the right patch of space at the right moment. The margin for error is razor thin, but the payoff would rewrite biology textbooks. Understanding what makes this possible requires examining Europa's surface in detail. When Voyager 1 flew past in 1979, it sent back images that baffled scientists. Europa looked nothing like a typical moon. No impact craters pockmarked the surface. No mountains broke the horizon. Instead, the images showed a smooth, cracked sphere crisscrossed by dark reddish-brown streaks and linear fractures stretching hundreds of miles. Those features told a story. The lack of craters meant the surface was young, geologically speaking, probably only 40 to 90 million years old. On cosmic timescales, that's yesterday. Something was constantly resurfacing Europa, erasing ancient impact scars. The cracks suggested movement, tectonic activity driven not by internal heat alone but by the flexing of the ice shell as Jupiter's gravity squeezed and released the moon every 5 days. The reddish-brown material coating those fractures became a mystery that took decades to solve. Early theories proposed sulfur compounds ejected from volcanic Io and deposited on Europa's surface. But spectroscopic analysis told a different story. The material appeared to be salts, magnesium sulfate primarily, mixed with other minerals. These weren't deposits from space. They came from below. When Europa's ice shell cracks under tidal stress, liquid water from the ocean can seep upward through the fractures. As it reaches the surface, the extreme cold and vacuum of space cause it to evaporate instantly, leaving behind dissolved salts and minerals. Those deposits form the reddish streaks we see. The color comes from radiation damage. Jupiter's intense magnetic field accelerates charged particles to enormous speeds, and when those particles slam into the surface, they break chemical bonds and create new compounds that absorb light differently. This process matters because it means Europa's surface isn't isolated from the ocean below. There's exchange happening, material moving between the deep ocean and the exposed surface. James Webb Space Telescope observations confirmed this in 2023 when astronomers detected carbon dioxide concentrated in a region called Terra Regio, an area of chaos terrain where the surface appears jumbled and disrupted. The carbon dioxide didn't come from space. Isotopic analysis showed it originated in the subsurface ocean and reached the surface recently. Geologically speaking, probably within the last few hundred years. Terra Regio itself reveals how dynamic Europa's surface can be. Chaos terrain forms when warm ice or liquid water rises from below, melting or disrupting the overlying ice shell. The result looks chaotic because it is: blocks of ice tilted at odd angles, fractured and refrozen in new configurations, surface material replaced by fresher ice from deeper layers. These regions offer windows into Europa's interior composition. Then there's the question of plumes. In 2012, Hubble observations suggested water vapor erupting from Europa's south polar region, shooting 125 miles into space before falling back to the surface. The detection was tentative, based on ultraviolet spectroscopy showing what appeared to be hydrogen and oxygen atoms where none should be. Follow-up observations in 2016 provided additional evidence. Researchers analyzing old Galileo data discovered that when the spacecraft flew past Europa in 1997, it might have passed directly through a plume without anyone realizing it at the time. But plumes remain controversial. Later observations with more sensitive instruments found nothing. The James Webb Space Telescope examined Europa thoroughly and detected no active plumes. Radio telescope arrays saw no molecular emissions. Either the earlier detections were misinterpreted, or plumes on Europa are sporadic, erupting only occasionally under specific conditions. Models suggest that if plumes exist, they're most likely when Europa reaches the farthest point in its orbit from Jupiter. At that moment, tidal forces stretch the Moon maximally, potentially opening cracks wide enough for pressurized water to escape. The plumes wouldn't be steady geysers like those on Saturn's moon Enceladus. They'd be brief, localized eruptions that might occur every few orbits or less frequently still. This uncertainty actually increases Clipper's importance. The spacecraft will fly past Europa 49 times over 4 years, sampling different locations under different orbital conditions. If plumes exist, Clipper has excellent odds of encountering one. If they don't exist, or if they're too weak to detect remotely, Clipper will still gather material from Europa's exosphere, the thin envelope of gas and dust particles surrounding the Moon. Every object in space loses material to its surroundings. Solar radiation and Jupiter's magnetospheric particles constantly bombard Europa's surface, breaking molecular bonds and ejecting atoms and molecules into space. Some of that material escapes entirely. Some falls back. And some lingers in a thin cloud around the Moon. SUDA will sample that cloud, collecting particles that originated on the surface or potentially from the ocean itself if exchange processes are active. Recent discoveries add weight to the idea that Europa's surface and ocean communicate regularly. Analysis of old Galileo spectrometer data revealed ammonia-bearing compounds near surface fractures. Ammonia is significant for 2 reasons. First, it's a nitrogen compound, and nitrogen is essential for life as we know it, playing key roles in amino acids, DNA, and proteins. Second, ammonia lowers water's freezing point. An ocean containing dissolved ammonia could remain liquid at temperatures several degrees below 0 Celsius, potentially staying fluid even in regions where pure water would freeze. The ammonia detection came from reanalyzing data that had sat in archives for decades. Scientists applied modern processing techniques to old near-infrared observations and found faint spectral signatures that earlier analysis had missed. The compounds appeared concentrated near fractures and pits, exactly where you'd expect material from below to reach the surface. This pattern keeps repeating. Every time researchers look more carefully at Europa, they find more evidence of an active world. The surface isn't a static ice shell sitting atop a stagnant ocean. It's a dynamic interface where processes from below continuously reshape what we see from above. Cracks form and heal. Chaos terrain disrupts and refrees us. salts and minerals migrate upward. Carbon dioxide deposits in specific locations. Ammonia appears near fractures. All of this paints Europa as a world where the ocean isn't sealed away forever beneath impenetrable ice. It's accessible, at least in principle. Material from the ocean reaches the surface through various processes. That's what makes Clipper's mission feasible without landing or drilling. The moon itself brings samples to the surface. But here's what nobody can answer yet: how much exchange actually occurs? Is it constant and widespread, or rare and localized? Do these processes deliver enough material from the deep ocean to the surface that Clipper can sample it? Or does radiation and weathering destroy organic molecules before they can be detected? These questions matter because they determine what Clipper will find. If exchange is robust and frequent, the spacecraft should detect clear chemical signatures from the ocean, potentially including organic compounds or even biosignatures. If exchange is minimal or if surface conditions destroy delicate molecules quickly, Clipper might see only heavily altered material that doesn't reflect the ocean's true composition. The mission design acknowledges this uncertainty. Clipper's instruments are built to detect a wide range of compounds at very low concentrations. The radar can peer through several miles of ice, potentially detecting liquid water pockets trapped within the shell. Magnetometers will map the induced magnetic field with unprecedented precision, revealing ocean depth and conductivity. Cameras will image the surface at resolutions allowing scientists to identify the freshest terrain, where material from below reached the surface most recently. That last capability could prove crucial. If Clipper can identify very young surface features, areas that formed within the last few years or decades, those locations offer the best chance of finding pristine ocean material before radiation has had time to alter it significantly. Timing matters in ways that aren't immediately obvious. Europa's orbit creates predictable patterns. Every 3-5 days, the moon completes one trip around Jupiter. That orbital period determines when tides peak, when ice flexes most dramatically, and potentially when material from below has the best chance of reaching the surface. Clipper's mission design accounts for this. The spacecraft won't arrive at random moments. Its flybys will be timed to capture Europa at different points in its orbital cycle, sampling conditions when tidal forces are strongest and when they're weakest. This approach should reveal whether surface activity varies with orbital position. But there's a complication. Europa's surface doesn't respond instantly to tidal forces. Ice has memory. When stress builds, cracks don't necessarily open immediately. They might propagate hours or days later. When tidal forces relax, fractures don't seal up right away. Material could continue rising through a crack long after the peak stress has passed. This delayed response makes prediction difficult. Scientists can calculate exactly when tidal forces reach maximum strength. They can't say with certainty when a particular crack will open or when water might breach the surface. Clipper will have to sample the moon repeatedly, building statistical understanding of how surface activity correlates with orbital mechanics. The spacecraft's trajectory creates its own set of constraints. Radiation near Jupiter is intense. Europa orbits deep within Jupiter's magnetosphere, where trapped charged particles create a radiation environment that would destroy unshielded electronics within hours. Clipper can't orbit Europa directly because sustained exposure would kill the spacecraft. Instead, it orbits Jupiter on a highly elliptical path designed to bring it close to Europa periodically while spending most of its time farther out where radiation is less severe. Each close approach lasts only hours. The spacecraft swoops in, gathers data frantically, then retreats to a safer distance. Those brief encounters must be choreographed precisely. Different instruments need different viewing geometries. Cameras want sunlight illuminating the surface at specific angles to reveal topography. Spectrometers need different lighting to identify surface composition. The radar works best when looking straight down through the ice. Mission planners spent years designing a sequence of flybys that balances these competing needs. Some passes prioritize imaging. Others focus on spectroscopy or radar. A few are optimized for sampling material above the surface, flying through regions where plumes might be active. The word "might" appears frequently in mission documentation. Plumes remain one of Europa's biggest mysteries. Hubble spotted what appeared to be water vapor erupting from the surface in 2012. Additional observations in 2014 and 2016 found similar features. These weren't continuous geysers like those on Saturn's moon Enceladus. They appeared intermittently, visible during some observations but absent during others. More recent observations haven't confirmed the plume detections. James Webb Space Telescope looked for plumes in 2023 and found nothing. That doesn't mean the earlier detections were wrong. It means plumes, if they exist, are sporadic and localized. This uncertainty shaped Clipper's design. The spacecraft carries instruments specifically built to detect and analyze plume material. But it doesn't depend on plumes existing. If Europa is actively venting ocean water into space, Clipper will sample it. If plumes are rare or absent, the mission can still accomplish its goals through remote sensing. That flexibility is critical because nobody knows what Clipper will actually encounter. Models predict certain features. Observations suggest others. But Europa has surprised scientists before. Every time new data arrives, it reveals something unexpected. Take chaos terrain. These are regions where the surface appears to have broken apart and were frozen in a jumbled mess. The first chaos terrain identified decades ago looked like enormous ice floes had drifted apart, rotated, and then frozen back together. Scientists proposed that liquid water or warm ice had risen from below, disrupting the solid surface. Higher resolution images complicated that picture. Some chaos regions show features that don't match simple flooding models. Others have characteristics suggesting multiple episodes of disruption. The process creating chaos terrain isn't straightforward melting and refreezing. Something more complex is happening. Carbon dioxide detections added another layer. Terra Regio, one of the largest chaos regions, shows concentrated carbon dioxide deposits. The carbon appears recently placed, geologically speaking. It hasn't been sitting on the surface for millions of years getting degraded by radiation. Something delivered it relatively recently. If that carbon came from the ocean, it means chaos terrain represents active exchange zones. These aren't ancient scars from billions of years ago. They're places where the ocean still communicates with the surface. That makes them prime targets for Clipper. But here's the challenge. Terra Regio covers an area larger than California. Concentrated carbon dioxide means higher levels than surrounding terrain, not a single rich deposit. The spacecraft will fly over this region multiple times, but each pass covers only a narrow swath. Finding the exact spots with the strongest signals requires careful targeting. Clipper's cameras can image at resolutions down to 50 centimeters per pixel during the closest approaches. That's detailed enough to see individual ice blocks and small-scale surface textures. But at that resolution, each image covers only a tiny fraction of Europa's surface. Taking pictures of everything at maximum resolution would require thousands of years. The mission strategy involves multiple resolution tiers. Wide area imaging identifies interesting regions. Moderate resolution imaging characterizes those regions in more detail. High resolution imaging targets the most promising specific features. This hierarchical approach maximizes the science return from limited flyby time. Similar logic applies to spectroscopy. Clipper carries two spectrometers, one working in visible and near-infrared wavelengths, another in thermal infrared. These instruments can identify surface composition, but they need time to gather enough light for clear signatures. The spacecraft can't point both spectrometers at every interesting feature during every flyby. Prioritization becomes necessary. Mission planners have already identified dozens of high-priority targets based on existing data. As Clipper begins returning its own observations, that target list will evolve. Early flybys will reveal new features that demand closer inspection during later passes. This iterative process mirrors how Galileo explored the Jupiter system in the 1990s. That mission's early observations raised questions that later observations addressed. Unexpected findings forced mission planners to revise strategies mid-mission. Clipper will likely follow a similar pattern. One advantage Clipper has is processing power. Galileo's computers had less capability than a modern smartphone. Data had to be compressed heavily before transmission to Earth, losing detail. Clipper's systems can do more onboard processing, making smarter decisions about what data to prioritize for transmission. That matters because communication bandwidth is limited. Europa sits over 600 million kilometers from Earth at Jupiter's closest approach. Radio signals take 33 to 52 minutes to travel one way, depending on planetary positions. The spacecraft can transmit data at rates up to 14 kilobits per second under optimal conditions, far slower than your internet connection. A single high-resolution image from Clipper's cameras might contain hundreds of megabits of data. Transmitting one image could take hours. The spacecraft will generate far more data during each flyby than it can possibly send home in the weeks between encounters. Onboard systems must decide what to transmit first. Engineers program priorities into Clipper's software. Certain measurements take precedence. Data from instruments that can't repeat an observation get transmitted before data from instruments that will have another chance. But the system also allows ground controllers to request specific data sets when something particularly interesting appears. This semi-autonomous approach represents decades of lessons learned from planetary missions. Early spacecraft were essentially remote-controlled robots. Every command came from Earth. Later missions gained more autonomy, able to execute pre-planned sequences without constant ground contact. Clipper sits somewhere between, capable of independent operation but still taking direction from mission control. That balance will be tested during the mission's most critical moments. When Clipper makes its closest approaches to Europa, sometimes skimming just 25 kilometers above the surface, communication delays mean ground controllers can't respond to unexpected situations in real time. The spacecraft must handle problems itself. Radiation poses the biggest threat during these close passes. Europa orbits within Jupiter's intense radiation belts. The spacecraft's electronics sit inside a vault with thick aluminum walls, but radiation still penetrates. Over time, cumulative exposure will degrade systems. Some components will fail eventually. The question is whether they'll last long enough to complete the mission. Engineers designed Clipper's radiation vault using techniques borrowed from nuclear reactor shielding. The walls use interlocking aluminum plates that scatter incoming particles, reducing their energy before they reach sensitive electronics. But aluminum alone can't stop everything. High-energy protons still penetrate. Some will strike memory chips, flipping bits from 0 to 1 or back again. Most bit flips won't matter. They'll occur in unused memory locations or get corrected by error-checking systems. Others will cause software glitches that the spacecraft can recover from by rebooting. A few might prove catastrophic. Mission planners accept this risk because there's no alternative. Clipper must operate in Jupiter's radiation environment to study Europa. The spacecraft carries redundant systems for critical functions. If one computer fails, another takes over. If a sensor stops working, others can partially compensate. This redundancy adds weight and complexity, but it's necessary insurance. The most vulnerable moment comes during each close flyby. Radiation intensity increases dramatically as Clipper drops toward Europa's surface. The spacecraft spends only minutes in the most intense zones, but those minutes accumulate. After 49 flybys, cumulative radiation exposure will reach levels that would kill a human in hours. Some spacecraft systems will certainly fail before the mission ends. The question is which ones and when. What happens if a critical system fails during flyby number 20? Mission planners have contingency protocols. If the main computer crashes, the backup takes control and executes pre-programmed safe mode procedures. The spacecraft points its antenna toward Earth and waits for instructions. Ground controllers assess the situation and upload new commands. This recovery process takes days. The spacecraft misses its next flyby opportunity, but the mission continues. Total mission failure becomes likely only if multiple redundant systems fail simultaneously. Probability calculations suggest this scenario is unlikely but not impossible. Radiation damage is partly random. A particularly energetic particle might strike a critical component in just the wrong way, causing cascading failures. Or gradual degradation might weaken multiple systems until a minor problem triggers total collapse. NASA accepted a calculated risk by approving this mission. Previous Jupiter orbiters, like Juno, stay farther from the planet and experience less radiation. Clipper ventures closer because Europa's science value justifies the danger. But there's no guarantee the spacecraft will complete all 49 planned flybys. Mission success is measured in data returned, not flybys completed. Assuming Clipper survives long enough to complete its primary mission, what comes next? The spacecraft carries enough fuel for potential mission extensions. If key systems remain functional after the planned flybys, NASA might approve additional observations. But Clipper can't stay at Jupiter indefinitely. Eventually, radiation damage will accumulate beyond recovery. When that happens, the spacecraft has one final task. Planetary protection protocols require that Clipper not contaminate Europa with Earth microbes. The spacecraft was assembled in clean rooms, but complete sterilization is impossible. Some hardy bacteria almost certainly survived the construction process, hiding in cracks and crevices. If Clipper crashed into Europa, those microbes might contaminate the subsurface ocean, compromising future searches for indigenous life. To prevent this, mission planners will deliberately crash Clipper into Jupiter or one of the other Galilean moons when the mission ends. The intense heat of atmospheric entry will vaporize any remaining biological contamination. This controlled destruction ensures Europa remains pristine for future missions. It also means Clipper is a one-way mission. The spacecraft will never return to Earth. Understanding what Clipper might find requires understanding what scientists already know about Europa's ocean. Galileo provided the first strong evidence for liquid water beneath the ice. Magnetic field measurements showed that something electrically conductive exists below the surface. In Europa's case, that something is almost certainly a global ocean of salty water. How salty? Estimates suggest Europa's ocean contains dissolved salts at concentrations similar to Earth's oceans, roughly 35 grams per liter. Magnesium sulfate appears particularly abundant based on spectroscopic observations of surface ice. That composition matters because it affects the ocean's chemistry and potential habitability. Recent analysis of old Galileo data revealed ammonia-bearing compounds on Europa's surface, concentrated near fractures where subsurface material might have emerged. Ammonia is chemically interesting for several reasons. It contains nitrogen, an essential element for life as we know it. Ammonia also lowers water's freezing point, potentially allowing liquid to exist at temperatures where pure water would freeze. Where did Europa's ammonia come from? Two possibilities exist. It might have been present in the original material that formed Europa billions of years ago, trapped in ice and rock. Or it might be produced by chemical reactions in the subsurface ocean today. Distinguishing between these scenarios requires understanding Europa's internal chemistry. The ocean's temperature provides another clue about habitability. Tidal heating from Jupiter should keep the ocean slightly above freezing, perhaps near 0 degrees Celsius. But the ocean isn't uniformly cold. Heat flows from Europa's rocky interior toward the ice shell. Temperature gradients create circulation patterns, potentially mixing nutrients throughout the water column. Does Europa's seafloor host hydrothermal vents like those found in Earth's oceans? This question sparked intense debate in early 2026 when researchers published calculations suggesting Europa's tidal heating might be insufficient to drive seafloor volcanism. Their models indicated that Europa's rocky core cooled long ago, leaving the seafloor geologically quiet. On Earth, hydrothermal vents support rich ecosystems independent of sunlight. Microbes harvest chemical energy from compounds dissolved in hot vent fluids. These ecosystems demonstrate that life doesn't require photosynthesis. Chemical energy alone can sustain biological communities. If Europa lacks hydrothermal activity, one potential energy source for life disappears. But the debate isn't settled. Other researchers proposed alternative mechanisms that might support habitability without requiring active volcanism. Radiation from Jupiter bombards Europa's surface, breaking chemical bonds in ice and creating reactive compounds. These radiation-produced chemicals might work their way down into the ocean through a process called crustal delamination. Here's how that might work. Dense, chemically altered ice on Europa's surface becomes heavier than the ice below it. Gravity pulls the dense material downward while lighter ice rises, similar to how Earth's tectonic plates move. This overturning process could transport surface chemicals into the ocean over millions of years, providing nutrients that life might use. Another possibility involves serpentinization, a chemical reaction between water and certain types of rock. When water percolates through olivine-rich rock, it triggers reactions that produce hydrogen gas and other compounds useful to microbes. This process occurs on Earth's seafloor even without volcanic activity. If Europa's rocky interior contains the right minerals, serpentinization might generate chemical energy regardless of whether the seafloor is geologically active. These competing models highlight how much remains unknown about Europa's interior. Clipper's measurements will constrain the possibilities. Magnetic field observations can reveal how thick the ocean is and how conductive it is, providing clues about salt concentration and temperature. Gravity measurements during flybys will reveal density variations in Europa's interior, indicating how the Moon's mass is distributed between ice, water, and rock. The ice shell's thickness matters tremendously for future exploration. If the ice is only a few kilometers thick, a future lander mission might drill through it to reach the ocean directly. If the ice extends 15 or 20 kilometers deep, drilling becomes far more challenging. Clipper's ice-penetrating radar will measure thickness by timing how long radio pulses take to bounce off the ice-ocean boundary. Surface features provide additional clues about ice thickness. Chaos terrain, regions where the surface appears jumbled and disrupted, might form when warm ice rises from below, partially melting the overlying crust. The size and distribution of chaos terrain features can constrain thermal models of the ice shell. One particularly intriguing feature is Terra Regio, a region where recent observations detected carbon dioxide concentrated on the surface. Spectroscopic analysis suggests this carbon dioxide came from the subsurface ocean, not from asteroid impacts. That finding implies relatively recent exchange between the ocean and surface, possibly within the last few million years. If material from the ocean does reach the surface, it might carry chemical signatures of whatever exists in the water below. Organic molecules, if present, would be broken down by radiation quickly. But inorganic compounds would persist longer. Clipper's spectrometers will search for these chemical fingerprints, mapping their distribution across Europa's surface. The mission's most ambitious goal involves detecting life directly, though few scientists expect this outcome. One of Clipper's instruments, SUDA, will analyze tiny ice grains and dust particles as the spacecraft flies through the tenuous cloud of material surrounding Europa. Laboratory tests showed that SUDA can detect bacterial cell material in ice grains even when only 1% of the grain consists of biological matter. If Europa has plumes that occasionally erupt from the surface, SUDA might sample them. Previous observations from Hubble suggested plumes might exist, rising as high as 200 kilometers above the surface. But more recent observations with the James Webb Space Telescope found no evidence of active plumes during the periods observed. This doesn't mean plumes don't exist. It means if they do exist, they're sporadic, weak, or happening in places we haven't looked at the right times. Europa might be venting material only occasionally, perhaps when tidal stresses reach certain thresholds during specific points in its orbit. The Moon experiences maximum tidal flexing when it's farthest from Jupiter, and that's when plumes would most likely occur. Think about trying to photograph lightning. You might point your camera at the sky for hours and see nothing, but that doesn't prove lightning never happens. You need to be looking at the right place at the right time. Europa might work the same way. The surface could be quiet for months or years, then suddenly release a burst of water vapor that lasts only hours before subsiding. Clipper's trajectory was designed with this uncertainty in mind. The spacecraft won't orbit Europa directly. Instead, it will orbit Jupiter and make close flybys of Europa every few weeks. Each flyby will take the spacecraft through different regions above Europa's surface at different times in the Moon's orbital cycle. This approach maximizes the chances of intercepting a plume if one happens to erupt during the mission. The spacecraft's path will carry it as low as 25 kilometers above Europa's surface during some passes. That's remarkably close for a spacecraft traveling at several kilometers per second. At that altitude, SUDA will be positioned to capture ice grains ejected from any active plumes. Even if no dramatic eruptions occur, the instrument should still detect particles knocked off the surface by micrometeorite impacts or sputtered away by Jupiter's intense radiation. Radiation poses both a challenge and an opportunity. Jupiter's magnetic field traps charged particles, creating radiation belts far more intense than Earth's Van Allen belts. Europa orbits within these belts, and the Moon's surface receives a radiation dose that would be lethal to any exposed organism within hours. This radiation constantly bombards the ice, breaking chemical bonds and creating reactive compounds. On one hand, this makes Europa's surface inhospitable. No life could survive exposed on the surface for any meaningful length of time. But on the other hand, The radiation creates oxidants, molecules with extra oxygen atoms that can participate in chemical reactions. These oxidants might accumulate in the ice and eventually make their way down to the ocean through the processes discussed earlier. If they do, they could provide an energy source for life independent of sunlight. Earth's deep ocean vents support ecosystems using chemical energy rather than photosynthesis. Microbes near these vents metabolize hydrogen sulfide and other chemicals released by geological activity. Europa's ocean might host similar communities, except the energy would come from radiation-produced oxidants rather than volcanic chemistry. Testing this hypothesis requires understanding what chemicals actually exist in Europa's ocean. Clipper's infrared spectrometers will map the composition of surface ice in detail, identifying organic molecules, salts, and other compounds. Different materials absorb infrared light at different wavelengths, creating unique spectral signatures. By analyzing these signatures, scientists can determine what's present and in what concentrations. The mission will pay particular attention to regions where subsurface material might have recently reached the surface. Chaos terrain and the areas around large fractures are prime targets. If ocean water has indeed been exposed at these locations, it might still retain some of its original chemistry before radiation alters everything beyond recognition. Temperature measurements add another layer of information. Europa's surface averages around -160 degrees Celsius at the equator and drops to -220 near the poles. But thermal cameras can detect warm spots where heat from below might be reaching the surface more easily. These thermal anomalies could mark places where the ice is thinner or where liquid water has recently been present near the surface. One instrument, reason, will be especially important for understanding ice thickness. This ice-penetrating radar transmits radio pulses downward and measures how long they take to bounce back. Ice and water reflect radio waves differently, so the radar can distinguish between solid ice and liquid water below. By measuring the time delay and signal strength of return pulses, scientists can map the ice shell's thickness across different regions. If the ice varies in thickness significantly, that tells us something important about Europa's interior dynamics. Uniform thickness would suggest a relatively stable ice shell with consistent heat flow from below. Variable thickness implies more complex processes, perhaps convection cells in the ice or localized heating from tidal friction. These variations would affect how easily material can move between the ocean and surface. The radar will also search for liquid water pockets within the ice itself. Some models suggest the ice shell might not be a solid block but rather a mixture of pure ice, slushy layers, and isolated liquid reservoirs. These subsurface lakes, if they exist, could be important intermediate environments between the ocean and the surface. They might be more accessible than the deep ocean while still being protected from surface radiation. Gravity measurements during each flyby will reveal Europa's internal structure more broadly. As Clipper approaches Europa, the Moon's gravity will pull slightly on the spacecraft, changing its velocity in ways that can be measured precisely using radio signals sent back to Earth. By analyzing these velocity changes during multiple flybys, scientists can construct a gravity map of Europa. This map shows where mass is concentrated within the Moon. A thick ice shell and deep ocean would produce one gravity signature. A thin ice shell and shallow ocean would produce another. The measurements will also reveal whether Europa's rocky interior is differentiated, with heavier elements sinking toward the core, or whether it remains a more uniform mixture. Magnetic field measurements will complement the gravity data. Europa's induced magnetic field arises because Jupiter's powerful magnetic field sweeps past the Moon every 11 hours as Jupiter rotates. This changing magnetic field induces electrical currents in any conductive material inside Europa. Salt water conducts electricity far better than ice or rock, so the strength and behavior of Europa's induced magnetic field provides information about the ocean's thickness, depth, and salinity. The magnetometer aboard Clipper will measure Europa's magnetic field during each flyby, building up a detailed picture of how it varies across the surface and over time. These measurements, combined with the gravity and radar data, will constrain models of Europa's interior structure more tightly than ever before. All of these investigations point toward a single overarching question. Does Europa have the conditions necessary for life? Notice that's different from asking whether life actually exists there. Clipper wasn't designed to search for life directly, though SUDA might accidentally detect it if organisms happen to be present in surface ice grains. The mission's goal is more fundamental, determining whether Europa could support life. That requires three things. Liquid water. Check. Europa almost certainly has a global ocean. Chemical building blocks. Probably. We've detected carbon dioxide, salts, and ammonia on the surface, all of which likely came from the ocean. Energy sources. This is the uncertain part. If the seafloor is geologically active, hydrothermal chemistry could provide energy. If not, radiation-produced oxidants might fill that role, assuming they can reach the ocean in sufficient quantities. Clipper will address each of these requirements. The mission will confirm the ocean's existence beyond any doubt, measure its properties, and determine its composition. It will assess how much exchange occurs between the ocean and surface. It will search for evidence of recent geological activity. And it will evaluate whether the moon's internal heat budget allows for seafloor processes that could generate chemical energy. The spacecraft will also document Europa's geology in unprecedented detail. High-resolution cameras will image the surface at scales of less than 1 meter per pixel in selected areas, revealing small-scale features that might indicate recent activity. Wider area images at lower resolution will provide context, showing how different terrain types relate to one another. Scientists will use these images to construct detailed maps of Europa's surface, identifying regions of interest for potential future missions. If plumes are detected, their source locations will be prime targets. If certain areas show strong evidence for thin ice or recent water exposure, those become candidates for a future lander or even a mission that could penetrate the ice. But all of that comes after Clipper arrives in April 2030. Between now and then, the spacecraft must survive a journey of nearly 3 billion kilometers through deep space. It must execute a precisely timed gravity assist at Earth in December 2026, using our planet's gravity to accelerate toward Jupiter. And it must withstand Jupiter's intense radiation environment once it arrives, a challenge that required extensive shielding and radiation-hardened electronics. The mission engineers designed Clipper's trajectory specifically to minimize radiation exposure. Instead of orbiting Europa directly, which would subject the spacecraft to constant bombardment, Clipper orbits Jupiter in a highly elliptical path. Each orbit brings it close to Europa for a brief flyby, then carries it far away from Jupiter's most intense radiation belts. This approach allows the spacecraft to accumulate the necessary science data while spending minimal time in the harshest environment. Even so, the radiation dose adds up. Jupiter's magnetic field traps charged particles, creating radiation belts far more intense than anything near Earth. By the end of its mission, Clipper will have received a total radiation dose equivalent to several million chest X-rays. That would kill a human instantly, but the spacecraft was built to withstand it. Critical electronics sit inside a thick-walled vault made of titanium and aluminum. Cables are specially shielded. Software can detect and correct errors caused by radiation hitting computer chips. Every component was tested to ensure it could survive. But there's another challenge nobody talks about much. the spacecraft has to work autonomously for long periods. Radio signals take nearly an hour to travel between Jupiter and Earth, so real-time control is impossible. If something goes wrong during a flyby, the spacecraft must recognize the problem and fix it before ground controllers even know there's an issue. That requires sophisticated onboard systems capable of monitoring spacecraft health, diagnosing problems, and executing contingency plans without human intervention. NASA tested these systems extensively before launch. Engineers simulated every failure mode they could imagine, then programmed responses into Clipper's software. The spacecraft knows how to save itself if it detects anomalies. It can switch to backup systems, adjust its orientation, or abort a flyby if necessary. This autonomy is essential because each flyby happens fast. At closest approach, Clipper races past Europa at several kilometers per second. The entire science observation period lasts only a few hours. Miss that window and you have to wait weeks for the next opportunity. The 49 flybys are carefully choreographed. Each one targets a different region of Europa's surface, gradually building up global coverage. Sun passes focus on the leading hemisphere, the side that faces forward as Europa orbits Jupiter. Others examine the trailing hemisphere. Several flybys are dedicated to high-priority targets like Terra Regio, where carbon dioxide and salts indicate recent exchange with the subsurface ocean. The lowest altitude passes, skimming just 25 kilometers above the surface, are saved for later in the mission after engineers gain confidence in the spacecraft's performance. What happens after Clipper completes its mission in 2034? The spacecraft won't have enough fuel left to return to Earth, and leaving it in orbit around Jupiter poses a contamination risk. There's a small chance, probably very small, that microbes from Earth could have hitched a ride despite NASA's strict sterilization procedures. If Clipper eventually crashes into Europa, those microbes might contaminate the subsurface ocean. That would be an ethical disaster, potentially compromising one of the solar system's best chances for finding life. So NASA plans to deliberately crash Clipper into Jupiter or one of the other Galilean moons at the end of its mission. This is called planetary protection. The Galileo spacecraft met the same fate in 2003, plunging into Jupiter's atmosphere to prevent any possibility of contaminating Europa. Clipper will likely follow suit. The exact disposal method depends on what orbit the spacecraft is in when it runs out of fuel, but the principle remains the same. We don't contaminate worlds where life might exist. Assuming Clipper succeeds, what comes next? The mission's findings will shape future exploration strategies. If the ocean appears highly promising, with strong evidence for recent geological activity and abundant chemical nutrients, NASA and other space agencies will likely prioritize a Europa lander. Such a mission would face enormous technical challenges. Landing on Europa's icy surface is difficult enough, but the real goal would be to access the subsurface ocean. That means drilling through kilometers of ice, an engineering problem we haven't solved even on Earth in comparable environments. Antarctica's Lake Vostok sits beneath nearly 4 kilometers of ice. After decades of effort, Russian scientists finally reached it in 2012, but the drilling process was slow, difficult, and raised contamination concerns. Europa's ice is colder, harder, and possibly thicker. It exists in a vacuum with no atmosphere to moderate temperature swings. And any mission there must be completely autonomous because of the communication delay. You can't have a human geologist making decisions in real time. Some mission concepts bypass the drilling problem entirely. Instead of landing, they would fly through Europa's plumes, if those plumes actually exist and can be reliably detected. A spacecraft passing through a plume could sample ocean water directly, analyzing it for signs of life without ever touching the surface. But that approach depends on plumes being active when the spacecraft arrives. Current evidence suggests they're intermittent at best, possibly erupting only when Europa is at certain points in its orbit. Timing a mission to coincide with a plume eruption is risky. Another possibility is an ice-penetrating probe. This concept envisions a nuclear-powered device that melts its way down through the ice, trailing a communication cable behind it. Once it reaches the ocean, it could deploy sensors to measure water properties, search for organic molecules, or even look for moving organisms. This sounds like science fiction, but NASA has funded preliminary studies. The technology isn't ready yet, but it might be within a few decades. All of these future missions depend on what Clipper discovers. If the spacecraft finds that Europa's ice is thicker than expected, or that the ocean has less interaction with the surface than hoped, enthusiasm for a follow-up mission might cool. If it finds strong evidence for thin ice, active plumes, and rich chemical exchange, the case for a lander becomes compelling. That's why Clipper's reconnaissance is so crucial. It sets priorities for everything that follows. There's also the broader question of what Europa tells us about life in the universe. If we find even simple microbes in Europa's ocean, that discovery fundamentally changes our understanding of biology's prevalence. Life on Earth might not be a unique miracle, but rather an inevitable consequence of liquid water and chemical energy. And if it happened twice in one solar system, it probably happened countless times across the galaxy. On the other hand, if Europa has all the right ingredients but remains lifeless, that suggests life is rarer than we thought. Either answer matters. Europa represents something profound in human exploration. For most of history, we could only wonder about other worlds. Now we build machines capable of traveling billions of kilometers to investigate them. We design instruments sensitive enough to detect molecules in ice grains. We write software that lets spacecraft think for themselves. And we do all of this driven by a single question that humans have asked since we first looked up at the stars. Are we alone? The answer might be waiting beneath Europa's ice. In April 2030, Clipper will begin its search. The spacecraft will spend 4 years mapping an alien ocean world, measuring its properties, testing its chemistry, and evaluating its potential to support life. We won't know what it finds until it looks. But either way, what we learn will reshape how we understand our place in the universe. Because if life can exist in the cold, dark waters of a moon orbiting Jupiter, then the cosmos is far stranger and more alive than we ever imagined. That's worth the journey. The spacecraft carrying humanity's best instruments for detecting alien life is already on its way. By the time you're watching this, Clipper has left Mars behind and is accelerating toward its December 2026 Earth flyby. That gravity assist will slingshot it toward Jupiter at speeds we can barely comprehend. Every second brings us closer to answers we've been seeking for generations. Think about the audacity of this mission. We built a spacecraft the size of a basketball court, packed it with instruments sensitive enough to detect a single % of bacterial material in a microscopic ice grain, wrapped its electronics in radiation shielding thick enough to survive Jupiter's particle bombardment, and launched it on a 6-year journey to a moon where temperatures would freeze your breath solid in seconds. All to answer one question: could something be alive in Europa's ocean? The weird part is we might already know the answer before Clipper arrives. Not from the spacecraft, but from the data it's designed to collect. If Europa's plumes turn out to be real and active, and if one of them happens to erupt while a ground-based telescope is watching during the 2020s, we might detect organic molecules or chemical signatures that suggest biology. That would fundamentally change Clipper's mission from reconnaissance to confirmation. But here's what makes Europa different from every other place we've explored. Mars might have had life billions of years ago. Venus might have been habitable before its atmosphere went rogue. Europa potentially has life right now, swimming in an ocean that has existed for most of solar system history. If organisms evolved there, they've had 4 billion years to adapt, diversify, and spread through a water volume twice as large as Earth's oceans. That's not a marginal environment clinging to existence. That's a world. The implications split in two directions depending on what Clipper finds. Discovery of life, even microbial life, would prove biology isn't unique to Earth. It would suggest that given liquid water, chemical building blocks, and energy, life emerges almost inevitably. That would make the universe less lonely but more mysterious. Because if life is common, why haven't we detected any signs of intelligence? Either technological civilizations are rare, or they don't last long, or they exist but remain invisible to our searches. None of those options is comforting. The alternative might be worse. If Europa has everything life needs but remains sterile, that suggests something is missing from our understanding. Maybe the origin of life requires conditions we haven't identified yet. Maybe the jump from chemistry to biology is so improbable that even 4 billion years in a massive ocean isn't enough time. If Europa is dead, it raises uncomfortable questions about how rare Earth's biosphere might be. Either way, Clipper's data will reshape astrobiology. The mission will establish whether Europa's ocean is habitable in practice, not just in theory. It will measure the ice thickness, map the chemistry, evaluate the energy budget, and determine how much exchange occurs between the ocean and surface. Those measurements will tell us whether a future mission could realistically access the ocean and what it might find there. The engineering challenges facing any follow-up mission are staggering. Drilling through kilometers of ice in a vacuum at -200 degrees with no human supervision isn't something we know how to do yet. But neither was landing on Mars, or flying a helicopter in its thin atmosphere, or catching a rocket booster with mechanical arms. We solve problems like this by trying, failing, learning, and trying again. Europa might require decades of development before we can touch its ocean. But the fact that we're seriously planning for it means we've crossed a threshold as a species. There's something almost absurd about the whole endeavor. Humans, creatures that evolved to survive in Earth's oxygen-rich atmosphere at comfortable temperatures, spending billions of dollars to investigate whether microbes might exist in a freezing ocean beneath 20 kilometers of ice, 390 million miles from home. We can't eat anything we find there. We can't colonize it. We can't extract resources from it. The entire mission serves pure curiosity, our need to know what's out there. That might be the most human thing we do. Every civilization that has ever existed has looked at its boundaries and wondered what lies beyond. We crossed oceans not knowing what was on the other side. We climbed mountains because they were there. We went to the moon partly to prove we could. Now we're sending robots to investigate an alien ocean because we need to know if we're alone. The question drives us in ways that practical concerns never could. The timeline stretches ahead. Clipper arrives at Jupiter in April 2030. First science operations begin shortly after. The 49 flybys will take 4 years to complete, ending in 2034. Data analysis will continue for years beyond that as scientists work through the measurements, compare them to models, and piece together a comprehensive picture of Europa's interior. We might not have definitive answers about habitability until the late 2030s. And if those answers justify a follow-up mission, that spacecraft won't launch until the 2040s at the earliest. Most people reading this will live to see the results. That's remarkable when you think about it. Previous generations could only speculate about other worlds. This generation will know whether at least one of them could support life. Your children might grow up in a world where the existence of extraterrestrial biology is an established fact, not a hypothesis. The implications of that shift are difficult to grasp. But we're not there yet. Right now, Europa remains a mystery. Its ocean stays hidden beneath ice that has never felt sunlight. Whatever exists down there, if anything, has never been observed by human eyes or instruments. Clipper will change that. In April 2030, when the spacecraft makes its first close pass, we'll begin seeing Europa as it actually is, not as we imagine it might be. Some of our assumptions will prove correct. Others won't. The moon will surprise us because nature always does. What we're witnessing is the beginning of a new phase in human exploration. For centuries, we explored Earth's surface, mapping continents and oceans. For decades, we've been exploring space, sending probes to planets and moons. Now we're starting to explore the interiors of those worlds, investigating oceans and atmospheres and geological processes happening beneath surfaces we can barely see. Europa is the first target of this deeper investigation, but it won't be the last. Saturn's moon Enceladus also has a subsurface ocean and active plumes. So does Saturn's largest moon Titan, though its ocean is probably too cold and too far beneath the surface to access easily. Other candidates exist throughout the outer solar system. The search for life is expanding from a question about Earth's uniqueness to a systematic survey of potentially habitable environments across multiple worlds. This is the future of astrobiology, not waiting for signals from distant civilizations, but investigating the places where life might exist right now in our cosmic neighborhood. Europa leads that investigation because we can actually get there with current technology and because the evidence for its ocean is so strong. But it's part of a larger project that will occupy humanity for generations. When Clipper completes its mission in 2034, it will have generated more data about Europa than all previous missions combined. That data will feed into models, simulations, and predictions about what the ocean contains. It will guide the design of future missions. It will answer old questions and raise new ones. And somewhere in those terabytes of measurements might be a signature that changes everything, a chemical anomaly that can't be explained by geology alone, a pattern that suggests something other than sterile water beneath the ice. Or maybe not. Maybe Europa will turn out to be a magnificent but lifeless ocean, a reminder that water and chemistry alone aren't sufficient. We'll learn something profound either way. That's the nature of genuine exploration. You don't know what you'll find until you look, and the act of looking transforms your understanding regardless of the outcome. Europa forces us to confront possibilities we can barely articulate, questions about the nature of life and its distribution in a universe that we're only beginning to learn how to ask properly. The spacecraft flying toward Jupiter right now carries more than instruments and computers. It carries our best attempt to answer whether Earth's biology is an isolated accident or part of a broader pattern. In 4 years, when Clipper begins its flybys, we'll start getting answers. Those answers will shape how we think about our place in the universe for the rest of human history. Because knowing whether we're alone changes everything about how we understand ourselves and our future. Europa might tell us that story. We just have to wait for the spacecraft to arrive and start reading what's written in the ice. Something's out there. Something massive, something cold, something so distant it takes 10,000 to 20,000 years to complete a single orbit around our sun. We haven't seen it. We can't photograph it. Yet the mathematical evidence suggests it's real, and it's 10 times more massive than Earth. This is Planet 9, a world that shouldn't exist according to everything we thought we knew about our solar system. But the math keeps pointing to the same conclusion. There's a giant lurking in the darkness beyond Neptune. In 2016, two astronomers at Caltech made an announcement that sent shockwaves through the scientific community. Konstantin Batygin and Mike Brown claimed they'd found evidence for a ninth planet, not through direct observation, but through pure mathematics and computer simulations. The prediction was bold. The implications were staggering. And the astronomical world split into believers and skeptics almost immediately. Here's what makes this different from every other "maybe there's something out there" claim. The evidence doesn't come from a single strange observation or a blurry photograph. It comes from watching how dozens of distant objects move, objects so far away they barely reflect any sunlight, objects that take thousands of years to complete their journeys around the sun. These frozen worlds are telling us something. Their orbits are aligned in ways that shouldn't be possible unless something massive is pulling on them. 6 of the most distant objects we've ever discovered all point in the same direction. They tilt downward from the plane of our solar system at nearly identical angles. The odds of this happening by random chance? About 1 in 500. Those aren't lottery odds. Those are "something's definitely going on here" odds. But let's back up. How do you lose a planet? The story begins much earlier than 2016. It starts over a century ago with an astronomer named Percival Lowell. In 1915, Lowell became convinced that something was disturbing the orbit of Uranus. He called this hypothetical object Planet X, where X stood for the unknown, not for the Roman numeral 10. Lowell died in 1916, never finding his mysterious planet. But his search continued at the observatory he founded in Flagstaff, Arizona. In 1930, a young astronomer named Clyde Tombaugh discovered Pluto. For decades, astronomers believed they'd found Lowell's Planet X. Pluto was celebrated as the 9th planet, the final member of our solar system family. Except there was a problem. Pluto was far too small to cause the gravitational effects Lowell had predicted. It turned out those perturbations to Uranus's orbit were measurement errors. They weren't real. The search for Planet X was based on a mistake. Pluto's story took another turn in 2006. The International Astronomical Union redefined what it means to be a planet. Pluto didn't make the cut. It became a dwarf planet instead, one of many similar objects in the Kuiper Belt. The man who provided much of the evidence leading to Pluto's demotion? Mike Brown. He even wrote a book titled "How I Killed Pluto and Why It Had It Coming." The irony that Brown might now discover a true 9th planet hasn't been lost on anyone. So if the old Planet X was a myth based on bad data, why should we believe in this new Planet 9? Because the evidence is completely different. This isn't about measurement errors or wishful thinking. It's about patterns that emerge when you look at the most distant objects in our solar system, objects that exist in a realm we barely understand. The outer solar system is strange. Beyond Neptune, at distances greater than 250 astronomical units, that's 250 times farther from the Sun than Earth, you enter a region where sunlight is so faint it's almost meaningless. Out here, objects move in slow motion, taking millennia to complete their orbits. We've discovered dozens of these extreme trans-Neptunian objects, and they're revealing something unexpected. In 2014, astronomers Scott Shepard and Chadwick Trujillo noticed something odd. A handful of these distant objects had orbits that clustered together. They weren't randomly scattered across the sky like you'd expect. They were grouped, almost shepherded, as if something massive was organizing them. Shepard and Trujillo suggested an unseen planet might be responsible, something several times larger than Earth and more than 200 times our planet's distance from the Sun. Badigian and Brown heard about this clustering and decided to investigate. What they found went far beyond the initial observations. When they ran computer simulations of the outer solar system, trying to recreate the orbits of these distant objects, they kept hitting the same conclusion. Without a massive planet out there, the simulations couldn't reproduce what we actually observe. But add a planet with specific characteristics, about 10 Earth masses in a highly elongated orbit, and suddenly everything clicked into place. The simulations matched reality. The alignment of these objects isn't subtle. 6 of them point in the same direction when they make their closest approach to the Sun. They're tilted at about 30 degrees downward from the plane where the other planets orbit. This kind of alignment doesn't happen naturally in a chaotic system. Something organized it. Something massive enough to gravitationally dominate a region of space larger than any known planet. There's more. Badigian and Brown's simulations predicted that a second group of objects should exist, forced into positions at right angles to Planet 9 and into orbits perpendicular to the solar system's plane. 5 known objects fit this prediction exactly. The math predicted they should be there before anyone found them. In April 2024, Badigian and Brown published new evidence. They focused on a different population of trans-Neptunian objects, ones with orbits that reach inside Neptune's orbit. These objects spread inward from Neptune in a pattern that matches Planet 9's predicted gravitational influence precisely. Without Planet 9 in the simulations, this pattern doesn't appear. With it, the match is almost perfect. The study was statistically significant at about a 5 sigma confidence level, which in scientific terms means the probability of this being a coincidence is vanishingly small. Mike Brown stated it plainly. I think it is very unlikely that Planet 9 does not exist. There are currently no other explanations for the effects that we see. If Planet 9 isn't real, astronomers would need 5 or 6 separate unknown explanations for all the oddities they're observing in the outer solar system. That's possible, but it violates a principle scientists hold dear. The simplest explanation that accounts for all the evidence is usually correct. But here's what makes this search so difficult. Planet 9, if it exists, is unimaginably far away. The most recent estimates place it around 290 astronomical units from the Sun on average. To put that in perspective, Neptune orbits at about 30 astronomical units. Pluto's average distance is around 40 astronomical units. Planet 9 is 7 to 10 times farther out than that. At such distances, sunlight is incredibly weak. The planet would reflect almost no visible light. It would be extraordinarily dim, with an apparent magnitude somewhere around 21 or 22. That's roughly 25,000 times fainter than the faintest stars you can see with your naked eye. Even with the world's most powerful telescopes, finding Planet 9 is like searching for a specific grain of sand on a beach at midnight. You know roughly which beach to search, but the grain could be anywhere along miles of coastline. Previous searches have eliminated about 78% of the possible sky positions. That sounds impressive until you realize 22% of an already enormous search area is still enormous. The planet moves slowly, incredibly slowly. At its estimated distance, it would take between 10,000 and 20,000 years to complete one orbit. In the time since humans built the pyramids, Planet 9 has moved only a fraction of its total path. This makes it harder to detect because astronomers typically find distant objects by watching them move against the background stars. If something barely moves over months or years of observation, it can easily be mistaken for a distant star or galaxy. There's another complication. The planet's orbit is highly elongated. Sometimes it might be relatively closer to the Sun, perhaps 200 to 300 astronomical units away. At other times, it could be 600 astronomical units out or even farther. According to Kepler's laws of planetary motion, objects move more slowly when they're farther from the Sun. Statistically, Planet 9 is more likely to be near the far end of its orbit right now, where it's moving slowest and is dimmest. That's the worst possible scenario for detection. Yet despite these challenges, astronomers are confident they'll find it soon. The reason for this confidence lies not in traditional telescopes, but in a revolutionary new observatory that's about to begin operations. The Vera C. Rubin Observatory in Chile represents a complete game-changer for astronomy. This facility, a joint project of the National Science Foundation and the Department of Energy, has been under construction for years. It's equipped with the largest digital camera ever built for astronomy, and it's designed to do something no other telescope can match. Starting in 2025, it will photograph nearly the entire southern sky every few nights, creating an ongoing movie of the cosmos. Mike Brown calls it the perfect tool for finding Planet 9. If you were to hand me a big wad of cash and say, "Go build a telescope to either find this Planet 9 or find the best evidence possible for Planet 9, I would probably go and build the Vera Rubin Observatory. The observatory will capture images of roughly 10 billion objects over the next decade. Computer systems will constantly compare new images to previous ones, flagging anything that changes or moves. If Planet 9 is in the southern sky, Rubin will almost certainly detect it. Scott Shepard estimates the observatory has a 70 to 80% chance of finding the planet if it's real. But what if it's not in the southern sky? What if it's in the northern hemisphere, outside Rubin's view? That's where other telescopes come in. The Subaru telescope in Hawaii, with its combination of large aperture and wide field of view, is conducting its own search. Two teams of astronomers, Badijan and Brown along with Trujillo and Shepard, are working together, expecting the combined search to take up to 5 years. 5 years might seem like a long time, but in astronomical terms, it's remarkably quick. We're talking about finding an object that's been hiding for 4.6 billion years, an object that's never been seen by human eyes, an object that challenges everything we thought we understood about how our solar system formed. Because that's the real question lurking behind all of this. If Planet 9 exists, how did it get there? A planet that massive, that far from the Sun, shouldn't exist according to standard models of planetary formation. The solar system's outer regions didn't have enough material to build something that large at such distances. So where did it come from? The answer might be even stranger than the planet itself. The leading theory suggests our solar system once had 5 giant planets, not 4. Jupiter, Saturn, Uranus, Neptune, and a fifth world roughly the size of Uranus or Neptune. During the chaotic early days of the solar system, these giants were packed much closer together than they are now. They orbited in a dense disk of planetesimals, the leftover building blocks from planetary formation. Then, over millions of years, gravitational interactions between the giant planets and these smaller objects caused the planets to migrate. Jupiter moved slightly inward. The others drifted outward. This migration wasn't smooth or gentle. It was violent, chaotic, a cosmic game of pinball played with planet-sized objects. At some point during this upheaval, the fifth giant planet got too close to Jupiter. Jupiter, the most massive planet in the solar system with more than twice the mass of all other planets combined, acted like a gravitational slingshot. It flung the fifth giant outward with tremendous force. Most computer simulations of this scenario show the ejected planet being thrown completely out of the solar system, lost forever to interstellar space. But in a small percentage of simulations, something different happens. The ejected planet doesn't quite reach escape velocity. Instead, it settles into a distant, highly elliptical orbit, exactly the kind of orbit predicted for Planet 9. This scenario is called the Nice model, named after the French city where it was developed. The Nice model has become widely accepted because it explains several puzzling features of the solar system. It accounts for the late heavy bombardment, a period roughly 4 billion years ago when the inner solar system was pummeled by asteroids and comets. It explains why Neptune's orbit is slightly eccentric. It clarifies the structure of the Kuiper belt. And now, it might explain Planet 9. The ejection hypothesis solves a fundamental problem. You can't build a planet as massive as Planet 9 at such extreme distances from the Sun. There simply wasn't enough material out there. The solar nebula, the disk of gas and dust from which planets formed, was too thin and spread out at those distances. Planet formation requires material to collide and stick together, and that process becomes exponentially slower when particles are spread across vast expanses of space. But if Planet 9 formed closer to the Sun, in the region where Uranus and Neptune formed, and was then ejected outward, suddenly its existence makes perfect sense. The physical characteristics match this origin story remarkably well. Planet 9 is predicted to have a mass of about 5 Earth masses, similar to Uranus and Neptune when you account for their thick atmospheres. It would be gaseous, an ice giant with a rocky core surrounded by water, methane, and ammonia ices, all wrapped in a hydrogen and helium envelope. These are exactly the characteristics you'd expect from a planet that formed in the outer solar system 6 billion years ago. But there's another possibility, one that's even more extraordinary. What if Planet 9 didn't form in our solar system at all? The Sun wasn't born in isolation. It formed in a stellar nursery, a dense cluster containing thousands of young stars packed into a relatively small volume of space. In such environments, close encounters between stars are common. During the first few 100 million years of the solar system's existence, another star could have passed within a few hundred astronomical units of the Sun. If that star had its own planetary system, and if one of its planets happened to be in just the right position during the encounter, the Sun's gravity could have captured it. This capture scenario would make Planet 9 an exoplanet, a planet that formed around another star. If confirmed, it would be the first exoplanet discovered within our own solar system, a world that spent billions of years orbiting a different sun before becoming part of ours. The odds of such a capture are low, but they're not zero. Computer simulations show that in dense stellar nurseries, planetary capture events do occur, though rarely. The capture hypothesis has an appealing elegance. It would explain why Planet 9's orbit is so different from the other planets, tilted relative to the solar system's plane and highly elongated. A captured planet wouldn't follow the orderly, nearly circular orbits of planets that formed in place. Its orbit would bear the fingerprints of a violent gravitational encounter, exactly what we see predicted for Planet 9. But here's what makes this puzzle even more complex. There's a third option that astronomers are seriously considering. What if there isn't just one Planet 9, but multiple smaller planets? What if instead of a single 5 Earth mass world, there are 2 or 3 planets, each a few Earth masses, scattered across the outer solar system? This multi-planet scenario could produce similar gravitational effects on trans-Neptunian objects while being harder to detect because each individual planet would be smaller and dimmer. Some researchers have proposed an even more exotic alternative involving a disk of small icy bodies with a combined mass of 10 Earth masses, spread across the outer solar system. This disk, if it exists, could gravitationally shepherd trans-Neptunian objects in ways that mimic the effects of a single large planet. The challenge with this disk hypothesis is that such a structure should be detectable through its infrared emission, and so far, surveys haven't found it. Then there are the truly speculative ideas. Could Planet 9 be a primordial black hole, a microscopic black hole formed in the early universe? Such an object would have the right mass to produce the observed gravitational effects but would be nearly impossible to detect directly. Or could it be a concentration of dark matter, the mysterious substance that makes up most of the universe's mass but doesn't interact with light? These exotic explanations remain on the fringes of scientific consideration because they require invoking phenomena we've never directly observed in our solar system. Occam's razor suggests the simpler explanation, a planet, is more likely. But the fact that astronomers are even considering such alternatives demonstrates how profoundly puzzling this situation is. What makes the formation question so crucial is this: the answer would tell us whether our solar system is typical or unusual. If Planet 9 is an ejected fifth giant, it suggests that planetary systems commonly lose planets during their chaotic youth. Astronomers have found evidence of ejected planets around other stars, so this wouldn't be unprecedented. It would mean that for every planetary system we observe, there might be one or more invisible planets lurking in the darkness beyond what we can easily detect. If Planet 9 is a captured exoplanet, it would suggest that stellar nurseries are dynamic enough to exchange planets between forming systems. This would have profound implications for understanding planetary demographics in the galaxy. How many stars captured planets? How many lost them? The architecture of planetary systems might be far more fluid and dynamic than we've imagined. Recent refinements to the Planet 9 hypothesis have actually made the formation question more pressing. A 2025 study using an expanded sample of 51 extreme trans-Neptunian objects proposed that Planet 9's orbit might be smaller than previously thought, with a semi-major axis of around 290 astronomical units rather than 400 to 600. If true, this would place Planet 9 closer to the Sun, making it brighter and easier to find, but it also changes the dynamical requirements for how the planet reached that orbit. The nice model simulations that showed a fifth giant being ejected to Planet 9's orbit were based on the earlier, larger orbital estimates. With a smaller orbit, the ejection dynamics would need to be recalculated. Could Jupiter fling a planet to 290 astronomical units without ejecting it entirely from the solar system? The answer depends on precise details of the ejection event, the angle, the velocity, the gravitational assists from other planets. What we're witnessing is science in action, the process of refining hypotheses as new data emerges. Each new trans-Neptunian object discovered adds another constraint to the models. Each failed search narrows the possible locations. The picture is becoming clearer, but the fundamental mystery remains. Somewhere out there, moving slowly through the darkness, there might be a world that holds the key to understanding our solar system's violent past. And the clock is ticking. Within the next few years, the Vera Rubin Observatory will either find Planet 9 or rule out large portions of the remaining search space. We're approaching a definitive answer to one of astronomy's biggest questions. But before we get there, we need to understand what finding Planet 9 would actually mean for the rest of the solar system, because its gravitational influence extends far beyond just those handful of trans-Neptunian objects. Planet 9's gravitational reach doesn't stop at those extreme trans-Neptunian objects. It extends throughout the outer solar system in ways that are subtle but detectable. Jupiter family comets, those periodic visitors that swing through the inner solar system every few years, would show different orbital tilts if Planet 9 exists. Computer simulations predict their inclination distribution should be broader, more spread out, than what we'd see in a Planet 9-free solar system. And when astronomers look at the actual data, that's exactly what they find. The distribution matches the prediction. Then there's the Oort cloud, that vast spherical shell of icy bodies surrounding the solar system at distances up to 100,000 astronomical units. Planet 9 would have affected how many objects got captured into the Oort cloud during the solar system's formation. Simulations show that with Planet 9 in its predicted orbit billions of years ago, fewer objects would have been flung into the Oort cloud. The gravitational stirring from a massive planet in the outer reaches would have ejected more objects entirely from the solar system rather than parking them in distant orbits. This prediction is harder to test directly since we can't count Oort cloud objects with any precision, but it represents another testable consequence of the hypothesis. What about the giant planets themselves? Would Planet 9 have left fingerprints on Jupiter, Saturn, Uranus, and Neptune? The answer depends on when Planet 9 reached its current orbit. If it was ejected early in the solar system's history, during the period of planetary migration described by the NICE model, then its ejection would have been part of the same chaotic reshuffling that moved all the giant planets. In that case, Planet 9's influence is already baked into the current orbital configuration we observe. The planets are where they are partly because of the gravitational chaos that sent Planet 9 outward. But there's a more direct effect. Planet 9's orbit is tilted about 6 degrees relative to the plane where the 8 known planets orbit. That tilt would exert a slow, subtle torque on the entire solar system over billions of years. Think of it like a spinning top that's slightly off balance. Over time, that imbalance affects the whole system's orientation in space. Calculations suggest that Planet 9 could explain a long-standing puzzle: why the Sun's equator is tilted about 6 degrees relative to the planetary orbital plane. The gravitational influence of a distant, tilted Planet 9, acting over 4.5 billion years, could have gradually torqued the entire inner solar system, including the Sun's rotation axis, into its current configuration. This prediction caught many astronomers by surprise when it was first published. It's one thing to affect distant icy bodies. It's another to tilt the Sun itself. But the math checks out. A 5 Earth-mass planet at 300 to 400 astronomical units, tilted at the right angle, applying gentle but persistent gravitational torque over geological timescales, could absolutely accomplish this feat. And suddenly Planet 9 isn't just explaining weird orbits at the edge of the solar system. It's explaining a fundamental property of our planetary system that's been visible since humans first pointed telescopes at the Sun. Yet another population shows Planet 9's fingerprints: high-inclination trans-Neptunian objects. These are objects whose orbits are tilted steeply relative to the plane where planets orbit, sometimes by 90 degrees or more. They're rare, which makes sense. Most of the solar system's material started in a flat disk and should stay relatively flat. But we found several objects with these extreme tilts, and they need an explanation. Planet 9's gravitational influence could pump up the inclinations of certain objects over millions of years through a process called causative oscillations. This mechanism causes orbits to trade eccentricity for inclination in a periodic cycle. An object might start with a moderately elliptical orbit in the plane, then gradually become more circular but more tilted, then swing back. With Planet 9's gravity driving these oscillations, some objects could get kicked into very high inclinations and stay there. 5 known objects fit this prediction with remarkable precision. They're positioned at roughly 90-degree angles to Planet 9's predicted location, and their orbits are perpendicular to the solar system's plane. When Badigian and Brown first ran their simulations, these objects appeared naturally in the results. The model predicted they should exist before anyone had specifically looked for them. Finding them in the real data wasn't just confirmation. It was the kind of successful prediction that makes scientists take notice. The gravitational mechanisms at work here operate on timescales that dwarf human civilization. An object in the outer solar system might take hundreds of thousands of years to complete one oscillation cycle. Planet 9 itself takes 10,000 to 20,000 years just to complete a single orbit. The gravitational dance between Planet 9 and these distant objects unfolds across geological epochs, invisible to any observer watching for less than millennia. We're catching a single frame of a movie that's been playing for billions of years. Does Planet 9 affect the known planets directly? Neptune's orbit should show tiny perturbations if Planet 9 exists, wobbles measurable in the planet's position over time. Astronomers have looked for these signatures. So far, the results are inconclusive, which actually makes sense given Planet 9's distance. At 300 to 600 astronomical units, its gravitational pull on Neptune is extraordinarily weak. Neptune is 30 astronomical units from the Sun. Planet 9 is 10 to 20 times farther out. Gravitational force drops off with the square of distance, so Planet 9's pull on Neptune is hundreds of times weaker than Neptune's pull on itself. Detecting such subtle effects requires decades of precise observations and sophisticated data analysis. We might not see clear perturbations in Neptune's orbit for years yet. Uranus presents a different puzzle. This ice giant is tilted on its side, rotating with its axis nearly in the plane of its orbit rather than roughly perpendicular like every other planet. Various theories have tried to explain this bizarre orientation: a giant collision during formation, gravitational interactions during planetary migration, or cumulative effects from multiple smaller impacts. Could Planet 9 be responsible? Probably not directly. The tilt likely originated during the solar system's chaotic youth, and Planet 9's current location doesn't provide the right geometry to have caused it. But if Planet 9 was ejected from the inner solar system, it might have been one of several factors contributing to the orbital chaos that tilted Uranus. Not the sole cause, but part of a complex sequence of gravitational interactions. The asteroid belt between Mars and Jupiter seems far removed from Planet 9's domain, but even here there might be subtle connections. Some asteroids have been found on highly elliptical orbits that take them far beyond Neptune. These aren't main belt asteroids in the traditional sense, they're trans-Neptunian objects that happen to pass through the inner solar system. Planet 9 could influence the population of these objects, determining which ones get perturbed onto planet-crossing orbits and which stay safely beyond Neptune. This matters for understanding impact rates on the inner planets over geological time. If Planet 9 exists, it's been shaping the flux of impactors throughout solar system history. Centaurs, those hybrid objects orbiting between Jupiter and Neptune, neither quite asteroids nor comets, show dynamical properties that could reflect Planet 9's influence. These objects are thought to originate from the trans-Neptunian region and get gravitationally scattered inward. The rate at which objects get scattered, and the specific orbits they end up on, depend on the outer solar system's gravitational environment. Add Planet 9 to the mix, and you change the probabilities. More objects might get kicked onto certain types of orbits, fewer onto others. Detailed population studies of centaurs could, in principle, reveal Planet 9's gravitational fingerprint even in the middle reaches of the solar system. What's remarkable about all these effects is their consistency. Planet 9 isn't just explaining one weird thing. It's explaining multiple independent phenomena across different populations of objects in different regions of the solar system. The clustering of extreme trans-Neptunian objects. The perpendicular objects. The Sun's axial tilt. The distribution of orbital inclinations. Each one could potentially have a different explanation. But they all point to the same solution: a massive planet on a distant, tilted orbit. That's what makes the hypothesis so compelling. Still, correlation isn't causation. Maybe these effects have other explanations we haven't considered. Maybe observational biases we haven't properly accounted for are creating patterns where none exist. Maybe the solar system is just weird in multiple unrelated ways. These possibilities keep skeptics skeptical, and rightfully so. Extraordinary claims require extraordinary evidence. But with each new study, with each additional prediction that proves correct, the case grows stronger. The question isn't really whether Planet 9 affects the solar system. If it exists at all, it must. Gravity doesn't have an off switch. The question is whether we can measure those effects precisely enough to confirm the planet's existence indirectly. And that's where the cutting edge of observational astronomy comes in, techniques for detecting planets not by seeing them directly, but by mapping their gravitational influence on everything around them. The art of finding invisible planets has evolved dramatically since Neptune's mathematical discovery in 1846. Back then, astronomers noticed Uranus wasn't following its predicted path. Something was tugging on it. They worked backward from those perturbations, calculated where the disturbing mass had to be, pointed their telescopes at that spot, and there it was. A new world revealed through pure mathematics. Planet 9 requires a more sophisticated approach. We're not tracking one object getting pulled by an unknown planet. We're analyzing dozens of distant bodies, each with its own orbital peculiarities, trying to extract a common signal from the noise. It's less like following footprints to find what made them and more like being a detective at a crime scene with multiple witnesses who each saw something slightly different. The statistical methods matter enormously here. Brown and Badijan didn't just notice the clustering and declare victory. They quantified it. They developed techniques to measure observational bias in each individual object's discovery, because not all parts of the sky get observed equally. Some regions get scanned more frequently. Some get deeper exposures. Telescopes point where astronomers tell them to point, and astronomers have their own interests and observing programs. This creates selection effects. If you only search for distant objects in certain parts of the sky, you'll only find distant objects in those parts of the sky. Obvious, right? But correcting for this bias mathematically isn't straightforward. You need to know not just where you looked, but how thoroughly you looked there, and with what sensitivity. Brown and Badijan accounted for these factors, and even after corrections, the clustering remained statistically significant. About 1 chance in 500 that it's random. That number has gotten better with time. As more objects get discovered and the sample size grows, the statistical confidence strengthens. By 2021, Brown and Badijan reanalyzed with improved bias corrections and found a clustering significant at 99.6% confidence. That's getting into the realm where you start taking things very seriously. But statistics alone don't make a planet. The real power comes from prediction. If your hypothesis is correct, it should tell you what else you'll find. Planet 9 makes specific predictions about populations of objects that should exist but hadn't been looked for yet. And that's where things get interesting. One prediction involves objects perpendicular to the solar system's plane. Not just tilted. Perpendicular. Orbiting the sun almost vertically while everything else goes around horizontally. These objects shouldn't exist in a normal solar system. There's no mechanism to put them there. Yet Planet 9's gravitational influence, according to the models, should create exactly this population. 5 objects matching this prediction have been found. 5 might not sound like many, but remember, these are extremely rare configurations. Finding even one was surprising. Finding 5 that matched the theoretical prediction in detail. That's not coincidence. Another test came in 2024. Brown and Badigian published analysis of a different population, low-inclination trans-Neptunian objects with orbits that reach inside Neptune's orbit. These objects have nothing to do with the original clustering that suggested Planet 9. They're on completely different types of orbits. Yet when you run simulations with Planet 9 included, these objects' orbital distribution matches what we actually observe. Remove Planet 9 from the simulations, and the match disappears. The statistical rejection of the Planet 9 free scenario sits at 5 sigma. That's the same confidence level physicists demanded before announcing the Higgs boson discovery. Does this prove Planet 9 exists? No. Science doesn't deal in proof, only in evidence and confidence levels. But the confidence is getting high enough that dismissing the hypothesis requires explaining away multiple independent lines of evidence. The skeptics haven't been silent. Samantha Lawler and others argue that observational biases are stronger than Brown and Badigian acknowledge. In 2020, 2 large surveys, the Outer Solar System Origins Survey and the Dark Energy Survey, found hundreds of trans-Neptunian objects and saw no significant clustering. OSOS documented over 800 objects. DES found 316 new ones. Both surveys carefully accounted for observational bias and concluded the orbits could be explained by known physical processes without invoking a 9th planet. This disagreement cuts to the heart of how science works. Same solar system, same objects, different conclusions. Why? It comes down to which objects you include in your analysis and how you correct for bias. Brown and Badigian focus on the most extreme objects, the ones farthest out with the most elongated orbits. These are the objects most likely to be influenced by Planet 9 because they venture into its gravitational domain. OSOS and DES looked at a broader population including objects that wouldn't be strongly affected by Planet 9 even if it exists. The debate also involves sample size versus sample quality. OSOS has more objects, but are they the right objects for testing this particular hypothesis? 1,000 data points don't help if they're measuring the wrong thing. Meanwhile, Brown and Badigian's smaller sample focuses on exactly the objects that should show Planet 9's influence most clearly. It's a classic tension in observational astronomy. More data isn't always better data if it dilutes your signal. Alternative explanations have emerged. Maybe instead of one big planet, there's a disk of smaller icy bodies with combined mass equivalent to Planet 9. Spread that mass out, and you might get similar gravitational effects. Or perhaps these orbits were set during the solar system's birth, when the Sun formed in a stellar cluster and neighboring stars perturbed the outer reaches. Some researchers even propose multiple Earth-mass rogue planets rather than one super-Earth. Each alternative has problems. The disk hypothesis requires an improbably specific mass distribution that stays stable over billions of years. The stellar cluster scenario works for setting initial conditions but doesn't explain why the clustering persists today, billions of years after the Sun left its birth cluster. Multiple rogues would need to have been captured with just the right orbits and masses to produce the observed effects without disrupting everything else. What makes Planet 9 compelling isn't that it's the only possible explanation. It's that it's the simplest explanation that accounts for multiple independent observations. One object, one orbit, multiple predictions that keep being confirmed. That's powerful. The thermal emission angle offers another avenue. Planet 9, if it exists, is still cooling from its formation. At 5 Earth masses, it retains significant internal heat. Even at 47 Kelvin, frigidly cold by any human standard, it radiates in the infrared. This radiation should be detectable with the right instruments, particularly submillimeter telescopes that specialize in this wavelength range. The challenge is sensitivity. Planet 9's thermal signature is faint, and the infrared sky is crowded. Lots of things emit at these wavelengths. You need long integration times, careful subtraction of foreground and background sources, and the patience to search a large area of sky. Several groups are working on this, using facilities like the Atacama Large Millimeter Array. No detections yet, but the search continues. Direct optical detection faces a different set of challenges. At aphelion, Planet 9 could be 800 astronomical units away or more, moving through the most distant parts of its orbit. At that distance, reflected sunlight is vanishingly faint. You need large telescopes with wide fields of view, and you need to image the same regions repeatedly to detect motion. The Subaru telescope in Hawaii has been conducting systematic searches. So have other facilities. They've covered about 78% of the possible sky positions where Planet 9 might be. That sounds good until you realize the remaining 22% is still a huge search space. Statistically, Planet 9 is more likely to be near aphelion than perihelion, simply because it moves slower out there and spends more time in that part of its orbit. That's where Kepler's second law bites you. Objects sweep out equal areas in equal times, which means they crawl along when far from the Sun. If Planet 9 is currently near aphelion, it's at its faintest and hardest to detect. Bad luck for us, but that's the reality. The search isn't hopeless. It's methodical, systematic, and ongoing. Every survey that comes up empty eliminates possibilities and narrows the remaining search space. Brown and Badijan have refined their predictions multiple times based on new data, updating the most likely orbital parameters. Their current best estimate puts the semi-major axis around 380 to 460 astronomical units, though a 2025 study by Siraj, Chaiba, and Tremaine suggests it might be closer, around 290 astronomical units. Closer means brighter. Brighter means easier to find. And then there's the Vera Rubin Observatory, scheduled to begin operations in 2025, which changes everything. The Vera Rubin Observatory is unlike anything that's come before. Sitting on Cerro Pachón in Chile at 2,700 meters elevation, it houses an 8.4-meter primary mirror and the largest digital camera ever built for astronomy. 3 gigapixels. That's not a typo. The camera weighs 3 tons and captures an area of sky equivalent to 40 full moons in a single image. Why does this matter for Planet 9? 2 reasons. Coverage and cadence. Rubin will survey the entire visible southern sky every few nights. Not targeted observations of specific regions. The whole sky, repeatedly, for 10 years. Every object in that survey gets tracked automatically. The system compares new images to previous ones, flagging anything that moves, changes brightness, or appears where nothing was before. Planet 9, if it exists, moves. Slowly. Over months and years, it would shift position relative to background stars. That's its signature. Rubin's repeated imaging strategy is custom-built to catch exactly that kind of motion. You don't need to know where to look ahead of time. You just watch everything and let the data tell you what moved. Mike Brown's enthusiasm about Rubin isn't exaggeration. He spent years searching with Subaru, which is an excellent telescope but requires choosing where to point. Rubin doesn't. It watches. Constantly. Systematically. If Planet 9 is anywhere in the southern sky at a detectable brightness, Rubin will find it. Not might find it. Will find it. Scott Shepard estimates the probability at 70 to 80%, assuming Planet 9 exists and has the predicted properties. Those are good odds in astronomy. Mario Jurek points out that Rubin will increase the known population of trans-Neptunian objects from around 4,000 to potentially 40,000. That's not just more objects. That's better statistics, tighter constraints, and a far clearer picture of what's actually happening in the outer solar system. The timeline is aggressive. Megan Schwam says the first year or two of Rubin operations should answer the question. Either Planet 9 shows up in the data, or the lack of detection tells us something definitive about where it isn't and what it can't be. This is the moment. After nearly a decade of predictions, simulations, and targeted searches, we're about to conduct the most comprehensive survey of the outer solar system ever attempted. If Planet 9 is real, 2025 through 2027 could be the years we finally see it. But what if Rubin doesn't find it? That's the scenario nobody talks about much, but it's worth considering. Absence of evidence isn't evidence of absence, except when you've looked everywhere the thing could possibly be. Rubin gets us close to that threshold. If Rubin completes its survey without detecting Planet 9, the hypothesis doesn't collapse entirely, but it gets significantly harder to maintain. Maybe Planet 9 is fainter than expected. Maybe it's in a part of the sky Rubin can't see as well. Maybe it's currently too close to the galactic plane where background star density makes detection difficult. There are outs. But they start sounding like special pleading after a while. The other possibility is that Planet 9 exists but isn't where the models predict. Orbital parameters have shifted multiple times as new data comes in. The 2025 Siraj study suggested a closer, less eccentric orbit than previous estimates. If that's correct, Planet 9 might be brighter and easier to find. But if the models are still off, we might be looking in the wrong regions entirely. Then there's the alternative explanations. What if the orbital clustering of trans-Neptunian objects isn't caused by a single planet but by a disk of smaller objects, each too faint to detect individually but collectively massive enough to produce gravitational effects? That hypothesis has been proposed. It works mathematically for some observations but struggles to explain others, particularly the perpendicular objects. Or what if the clustering is a transient phenomenon caused by something that's no longer there? A passing star could have perturbed orbits temporarily. The Sun's birth cluster could have left a dynamical imprint that's still visible today. Multiple captured rogue planets might produce similar effects without requiring a single massive world. These scenarios feel more contrived than a single planet, but they're not impossible. Brown has argued that rejecting Planet 9 means accepting 5 or 6 separate unexplained phenomena, each requiring its own cause. That's inelegant. Science favors parsimony. One explanation that accounts for multiple observations beats several disconnected explanations. But parsimony isn't proof. Sometimes reality is messy and complicated. The discovery of Ammonite, a new sednoid announced by the Subaru team, adds another wrinkle. Ammonite's orbit doesn't cluster with the other sednoids the way Planet 9's gravitational influence would predict. It's off on its own. That might mean Planet 9's orbit needs further adjustment to account for Ammonite. Or it might mean something else entirely is going on. Every new discovery refines the picture, but it also introduces new constraints that any hypothesis has to satisfy. That's how science works. You don't get to cherry-pick the observations that support your model and ignore the rest. You have to explain all of it. Brown and Badijan have been transparent about this process. They've updated their predictions multiple times based on new data. They've addressed criticisms. They've acknowledged uncertainties. That's not weakness. That's how you build a robust scientific case. You test it against everything, adjust when necessary, and see if it still holds up. The April 2024 paper on low-inclination trans-Neptunian objects is a good example. These are objects that cross Neptune's orbit, a completely different population from the extreme distant objects that sparked the original hypothesis. Yet when you model their distribution, Planet 9's gravitational influence predicts their observed spread with remarkable accuracy. No Planet 9. The distribution doesn't match. With Planet 9, it does. That's independent confirmation using a different dataset. Statistical confidence levels matter here. A 5 sigma result means the probability of the observation occurring by chance is less than 1 in 3. 5 million. That's the standard for discovery in particle physics. It's extremely stringent. The 2024 study rejected the no Planet 9 scenario at approximately 5 sigma confidence. That's not suggestive. That's strong. Brown's statement that he thinks it's very unlikely Planet 9 doesn't exist reflects this accumulating evidence. It's not arrogance. It's Bayesian updating. Start with a hypothesis. Test it against observations. Adjust your confidence based on how well it performs. After 8 years of testing, the hypothesis keeps working. That shifts the probability upward. Could everyone be wrong? Of course. Science has a long history of confident predictions that turned out to be false. Vulcan, the hypothetical planet inside Mercury's orbit, was predicted to explain perturbations that Einstein's general relativity later explained without needing an extra planet. The luminiferous ether seemed necessary until it wasn't. Confidence doesn't equal certainty. But here's the key difference. Vulcan was never observed. Planet 9 hasn't been observed either, but the effects attributed to it keep showing up in independent datasets. The orbital clustering persists after correcting for observational bias. The perpendicular objects exist. The low-inclination objects match predictions. The Jupiter family comet distribution changes in the expected way. The predicted reduction in Oort cloud capture efficiency aligns with simulations. That's a lot of things to get right by accident. It's not impossible, but it's increasingly unlikely. Each successful prediction raises the prior probability that the underlying model is correct. So where does that leave us as Rubin prepares to begin operations? We're at a decision point. Within 2 years, maybe 3, we'll have data comprehensive enough to either confirm Planet 9's existence or rule it out across most of its possible parameter space. This isn't a kind of question that lingers unresolved for decades. The technology exists. The survey is happening. The answer is coming. If Rubin finds Planet 9, it will be one of the most significant planetary discoveries in history. Not because it's a planet, though that's cool. Because of what it tells us about solar system formation, migration dynamics, and the possibility that our planetary census was incomplete for the entire history of astronomy. If Rubin doesn't find it, that's also significant. It means either the hypothesis was wrong, or Planet 9 is so far, so faint, or so weirdly positioned that even our best efforts can't detect it. That possibility can't be dismissed. The outer solar system is vast. Assumptions about brightness and location might be off. But at some point, a hypothesis that can't be tested stops being useful. The broader implications extend beyond our solar system. Discovering Planet 9 would make our system more similar to others. Most exoplanetary systems contain super-Earths, planets with masses between Earth and Neptune. We don't have any. Planet 9 would fill that gap, suggesting that our system formed similarly to others, but with a quirk. One of the planets got kicked outward instead of staying close. That has implications for planet formation theory. How common is ejection? What determines whether a forming planetary system ends up with all its planets in tight orbits versus having one or more in distant eccentric orbits? Are we typical or unusual? Planet 9 helps answer those questions. It also affects how we think about planetary migration. The NICE model explains a lot about how the giant planets reach their current orbits, but it's not complete. If Planet 9 is an ejected ice giant, that's a direct observation of a process we've only simulated. We could study its composition, atmosphere, and thermal properties. We could learn what happens to a planet that gets thrown into the outer darkness and survives there for billions of years. All of that depends on detection. And detection depends on Rubin. The next few years will be decisive. The search itself has an interesting dynamic. Brown and his team aren't the only ones looking. Multiple groups worldwide are scanning different portions of the sky, using different methods, hoping to be the first to spot it. There's a competitive element, though it's mostly friendly. Everyone wants the discovery, but everyone also wants the answer, regardless of who provides it. What happens if Rubin spots something in the right region with the right motion? Confirmation would take time. A single detection isn't enough. You need multiple observations over weeks or months to establish an orbit. Then you need spectroscopy to determine composition. Is it icy? Gaseous? Does it have an atmosphere? What's its temperature? All of that requires follow-up with other instruments. And here's something people don't always consider. If Planet 9 exists and Rubin finds it, that's not the end of the story. It's the beginning. We'd have a new planet to study. A super-Earth in our own solar system, close enough to observe in detail but far enough to be genuinely alien. What can we learn from it? For one thing, we could study its atmosphere if it has one. Most super-Earths we've detected around other stars are too far away for detailed atmospheric analysis. Planet 9 would be right here, relatively speaking. We could point infrared telescopes at it, measure its thermal emission, detect molecular signatures, and figure out what it's made of. We could also study its interaction with the surrounding environment. Does it have moons? Rings? A magnetic field? How does it affect the local dust distribution? Does it capture comets or asteroids into temporary orbits? All of those questions become answerable once we know where it is. The formation question would become more tractable too. If Planet 9 is an ejected ice giant, we could compare its properties to Uranus and Neptune. Are they similar? Different? That tells us about the conditions under which they formed and what happened during the ejection process. Did Planet 9 lose its outer layers during the encounter with Jupiter? Did it retain them? The answers matter for understanding how planetary systems evolve. There's also the possibility of detecting other distant planets. If one exists, maybe others do. The outer solar system is huge. We've barely scratched the surface. Rubin will find thousands of new trans-Neptunian objects, and some of them might have orbits that point to additional unseen bodies. Planet 9 might not be alone. But let's consider the other scenario. Rubin surveys the entire accessible region and finds nothing. What then? First, it doesn't immediately kill the hypothesis. The predicted orbit has uncertainty. If Planet 9 is near its aphelion and farther than expected, Rubin might miss it. Its brightness could be lower than predicted. There are scenarios where Planet 9 exists but remains undetected even after Rubin's survey. However, those scenarios become increasingly constrained. If Rubin doesn't find it, the parameter space shrinks dramatically. The planet would have to be fainter, farther, or in a very specific location that Rubin didn't cover. At that point, the hypothesis starts looking less likely. It wouldn't vanish entirely. Science doesn't work that way. But the community's confidence would shift. If the best survey we've ever conducted finds nothing, most astronomers would conclude that Planet 9 probably isn't there, at least not in the form currently predicted. That would leave the clustering problem unresolved. The orbital alignment of trans-Neptunian objects would still need an explanation. Maybe it's observational bias after all, despite the corrections. Maybe it's a temporary configuration that will disperse over time. Maybe there's a different mechanism at work that we haven't thought of yet. Or maybe there's something else out there, not a single planet but a different kind of object. A primordial black hole, for instance. That's been proposed as an alternative. A black hole with a few Earth masses could produce similar gravitational effects without being visible. It wouldn't emit light, wouldn't reflect sunlight, and would be nearly impossible to detect directly. The black hole hypothesis is speculative, but it's not absurd. Primordial black holes, if they exist, would have formed in the early universe from density fluctuations. Some could have been captured by the solar system. The gravitational effects would be identical to a planet of the same mass. The only difference is detectability. How would you find a black hole in the outer solar system? Gravitational lensing, maybe. If it passed in front of a distant star, the star's light would bend around it, creating a brief brightening. Rubin could detect that. It's a long shot, but it's possible. Another alternative is a disk of smaller objects, collectively massive enough to produce the observed effects. Instead of one planet, imagine thousands of smaller bodies distributed across a wide region. Their combined gravity could shepherd trans-Neptunian objects into aligned orbits. The disk hypothesis has problems though. To match the observed clustering, the disk would need a very specific mass distribution and configuration. It's not impossible, but it requires fine-tuning. A single planet is simpler. Occam's razor favors the simpler explanation, but simplicity doesn't guarantee correctness. So where does the evidence actually point right now, before Rubin starts observing? The statistical case for Planet 9 has strengthened. The 2024 study showing alignment of low-inclination objects was a big deal. That's a new population, independent of the original clustering, behaving exactly as predicted. The odds of that happening by chance are very low. But statistics aren't proof. Astronomy has seen confident predictions proven wrong before. The key is falsifiability. Planet 9 is falsifiable. If Rubin surveys the predicted region and finds nothing, the hypothesis is either wrong or needs major revision. That's good science. It's worth stepping back and asking why this matters beyond pure curiosity. Why should anyone care if there's a ninth planet? One reason is completeness. If we don't know our own solar system, how can we claim to understand others? Planet 9, if real, has been there the entire time humans have looked at the sky. Missing something that large in our own neighborhood would be humbling. Another reason is the connection to exoplanetary science. Super-Earths are everywhere. We've found thousands around other stars, but we don't have one here to study up close. Planet 9 would be the only super-Earth we can observe in detail, the only one we can send probes to eventually. That makes it scientifically valuable beyond its role in solar system dynamics. There's also the historical angle. Discovering a new planet is rare. It doesn't happen often. Neptune in 1846. Pluto in 1930, though that got reclassified. If Planet 9 is real, this generation gets to witness something that happens maybe once per century. That's not nothing. And then there's the sheer weirdness of it. A planet 10 times Earth's mass, orbiting hundreds of times farther from the Sun than we do, taking 20,000 years to complete one orbit. It's so far out that the Sun looks like just another bright star. Temperatures are near absolute zero. If it has an atmosphere, it's probably frozen solid. It's a world more alien than anything we've explored, and it's technically in our solar system. What would it be like to visit Planet 9? Impossible with current technology, obviously. The distance is staggering. Voyager 1, the fastest probe we've ever launched, has been traveling for over 40 years and still hasn't reached the predicted inner edge of Planet 9's orbit. Getting there would take centuries with existing propulsion systems. But imagine if we could. What would you see? The Sun would be a bright point of light, no disk visible, providing almost no heat. The sky would be black, filled with stars that don't twinkle because there's no atmosphere to distort them. The planet itself, if gaseous, might have faint cloud bands, though they'd be moving incredibly slowly in the cold. Moons, if they exist, would be frozen solid, covered in ancient impact craters. It would be the most isolated place a human could stand and still be within the Sun's gravitational influence. The nearest planet, Neptune, would be billions of kilometers away. Earth would be invisible without a telescope. You'd be at the edge of the solar system, looking outward toward interstellar space, inward toward the distant Sun, and feeling utterly, completely alone. That's Planet 9. If it exists. And within 2 years, we'll have a much better idea whether it does. Rubin starts observations soon. The data will accumulate. The algorithms will scan for slow-moving objects. And somewhere in those billions of data points, there might be a faint dot that moves just slightly between images. Or there might not. Either way, we're about to find out. The search for Planet 9 is entering its final phase. The question that's lingered for nearly a decade will finally get an answer. Whatever that answer is, it'll reshape how we understand the solar system. That's worth paying attention to. Looking at the timeline, we're living through something remarkable. The Vera Rubin Observatory represents the culmination of decades of technological advancement in astronomy. Its 2-gigapixel camera, its systematic survey strategy, its ability to track billions of objects simultaneously, all of it converges on this moment. We built the perfect machine for finding Planet 9 without necessarily intending to. The telescope doesn't care about the hypothesis. It's going to scan the southern sky regardless, cataloging everything that moves, everything that changes, everything that exists in its field of view. Planet 9 is just one target among billions. But if it's there, Rubin will see it. The odds are too good. The coverage too complete. The sensitivity high enough. What happens next depends entirely on what the data shows. If Planet 9 appears in the images, moving slowly across the background stars over weeks and months, the discovery will unfold gradually. Not a single eureka moment, but a pattern emerging from noise. Statistical confidence building with each new observation. orbital parameters refined as more data points accumulate. Eventually, certainty. The confirmation process would take time. You don't announce a planet based on a handful of detections. You need enough measurements to calculate an orbit accurately. You need spectroscopy to determine composition. You need infrared observations to measure temperature and size. The full characterization might take years. But the initial detection, the moment when someone realizes there's a new object in the right region with the right motion, that could happen within months of Rubin's first light. And if it doesn't show up? If 2 years pass, then 3, and the predicted regions yield nothing? The hypothesis doesn't instantly collapse, but it enters a different phase. The parameter space contracts. The alternative explanations become more attractive. At some point, you stop saying, "We haven't found it yet," and start saying, "It's probably not there." That outcome would be significant too. Not as exciting as discovering a new planet, but scientifically valuable nonetheless. We'd know the clustering of trans-Neptunian objects needs a different explanation. Maybe it's a selection effect we haven't fully accounted for. Maybe it's a transient configuration that won't persist. Maybe there's something else entirely driving those orbits, something we haven't considered. Science advances through ruling things out as much as confirming them. But the smart money is on detection. Brown and Badijan aren't betting their reputations on a whim. They've spent 8 years refining this hypothesis, testing it against new data, addressing criticisms, making predictions that keep being confirmed. The 2024 results on low-inclination objects were particularly compelling. Different population, same result. That pattern repeating across independent datasets is hard to dismiss. The formation question remains fascinating regardless of when detection happens. If Planet 9 is an ejected ice giant, it validates predictions from the NICE model that have been purely theoretical until now. We'd have direct evidence that planetary systems can eject giant planets without losing them entirely. That has implications for every exoplanetary system we observe. How many systems have hidden planets in distant orbits? How common is this configuration? If Planet 9 is a captured exoplanet, the implications are even stranger. It would mean our sun stole a world from another star during the solar system's youth. That's not impossible. Stellar nurseries are chaotic places where close encounters happen. But confirming it would be extraordinary. The first exoplanet discovered in our own solar system, a cosmic immigrant that's been here for 4.5 billion years. The public interest in Planet 9 reflects something deeper than just curiosity about astronomy. There's something compelling about the idea that we still don't fully know our own neighborhood. Despite centuries of observation, despite sending probes to the outer planets, despite thinking we'd mapped everything significant, there might still be a world we missed. A giant world, not some tiny asteroid, but a super-Earth mass planet that's been there all along. It's humbling in the right way. It reminds us that the universe doesn't reveal its secrets easily. Even in our own backyard, even with modern technology, there are still mysteries waiting to be solved. Planet 9, if real, represents the last great planetary discovery possible in the solar system. After this, we'll have found everything larger than Pluto. The inventory will be complete. The search itself demonstrates how modern astronomy works. No lone genius staring through a telescope. Teams of researchers analyzing data from multiple instruments, running simulations on supercomputers, developing statistical methods to extract signals from noise, publishing results for peer review, responding to criticism, refining predictions. It's collaborative, iterative, and methodical. Not as romantic as the old stories of discovery, but more reliable. Brown's comment about Rubin being the perfect telescope for finding Planet 9 wasn't hyperbole. The match between the hypothesis's requirements and the observatory's capabilities is almost perfect. Wide field for covering large search areas. Deep sensitivity for detecting faint objects. Repeated observations for tracking motion. Automated data processing for handling billions of measurements. Everything needed to find a slow-moving distant planet, built into one facility. The timing feels right too. The hypothesis emerged in 2016. The predictions have been tested and refined over nearly a decade. The search space has been narrowed through systematic surveys. And now, just as we're ready for a definitive answer, the ideal instrument comes online. It's not coincidence. It's how science progresses. You develop a hypothesis, you test it as best you can with existing tools, and eventually technology catches up to enable the critical test. Rubin's broader impact on astronomy will extend far beyond Planet 9. The 10-year survey will revolutionize our understanding of the outer solar system, discovering tens of thousands of new trans-Neptunian objects, tracking comets, detecting asteroids, mapping the structure of the Kuiper Belt. Planet 9 is just one target in a much larger program. But it's the target everyone will be watching for. Imagine the moment of discovery. Someone running detection algorithms on Rubin data, seeing an object appear in the right region with the right motion. The double-checking. The orbital calculation. The realization that this might actually be it. The careful announcement. The flood of follow-up observations from telescopes worldwide. The gradual confirmation as the data accumulates. The moment when doubt shifts to certainty. Or imagine the alternative. Years passing. The survey completing. The predicted regions thoroughly searched. Nothing found. The slow acceptance that Planet 9 probably isn't there, at least not where expected. The return to other explanations for the orbital clustering. The questions about what we missed or misunderstood. Both scenarios advance our knowledge. One gives us a new planet to study. The other forces us to rethink our interpretation of outer solar system dynamics. Either way, we learn something fundamental about our cosmic home. The next 2 years will answer a question that's persisted since 2016. Is there a ninth planet? The mathematics say yes. The statistics say yes. The predictions keep being confirmed. But science demands direct observation. We need to see it. And we're finally at the point where that's possible. Planet 9 represents the kind of mystery that makes astronomy compelling. Not abstract or impossibly distant. Right here in our solar system. Big enough to matter. Strange enough to surprise us. And just barely beyond our current ability to detect, though that's about to change. The giant lurking in the darkness beyond Neptune might soon step into the light. Or it might remain a mathematical phantom, a compelling hypothesis that couldn't be confirmed. Within 2 years, we'll know. Rubin will scan the sky, the algorithms will run, and the data will tell us what's really out there. The answer is coming. The planet you're standing on right now has died and been reborn more times than you can imagine. 252 million years ago, Earth crossed a threshold so catastrophic that 9 out of every 10 species simply vanished. What came after wasn't recovery. It was reinvention. The Triassic period emerged from that apocalypse, and the creatures that rose to fill the silence were unlike anything that had come before. This wasn't the age of dinosaurs yet. Not really. This was something stranger, more experimental, more desperate. Life was figuring itself out again from scratch, and the results were terrifying. At the dawn of the Triassic, Earth resembled a planet-sized wound trying to heal. The supercontinent Pangaea stretched from pole to pole, a single massive landmass surrounded by the Panthalassa Ocean. There were no ice caps. No polar bears waiting at the ends of the Earth. Just endless desert sprawling across the interior, where temperatures could spike beyond what most modern animals could survive. The Permian-Triassic extinction had just torn through the biosphere like a cosmic eraser. Volcanic eruptions in what's now Siberia had pumped gigatons of carbon dioxide and sulfur into the atmosphere for hundreds of thousands of years. The oceans acidified. Oxygen levels plummeted. Even insects, those nearly indestructible survivors, were pushed to the brink. So when life finally crawled back, it did so cautiously. The early Triassic was a shadow of what had been. Ecosystems were simple, almost primitive. Small reptiles and amphibians dominated, not because they were superior, but because they were what remained. Lystrosaurus, a pig-sized herbivore with a turtle's beak, made up roughly 95% of land vertebrates. Imagine a world where nearly every animal you encounter is the same species. That's how depleted Earth had become. But survival has a way of breeding innovation. As carbon dioxide levels stayed elevated and the planet remained hot, something unexpected happened. Life didn't just recover. It exploded into forms that had never existed before. The Middle Triassic saw the emergence of entirely new body plans, new strategies, new predators. And among them were the archosaurs, the ruling reptiles that would dominate for the next 150 million years. These weren't the archosaurs you're picturing. Not yet. Early forms like Euparkeria were small, maybe a meter long, with long tails and sprawling limbs. But they had something critical, an ankle joint that allowed more efficient movement, a more upright stance. This wasn't just anatomy. It was potential. While archosaurs were finding their footing, another group was already thriving. The cynodonts, distant cousins of modern mammals, were diversifying rapidly. They had differentiated teeth, whiskers, possibly even fur. Some paleontologists believe they were warm-blooded, a massive advantage in the volatile Triassic climate. These creatures weren't dominant, but they were persistent, occupying niches that larger predators ignored. Then there were the temnospondyls, massive amphibians that refused to give up their aquatic dominance. Mastodonsaurus could reach lengths of 6 meters, with a skull alone stretching over a meter. These weren't the frogs and salamanders you know. They were apex predators in rivers and lakes, crushing prey with bone-shattering jaws. But the real story of the Triassic isn't about who survived. It's about what they became. By the late Triassic, the world had changed again. Pangaea was beginning to fracture, though it would take millions more years to fully split apart. Rainfall increased in some regions, turning barren deserts into lush forests of conifers, ferns, and cycads. With more vegetation came more herbivores. And with more herbivores came larger, more sophisticated predators. This is when the monsters arrived. Postosuchus stalked the landscape of what's now North America, a quadrupedal predator built like a crocodile but acting like a wolf. For meters long, with powerful jaws and serrated teeth, it was an apex hunter, perfectly adapted to ambush prey in forested environments. Postosuchus wasn't a dinosaur. It was a Rauisuchian, part of that broader archosaur family that was experimenting with dominance. And it wasn't alone. Saurosuchus prowled South America, even larger, reaching up to 9 meters. These creatures moved on all fours but could rear up on their hind legs when attacking, combining power with flexibility. Their skulls were massive, reinforced to withstand the stress of crushing bone. They were, in every functional sense, the top of the food chain. Here's the strange part. These apex predators weren't dinosaurs, and they weren't destined to become dinosaurs. They were a separate lineage, one that would eventually go extinct. But for tens of millions of years, they ruled. Dinosaurs during this time were smaller, less specialized, still figuring out their niche. They weren't the kings yet. They were the understudies. So what were the early dinosaurs doing? Eoraptor, one of the earliest known dinosaurs, was about the size of a dog. It lived in what's now Argentina around 231 million years ago. Eoraptor had a lightweight frame, grasping hands, and a diet that was probably omnivorous. It wasn't dominating anything. It was surviving, adapting, learning. Herrerasaurus was another early dinosaur, slightly larger, more predatory. It had a flexible jaw that allowed it to grip struggling prey, a feature that would become more refined in later theropods. But even Herrerasaurus wasn't at the top. It coexisted with much larger predators, avoiding direct competition by targeting smaller animals. What's fascinating is that dinosaurs during the Triassic weren't inevitable. There was no sign they'd eventually take over. They were one experiment among many. Crocodile relatives were larger, more successful. Mammal ancestors were more adaptable. Dinosaurs were just another group trying to make it work. Then something shifted. The late Triassic brought another wave of extinction, smaller than the Permian catastrophe but significant. Volcanic activity surged again, this time associated with the breakup of Pangaea. Climate became more unpredictable. Sea levels fluctuated wildly. And in that chaos, many of the dominant groups faltered. Rauisuchians began to decline. Large amphibians lost ground. But dinosaurs, with their more efficient respiratory systems, upright posture, and flexible diets, started expanding. Not overnight. Not in some dramatic takeover. Just slowly, persistently, filling gaps as other groups weakened. By the end of the Triassic, dinosaurs were no longer marginal. They were ascending. Plateosaurus appeared in the late Triassic, one of the first large herbivorous dinosaurs. It could reach lengths of up to 10 meters and weighed several tons. Plateosaurus was a prosauropod, a precursor to the giant sauropods that would later dominate the Jurassic. It moved on all fours but could rear up on its hind legs to reach high vegetation, a body plan that hinted at future gigantism. And then there was Coelophysis, a small, agile carnivore that hunted in packs. Fossil sites in New Mexico have revealed dozens of Coelophysis skeletons together, suggesting social behavior. These weren't solitary killers. They were coordinated, adaptable, capable of taking down prey much larger than themselves through cooperation. This is the pattern that defines the Triassic. Life wasn't dominated by a single strategy. It was a chaotic competition of body plans, metabolisms, and survival tactics. Every group had a chance. Every lineage was testing the limits of what was possible. But there's another layer to this story, one that's often overlooked. The Triassic wasn't just about land. The oceans were undergoing their own transformation. Marine reptiles exploded in diversity during this period. Ichthyosaurs, dolphin-like predators, evolved from land-dwelling ancestors and returned to the sea, developing streamlined bodies, powerful tails, and sharp teeth for catching fish. Some species grew to over 15 meters in length. They weren't fish. They were air-breathing reptiles that had fully committed to an aquatic lifestyle, a transition that happened remarkably fast in evolutionary terms. Nothosaurs patrolled coastal waters, smaller than ichthyosaurs but equally adapted. They had webbed feet, long necks, and needle-like teeth for snagging slippery prey. These creatures occupied the shallow marine environments, hunting in estuaries and lagoons where the boundary between land and sea blurred. And beneath them, in the deeper waters, placodonts grazed on shellfish. These bizarre reptiles had flat, crushing teeth designed to crack open mollusks. Some species developed turtle-like shells, armored protection against the increasing number of marine predators. The Triassic oceans were becoming crowded, competitive, and dangerous. Just like on land, the rules were being rewritten. Predators were getting faster. Prey was getting smarter. And every evolutionary innovation triggered a counter-response. This is what makes the Triassic so critical. It's not just a prelude to the age of dinosaurs. It's the laboratory where modern ecosystems were forged. The Triassic tested carnivory, herbivory, gigantism, pack hunting, marine adaptation, and dozens of other strategies. Most failed. A few succeeded. And those successes shaped everything that followed. And then it ended. Not gradually. Not through slow decline. The Triassic closed with another mass extinction around 201 million years ago, erasing roughly 70 to 80% of terrestrial species. Volcanic eruptions associated with the breakup of Pangaea released massive amounts of carbon dioxide. Global temperatures spiked. Ocean acidification returned. Ecosystems that had stabilized after the Permian were shattered once more. The difference this time was what survived. Dinosaurs made it through. Most of their competitors did not. Rauisuchians vanished completely. Large amphibians were decimated. Many marine reptile lineages disappeared. When the dust settled, the playing field had been cleared. The Jurassic period began around 200 million years ago, and for the first time, dinosaurs weren't just participants. They were dominant. This is where the popular image of prehistory begins to take shape. Giant sauropods grazing on towering conifers. Massive predators stalking through dense forests. But the reality was more nuanced than the simplified picture we often see. The early Jurassic wasn't an instant explosion of giants. It was a gradual expansion. Dinosaurs diversified into nearly every terrestrial niche. Some became enormous. Others stayed small. Some hunted alone. Others moved in herds. The key advantage dinosaurs possessed was efficiency. Their upright stance meant less energy wasted on locomotion. Their respiratory systems, with air sacs that allowed continuous airflow through the lungs, provided more oxygen per breath than mammalian lungs could manage. This wasn't a minor edge. It was fundamental. It allowed dinosaurs to sustain activity levels that other groups couldn't match, especially at larger sizes. By the Middle Jurassic, sauropods had grown truly massive. Brachiosaurus stood over 13 meters tall and weighed as much as 50 tons. Its long neck allowed it to browse vegetation that no other herbivore could reach, creating a feeding strategy that minimized competition. Diplodocus stretched even longer, reaching lengths of up to 30 meters, though much of that was tail. These weren't clumsy, slow-moving creatures. Recent biomechanical studies suggest sauropods could move at reasonable speeds, and their tails functioned as effective defensive weapons. A full-force tail strike from a diplodocus could shatter bone. Predators had to adjust. Allosaurus emerged as one of the dominant carnivores of the late Jurassic. At around 9 meters long and weighing up to 2 tons, Allosaurus wasn't the largest predator ever, but it was built for efficiency. Sharp, serrated teeth designed to tear flesh. Powerful forelimbs with large claws. A skull structure that allowed it to deliver slashing bites rather than crushing ones. Fossil evidence shows Allosaurus targeted sauropods, despite the size difference. Bite marks on sauropod bones match Allosaurus teeth. Some researchers suggest pack hunting, though the evidence remains debated. What's clear is that Allosaurus didn't need to bring down a full-grown sauropod alone. Juveniles, sick individuals, or isolated stragglers would have been easier targets. One successful kill could feed a predator for weeks. But not every dinosaur followed the path toward gigantism. Compsognathus, a contemporary of Allosaurus, was chicken-sized. Fast, agile, likely warm-blooded or at least capable of maintaining elevated body temperatures. It hunted insects, small lizards, and early mammals. Compsognathus represents the other end of the spectrum. Size wasn't everything. Speed and adaptability mattered just as much. The Jurassic also saw the rise of stegosaurs. Stegosaurus itself, with its distinctive double row of plates along its back and spiked tail, has become one of the most recognizable dinosaurs. But those plates weren't armor. They were likely thermoregulatory structures, helping control body temperature through blood flow. The real defense was the tail. For long spikes arranged in a cluster, capable of being swung with devastating force. Fossil evidence shows at least one Allosaurus died from a Stegosaurus tail-wound, penetrated vertebrae. Fatal injury. This wasn't prey waiting passively to be eaten. This was a creature that could fight back effectively. Meanwhile, in the skies above, pterosaurs were diversifying. These weren't dinosaurs, but archosaurs, a related group that had taken a different evolutionary path. Pterosaurs ranged from sparrow-sized insectivores to massive gliders with wingspans exceeding 10 meters. Pteranodon, though technically from the later Cretaceous, represents the culmination of this lineage. But even in the Jurassic, pterosaurs like Rhamphorhynchus were highly successful. Long tails for stability, sharp teeth for catching fish, membranes stretched between elongated fingers forming wings. Flight had evolved independently multiple times in Earth's history, but pterosaurs were the first vertebrates to truly master it. And then there's Archaeopteryx. Discovered in Germany in 1861, Archaeopteryx is one of the most famous transitional fossils ever found. It had feathers, clearly visible in the fossil impressions. It had wings. But it also had teeth, claws on its wings, and a long bony tail. Was it a bird? Was it a dinosaur? The answer is both. Archaeopteryx represents the evolutionary bridge between non-avian dinosaurs and modern birds. It couldn't fly like a modern bird. Its flight muscles were weaker, its wings less refined. But it could glide, possibly flap for short bursts. And that was enough. Flight didn't emerge fully formed. It evolved incrementally, each small improvement providing a slight advantage. Archaeopteryx lived around 150 million years ago, in the late Jurassic. By that point, feathers had already been around for millions of years, originally evolving for insulation or display rather than flight. Flight was a secondary adaptation, a repurposing of existing structures. This pattern repeats throughout evolution. Features evolve for one reason, then get co-opted for another. Feathers for warmth became feathers for flight. Fins for stability became limbs for walking. Evolution doesn't plan ahead. It tinkers with what's already there. The Jurassic world wasn't static. Climates shifted. Sea levels rose and fell. Pangea continued breaking apart, creating new coastlines, new ocean currents, new weather patterns. As continents separated, populations became isolated. Species that once could migrate freely were now cut off. This drove further diversification. Different environments selected for different traits. Dinosaurs in what would become North America evolved differently from those in Europe, Africa, or Asia. By the end of the Jurassic, around 145 million years ago, the stage was set for an even more dramatic period. The Cretaceous was approaching, an era that would see dinosaurs reach their absolute peak in size, diversity, and ecological dominance. But it would also be their last. Before we get there, though, there's something else worth examining. While dinosaurs dominated the land and pterosaurs ruled the air, life in the oceans was undergoing its own revolution. Marine reptiles had filled nearly every aquatic niche. Ichthyosaurs continued their reign as fast-swimming predators. But they were joined by plesiosaurs, creatures with long necks, small heads, and 4 powerful flippers. Plesiosaurs weren't fast swimmers. They were ambush predators, using their necks to dart forward and snatch fish. Some species had necks longer than their bodies, an adaptation that seems almost absurd until you consider the hunting strategy. Slow approach, sudden strike. And then there were the pliosaurs, the short-necked relatives of plesiosaurs. These were the apex predators of the Jurassic seas. Liopleurodon, though often exaggerated in popular media, was still a formidable hunter. Estimates put it at around 7 meters long with a bite force comparable to modern saltwater crocodiles. It fed on large fish, other marine reptiles, and possibly even smaller plesiosaurs. The oceans were just as competitive as the land. Every advantage mattered. Every weakness was exploited. The Jurassic represents a peak in biological experimentation. Dinosaurs had proven their dominance on land. Pterosaurs owned the skies. Marine reptiles controlled the seas. Mammals still existed, but they were small, nocturnal, and largely irrelevant to the larger story unfolding around them. Yet those mammals were learning, evolving, waiting. The Jurassic ended not with a catastrophe but with a transition. Climates continued shifting. New species emerged. Old ones faded. And as the Cretaceous began, the world entered the final act of the dinosaur era. The Cretaceous period began around 145 million years ago. It would last for 79 million years, making it the longest period of the Mesozoic era. And during that time, dinosaurs reached their absolute zenith. This wasn't just more of the same. The Cretaceous brought new families, new body plans, new extremes. Sauropods grew even larger. Theropods became more specialized. Herbivores developed unprecedented defenses. The arms race between predator and prey intensified to levels never seen before or since. One of the defining features of the Cretaceous was the rise of flowering plants. Angiosperms appeared around 130 million years ago and spread rapidly. Before this, the world was dominated by ferns, conifers, and cycads. Flowering plants changed everything. They grew faster, reproduced more efficiently, and offered new food sources. Herbivorous dinosaurs adapted. New species evolved specifically to exploit these plants. Hadrosaurs, the duck-billed dinosaurs, became incredibly diverse during this time. They had complex dental batteries, hundreds of tiny teeth packed together, perfect for grinding tough plant material. Some species developed elaborate crests on their heads, hollow structures that likely amplified sound. These weren't just for display. They were communication tools. Hadrosaurs lived in herds, and being able to signal across distances was crucial for survival. Ceratopsians also flourished. Triceratops is the most famous, but it was just one of many. These dinosaurs had massive frills and horns, features that served both defensive and social purposes. The frills weren't solid bone. They had large openings covered by skin, which reduced weight. This suggests they weren't purely defensive. Display mattered. Intimidation mattered. In a world full of predators, looking dangerous could be just as important as actually being dangerous. And the predators? They were more lethal than ever. Tyrannosaurus rex appeared late in the Cretaceous, around 68 million years ago. It's often called the ultimate predator, and for good reason. T. Rex could grow up to 13 meters long and weigh over 8 tons. Its bite force has been estimated at over 12,000 pounds, strong enough to crush bone. But size wasn't its only advantage. Recent studies suggest T. Rex had excellent vision, a keen sense of smell, and could move surprisingly fast for its size. Estimates range from 17 to 25 miles per hour. Not cheetah fast, but fast enough to run down most prey. T. Rex also had tiny arms, a feature that's been mocked endlessly. But those arms weren't useless. They were heavily muscled and could lift several hundred pounds. Their function is still debated. Gripping prey during feeding, helping the animal stand after resting. We don't know for sure. What we do know is that T. Rex didn't need them for hunting. Its jaws did all the work. Other theropods took different paths. Spinosaurus, living around 95 million years ago in what is now North Africa, was possibly the largest theropod ever. Some estimates put it at 15 meters long. It had a massive sail on its back, formed by elongated vertebrae. The purpose of this sail is still debated. Thermoregulation, display, fat storage, all are possible. But what's most striking about Spinosaurus is its lifestyle. Unlike most theropods, it was semi-aquatic. Its teeth were conical, better suited for catching fish than tearing flesh. Its nostrils were positioned high on its skull, allowing it to breathe while partially submerged. Fossil evidence suggests it spent significant time in water, hunting large fish and possibly smaller dinosaurs that came to drink. This adaptability is key. Dinosaurs weren't locked into rigid roles. They experimented. They adapted. They filled niches that hadn't existed before. The Cretaceous also saw the rise of the dromaeosaurs, the raptors. The Velociraptor is the most famous, though popular media gets it wrong. The real Velociraptor was about the size of a turkey, not the human-sized monster from movies. But it was still a formidable predator. It had a large sickle-shaped claw on each foot, used for gripping and slashing. Its arms were long and flexible, with 3-fingered hands capable of grasping prey. and it likely hunted in packs, coordinating attacks on larger animals. This level of social behavior suggests intelligence, at least relative to other dinosaurs. Larger dromaeosaurs did exist. Deinonychus, discovered in Montana, was around 3 meters long and weighed up to 70 kilograms. Utahraptor was even bigger, possibly reaching 7 meters and weighing half a ton. These weren't just scavengers. They were active hunters, using speed, coordination, and those devastating claws to bring down prey. Meanwhile, in the skies, pterosaurs reached their largest sizes ever. Quetzalcoatlus, appearing in the late Cretaceous, had a wingspan of up to 11 meters. That's wider than most small planes. It likely weighed around 200 kilograms, though some estimates go higher. How did something that large fly? Its bones were hollow and incredibly light. Its wings were made of a flexible membrane stretched between elongated finger bones. It probably spent more time gliding than flapping, riding air currents like modern albatrosses. What did it eat? Fossil evidence suggests fish, small dinosaurs, and carrion. It may have stalked shorelines, using its long neck to probe for prey. The oceans, too, were dominated by giants. Mosasaurs have replaced earlier marine reptiles as the top predators. These weren't dinosaurs. They were marine lizards, relatives of modern monitor lizards. The largest species, Mosasaurus hoffmanii, could reach 17 meters long. They had powerful jaws lined with sharp teeth, adapted for gripping slippery prey. They fed on fish, sharks, sea turtles, and even other mosasaurs. Bite marks on fossils show they weren't gentle. They were aggressive, dominant hunters. But the Cretaceous wasn't just about size. It was about diversity. Ecosystems became more complex. Food webs deepened. Interactions between species became more nuanced. Herbivores developed better defenses. Predators developed better attacks. Plants evolved chemical defenses, tough leaves, and toxic compounds. Herbivores evolved better digestion, detoxification systems, and behavioral strategies. This is coevolution in action. Each side pushes the other to adapt. Neither can afford to stop. And through all of this, the continents continued drifting. By the late Cretaceous, the world looked more recognizable. South America and Africa were fully separated. India was an island continent, drifting northward toward Asia. North America and Europe were still connected intermittently by land bridges, but the Atlantic Ocean was widening. These geographic changes had biological consequences. Populations isolated on different continents evolved independently. South American dinosaurs looked different from Asian ones. African species had their own unique traits. This geographic isolation drove further diversification. Climate during the Cretaceous was warmer than today. There were no polar ice caps. Sea levels were high, flooding low-lying areas and creating shallow inland seas. Forests extended into polar regions. Dinosaurs lived in Antarctica, which at the time was temperate, not frozen. This greenhouse climate was driven by high atmospheric carbon dioxide, likely from volcanic activity. The breakup of Pangaea created new volcanic zones, new mountain ranges, new sources of CO2. The planet was warmer, wetter, and more dynamic than at any point in the Mesozoic. But warmth doesn't mean stability. The Cretaceous experienced its own fluctuations. Ocean circulation patterns changed. Regional climates shifted. Sea levels rose and fell. These changes weren't catastrophic, but they were constant. Species had to adapt continuously. Those that couldn't went extinct. Turnover rates were high. New species appeared, old ones vanished. Evolution never stopped. Toward the end of the Cretaceous, around 70 million years ago, something else was happening. Volcanic activity was increasing. The Deccan Traps in what is now India began erupting, releasing massive amounts of lava and gas. These eruptions would continue for hundreds of thousands of years, pouring out enough lava to cover an area larger than France. The environmental impact was significant. Sulfur dioxide and carbon dioxide flooded the atmosphere. Temperatures fluctuated. Acid rain became common. Ecosystems were stressed. But they endured. Dinosaurs were still thriving. The fossil record from the latest Cretaceous shows no sign of decline. Diversity remained high. New species were still evolving. There was no slow fade, no gradual weakening. Right up until the end, dinosaurs were doing what they had always done. Adapting. Competing. Surviving. And then, 66 million years ago, everything changed. An asteroid roughly 10 kilometers in diameter struck what is now the Yucatan Peninsula in Mexico. The impact released energy equivalent to billions of nuclear bombs. The immediate effects were apocalyptic. A shockwave flattened forests for hundreds of kilometers. Tsunamis hundreds of meters high swept across coastlines. Debris blasted into the atmosphere, then rained back down as molten rock, igniting global wildfires. Within hours, much of the planet was burning. But the real killer wasn't the immediate impact. It was what came after. Dust and ash filled the atmosphere, blocking out sunlight. Temperatures plummeted. Photosynthesis stopped. Plants died. Herbivores starved. Carnivores followed. This wasn't a quick extinction. It unfolded over months, years, possibly decades. The darkness lasted long enough to collapse food chains from the bottom up. By the time the skies cleared, 75% of all species were gone. Every non-avian dinosaur vanished. Pterosaurs disappeared. Mosasaurs went extinct. The Cretaceous ended not with a gradual decline, but with a single, catastrophic blow. Yet some things survived. Birds made it through. Small mammals endured. Crocodiles persisted. Turtles survived. These weren't random survivors. They shared traits that mattered when the world went dark. Small body size meant lower energy needs. Burrowing behavior provided shelter from temperature extremes. Omnivorous diets allowed flexibility when food chains collapsed. The ability to enter dormancy, to slow metabolism and wait out the crisis, proved invaluable. Birds survived because they were small, adaptable, and could fly to wherever resources remained. Mammals survived because they were already living in the margins, already adapted to scavenging, already capable of exploiting whatever was available. The extinction didn't choose the strongest. It chose the most flexible. In the immediate aftermath, Earth was unrecognizable. Forests were gone, replaced by ferns and pioneer plants that could colonize bare ground quickly. The fern spike, a layer of fern spores found in rock strata worldwide, marks this moment. It's a geological signature of devastation, a planet resetting itself from scratch. For perhaps 1 million years, ecosystems remained simple. Food webs were short. Biodiversity was low. The survivors spread out, filling niches left empty. Mammals, no longer constrained by dinosaur dominance, began to diversify. Within 10 million years, they had radiated into forms that would eventually lead to whales, bats, primates, ungulates. Birds did the same, splitting into lineages that would become songbirds, raptors, seabirds, flightless giants. Life didn't pause. It exploded into the vacuum. But this wasn't a return to what came before. The Mesozoic was over. The age of dinosaurs had ended. What followed was something entirely new. The Cenozoic era, the age of mammals, had begun. And with it came a different set of rules. Mammals didn't dominate immediately. For the first few million years of the Paleocene, they remained small. The largest mammals were about the size of modern dogs. But they were experimenting. Some became herbivores, developing teeth suited for grinding plants. Others became carnivores, refining hunting strategies. Still others took to the trees, developing grasping hands and forward-facing eyes. The evolutionary paths that would lead to modern biodiversity were being laid down in real time. By 55 million years ago, during the Eocene, mammals had grown larger. Forests have returned, denser and more complex than before. Flowering plants, which had begun their rise in the Cretaceous, now dominated. They brought with them insects, specifically pollinators, creating intricate relationships that reshaped ecosystems. Mammals adapted to these new forests. Primates evolved, moving through the canopy. Burly horses appeared, small forest dwellers nothing like their modern descendants. Whales began their transition from land to sea, a process documented in fossil sequences showing progressive adaptations. The planet was warm again, warmer than today. Palm trees grew in Alaska. Crocodiles lived in the Arctic. This was the Paleocene-Eocene thermal maximum, a period of rapid warming driven by massive carbon release, possibly from volcanic activity or methane clathrate destabilizing on the ocean floor. temperatures spiked by 5 to 8 degrees Celsius in just a few thousand years. Ecosystems shifted rapidly. Some species went extinct. Others migrated toward the poles. Mammals continued adapting, some growing larger to cope with heat stress, others becoming more specialized. Then the planet began to cool. Gradually at first, then more dramatically. By 34 million years ago, Antarctica had frozen over. Ice sheets formed at the poles for the first time since the Mesozoic. Ocean currents changed. Climate zones sharpened. Tropical forests retreated toward the equator. Grasslands began to spread. This cooling trend, driven by shifting continental positions and declining atmospheric CO2, fundamentally altered life on land. Forests gave way to open plains. Mammals that had thrived in dense vegetation now faced new challenges. Some adapted by becoming faster, developing long legs for running. Others grew larger, using size as defense against predators. Horses evolved from small forest browsers into larger grassland grazers. Their teeth changed, becoming taller and harder to withstand the abrasive silica in grass. Their legs lengthened, their bodies streamlined for speed. This wasn't random. It was direct adaptation to a changing environment. Predators evolved in response. Carnivores became faster, more coordinated, more efficient. Pack hunting emerged as a strategy. Canids, ancestors of modern wolves and dogs, began working together to bring down prey larger than themselves. Cats refined ambush tactics, developing retractable claws and powerful builds suited for explosive attacks. The grasslands became arenas of predator-prey dynamics more intense than anything in the forests. Meanwhile, other lineages took different paths. Elephants and their relatives grew massive, developing trunks, tusks, and complex social structures. Whales, now fully aquatic, diversified into filter feeders and toothed predators, dominating the oceans in ways no marine reptile ever had. Bats refined echolocation, becoming the only mammals capable of true flight. Each group found its niche, exploited it, and diversified. By 20 million years ago, the planet looked more familiar. Continents were approaching their modern positions. India had collided with Asia, forming the Himalayas. Africa was moving toward Europe. North and South America were still separated, but the gap was closing. These geographic changes continued to drive evolution. Species isolated on different continents evolved in isolation. South America, cut off from other land masses, developed its own unique fauna. Giant ground sloths, armadillo relatives the size of cars, terror birds, flightless predatory birds standing 3 meters tall. These were the dominant animals of South America for millions of years. Africa had its own distinct groups. Early elephants, hippos, giraffes. Asia had rhinos, giant apes, saber-toothed cats. North America had camels, horses, mastodons. Each continent was its own evolutionary laboratory. Then, about 3 million years ago, the Isthmus of Panama formed, connecting North and South America. Animals began moving between continents. The Great American Interchange had begun. North American predators, more efficient and aggressive, moved south. South American herbivores, unused to such pressure, declined. Many unique South American groups went extinct. Ground sloths and armadillos moved north, but most didn't last long. The exchange was asymmetrical. North American species generally outcompete their southern counterparts. This wasn't because they were inherently superior. They came from ecosystems with higher competition, more predators, more pressure. They were battle-tested. Around 2.5 million years ago, the Pleistocene began. Ice ages returned, not as permanent features but as cycles. Glaciers advanced and retreated in roughly 100,000-year intervals, driven by variations in Earth's orbit and axial tilt. During glacial periods, ice sheets covered much of North America, Europe, and Asia. Sea levels dropped as water locked into ice. Land bridges appeared, connecting continents. Animals migrated across these bridges, spreading into new territories. Mammoths moved from Africa into Eurasia, then across Beringia into North America. Humans would follow the same route tens of thousands of years later. During interglacials, the ice retreated. Forests returned to high latitudes. Sea levels rose, flooding coastlines and isolating populations. This constant cycling drove rapid evolution. Species adapted to cold climates during glacials, then had to adapt again when warmth returned. Those that couldn't keep up went extinct. Megafauna thrived during this time. Giant mammals dominated every continent. Mammoths, mastodons, giant ground sloths, saber-toothed cats, dire wolves, short-faced bears, giant beavers, enormous kangaroos in Australia, elephant birds in Madagascar. These weren't anomalies. They were the norm. Large body size was advantageous in fluctuating climates. It allowed for better heat retention during cold periods and longer fasting during resource scarcity. But size also made them vulnerable. They reproduced slowly, needed vast territories, and required large amounts of food. When conditions changed rapidly, they struggled. And then, something new appeared. A small bipedal primate, originating in Africa, began spreading across the globe. Humans didn't seem like much at first. They were weak compared to the megafauna, slow compared to predators, lacking any obvious physical advantages. But they had something else. Intelligence. Tool use. Language. Cooperation. These traits allowed humans to hunt animals far larger than themselves, to adapt to environments from tropical rainforests to Arctic tundra, to survive where other species couldn't. As humans spread, megafauna began disappearing. The pattern is striking. In Africa, where humans evolved gradually alongside large animals, megafauna persisted. Animals there had time to adapt to human hunting pressure. But in regions humans entered suddenly, extinctions followed quickly. Australia lost its giant kangaroos, wombats, and reptiles within a few thousand years of human arrival. The Americas saw similar losses. Mammoths, ground sloths, saber-toothed cats, all gone within millennia of humans crossing into the continent. The debate continues over how much humans contributed versus climate change, but the correlation is undeniable. Where humans went, giants fell. By 10,000 years ago, the Pleistocene was ending. The last ice age was retreating. Glaciers melted, sea levels rose, climate stabilized. And in this new, warmer world, humans did something unprecedented. They stopped moving. They settled. They began farming. Agriculture wasn't an invention. It was a necessity. As megafauna disappeared, hunting became harder. Reliable food sources vanished. Humans turned to plants, domesticating wheat, rice, maize. They domesticated animals too. Sheep, goats, cattle, pigs. These weren't random choices. They were species that could thrive near human settlements, that bred quickly, that provided consistent resources. Farming changed everything. It allowed populations to grow. It created surplus, which led to specialization. Not everyone had to hunt or gather. Some could build, some could craft, some could organize. Settlements became villages. Villages became cities. Cities became civilizations. And with civilization came new pressures. Humans began shaping the environment deliberately. Forests were cleared for farmland. Rivers were diverted for irrigation. Animals were hunted not just for survival but for trade. The planet, which had been shaped by geological and biological forces for billions of years, was now being reshaped by a single species. This brings us to the present. The Holocene, the epoch we've lived in for the past 10,000 years, has been remarkably stable. Temperatures haven't fluctuated wildly. Ice ages haven't returned. This stability allowed human civilization to flourish. But stability is ending. We're entering what scientists call the Anthropocene. A new geological epoch defined not by ice or heat, but by human impact. The evidence is everywhere. Carbon dioxide levels in the atmosphere are higher than they've been in 3 million years. Global temperatures are rising faster than at any point in the last 10,000 years. Species are going extinct at rates 1,000 times higher than the natural background rate. The oceans are warming, acidifying, losing oxygen. Ice sheets are melting. Sea levels are climbing. Weather patterns are destabilizing. This isn't speculation. It's measured, documented, undeniable. The question isn't whether humans are changing the planet. We are. The question is what happens next. Climate change gets framed as a future problem, but it's already here. We're living through it now. Arctic ice is vanishing. Permafrost, frozen for millennia, is thawing, releasing methane. Coral reefs, ecosystems that support a quarter of all marine life, are bleaching and dying. Forests are burning with increasing frequency and intensity. Droughts are lasting longer. Storms are growing stronger. These aren't isolated events. They're connected, part of a system pushed out of balance. And unlike past climate shifts that unfolded over thousands of years, this one is happening in decades. Species can't adapt that fast. Ecosystems can't adjust. We're conducting an experiment with no control group, no way to reverse course if things go wrong. The parallels to past mass extinctions are uncomfortable. The Permian extinction, the worst in Earth's history, was triggered by volcanic eruptions that released massive amounts of carbon dioxide. The oceans warmed, became acidic, lost oxygen. 90% of species died. Today, we're releasing carbon even faster than those ancient volcanoes. Not from lava, but from burning fossil fuels, coal, oil, gas. The difference? Volcanoes couldn't turn themselves off. We can. But we're not. Not fast enough, anyway. Emissions keep rising. Temperatures keep climbing. The longer we wait, the harder it becomes to stop. Some argue technology will save us. Carbon capture, geoengineering, solutions that sound promising in theory. But technology isn't magic. It requires energy, resources, time. And even if we develop these tools, deploying them at planetary scale is another challenge entirely. Others suggest adaptation. Humans are resilient, they say. We've survived ice ages, droughts, disasters. We'll figure it out. And maybe we will. But survival isn't the same as thriving. Civilizations have collapsed before when climates shifted. The Maya, the Akkadians, societies that seemed powerful until suddenly they weren't. They didn't have global supply chains, interconnected economies, cities housing millions. We do. Which makes us more vulnerable, not less. Agriculture, the foundation of civilization, depends on stable climate. Crops need predictable rainfall, consistent temperatures, healthy soil. As climates shift, growing seasons change. Droughts strike breadbasket regions. Floods destroy harvests. Pests and diseases spread to new areas. Food security becomes fragile. When food becomes scarce, people migrate. When people migrate, tensions rise. History shows what happens when resources dwindle. Conflict. War. Collapse. We're seeing early signs already. Droughts contributing to civil wars. Floods displacing millions. Fires forcing evacuations. This is just the beginning. If temperatures rise by 2, 3, 4 degrees, the disruptions will be far worse. The ocean tells its own story. It's absorbed 90% of the excess heat we've added to the system. That sounds helpful until you realize what it means. Warmer water expands, raising sea levels. Warmer water holds less oxygen, creating dead zones. Warmer water disrupts currents that regulate global climate. The ocean isn't infinite. It has limits. We're pushing those limits. Marine ecosystems are unraveling. Fish populations are crashing. Plankton, the base of the ocean food web, are struggling. If the ocean fails, we fail. We depend on it for food, for oxygen, for climate regulation. Half the oxygen we breathe comes from ocean plankton. When we damage the ocean, we're damaging ourselves. Then there's the sixth mass extinction. We're in it now. Species are vanishing not from asteroids or volcanoes, but from habitat destruction, pollution, climate change, human activity. Every species lost is a thread pulled from the web of life. Ecosystems are resilient to a point, but redundancy has limits. Remove enough threads and the web collapses. We don't know where that point is. We won't know until we've crossed it. And once crossed, there's no going back. Extinction is permanent. The species we're losing took millions of years to evolve. They won't return in any time frame that matters to us. But here's what makes this moment different from past extinctions. We know it's happening. Past species didn't see the asteroid coming, couldn't predict the volcanic eruptions. We can see what's coming. We have the data, the models, the evidence. We understand cause and effect. That means we have a choice. We can continue on our current path, hoping technology or luck saves us. Or we can change course. The window for change is closing, but it hasn't closed yet. The next few decades will determine the trajectory of the next few centuries. What does changing course look like? It starts with energy. Fossil fuels built modern civilization, but they're killing the planet. Transitioning to renewable energy, solar, wind, hydro, isn't just possible, it's happening. Solar costs have dropped 90% in a decade. Wind power is now cheaper than coal in many places. The technology exists. What's missing is political will, investment, urgency. Every year we delay makes the transition harder and more expensive. Waiting isn't cautious. It's reckless. Transportation is another piece. Cars, planes, ships, they all burn fuel, emit carbon. Electric vehicles are spreading but not fast enough. Public transportation needs expansion. Cities need redesigning around people, not cars. Air travel is trickier. Batteries can't yet power commercial jets for long distances. That means finding alternatives, biofuels, hydrogen, or accepting that some things need to change. Maybe we fly less. Maybe we find other ways to connect. Agriculture needs transformation too. Industrial farming is a massive carbon source. Fertilizers release nitrous oxide. Livestock produce methane. Deforestation for farmland destroys carbon-absorbing forests. Sustainable farming practices exist. Regenerative agriculture, crop rotation, reduced tillage. They work. They're just not standard practice. Changing how we grow food could sequester carbon, restore soil health, support biodiversity. But it requires rethinking our entire food system. That's daunting. It's also necessary. Then there's consumption. We live in a culture of waste. Products designed to break, trends that change seasonally, convenience prized over sustainability. This isn't sustainable. Not economically, not environmentally. A circular economy, where products are designed to last, to be repaired, to be recycled, isn't utopian fantasy. It's practical necessity. Resources are finite. Treating the planet like an infinite supply depot was always going to end badly. We're reaching that end. Individual actions matter, but systemic change matters more. You can recycle, drive less, eat plant-based, and it helps. But without large-scale policy changes, corporate accountability, global cooperation, individual efforts aren't enough. Governments need to regulate emissions, subsidize clean energy, penalize pollution. Corporations need to prioritize sustainability over short-term profits. International agreements need teeth, enforcement, commitment. The Paris Agreement was a start. It's not enough. We need more ambition, more urgency, more action. This isn't about saving the planet. The planet will survive. It survived worse. Asteroid impacts, ice ages, volcanic eruptions. Earth endures. Life endures. What's at stake is human civilization. The stable climate that allowed us to build cities, grow crops, thrive. That's what's threatened. We're not fighting for the planet. We're fighting for ourselves. The stakes are enormous, but the situation isn't hopeless. Human ingenuity got us into this mess. It can get us out. We've solved massive problems before. Eradicated diseases, split atoms, sent people to the moon. We can do this too. But it requires collective effort on a scale we've never attempted. It requires reimagining how we live, how we build, how we interact with the natural world. It requires seeing ourselves not as separate from nature, but as part of it. The same rules that apply to every other species apply to us. We're not exempt from ecological limits. We're subject to them. What gives me hope? The fact that change is already happening. Renewable energy is booming. Electric vehicles are multiplying. Reforestation projects are underway. Plastic bans are spreading. Climate awareness is growing. Young people especially are demanding action, refusing to accept the world as it is. That energy, that urgency, that refusal to give up, that's what drives progress. Change doesn't come from resignation. It comes from determination. The future isn't written. It's being decided now. By the choices we make, the actions we take, the systems we build or dismantle. We're at a crossroads. One path leads to catastrophe. The other leads to adaptation, resilience, a different way of living. Neither path is easy, but one is survivable. The question is whether we have the courage to take it. So what does taking that path actually look like? Not in abstract terms, but in concrete reality. Start with infrastructure. Cities aren't just collections of buildings. They're systems. Transportation, energy, water, waste. Every component connects. Redesigning them isn't about tearing everything down and starting over. It's about strategic retrofitting, smart planning, gradual transformation. Copenhagen didn't become a cycling capital overnight. It invested in bike lanes, prioritized pedestrians, made cars less convenient. Now cycling is faster, easier, safer than driving. That didn't require futuristic technology. It required political will and urban planning. Other cities can replicate that. Many are trying. The results speak for themselves. Less congestion, cleaner air, healthier populations. It works because it addresses the system, not just individual behavior. Energy grids need similar thinking. Centralized power plants feeding vast networks made sense when fossil fuels were cheap and climate impacts were ignored. That model is outdated. Distributed generation, microgrids, localized storage, these aren't fringe concepts anymore. They're practical solutions being implemented globally. A neighborhood with solar panels, battery storage, smart meters can generate its own power, share excess with the grid, reduce transmission losses. Scale that up. Communities, cities, regions. The technology exists. The barriers are regulatory, financial, political. Those can be overcome. They're being overcome. Slowly, unevenly, but steadily. Buildings themselves offer enormous potential. Most existing structures are energy sieves. Heat escapes in winter, enters in summer, requiring constant heating and cooling. Retrofitting with insulation, efficient windows, smart thermostats cuts energy use dramatically. New buildings can be designed to passive house standards, requiring minimal heating or cooling. Green roofs absorb rainwater, reduce urban heat islands, provide insulation. These aren't experimental ideas. They're established practices. The challenge is making them standard, not optional. Transportation is harder because it's so embedded in how we live. Sprawling suburbs designed around cars can't be fixed with bike lanes alone. But they can be densified, connected with public transit, integrated with mixed-use development. That takes time. Decades, not years. But the alternative is continuing a pattern that's unsustainable and increasingly unaffordable. Electric vehicles help, but they're not a complete solution. Fewer cars overall, more shared mobility, better urban design, these matter just as much. A city where you can walk to work, bike to the store, take a train across town, that's a city that doesn't need everyone to own a car. That's a city with lower emissions, less traffic, more livable public spaces. Agriculture presents its own complexities. Industrial farming feeds billions, but at a cost. Soil degradation, water depletion, chemical runoff, greenhouse gas emissions. Alternatives exist. Agroforestry integrates trees into farms, improving soil, sequestering carbon, supporting biodiversity. Precision agriculture uses data to apply fertilizers and pesticides only where needed, reducing waste and runoff. Vertical farming grows food in controlled environments, using less water and land. These methods aren't universally applicable. Some work better in certain climates, for certain crops, at certain scales. But collectively, they represent a shift toward farming that works with ecosystems, not against them. Diet matters too. Meat production, particularly beef, is resource-intensive. Massive land use, water consumption, methane emissions. Reducing meat consumption, especially in wealthy countries where intake is highest, would significantly lower agriculture's climate impact. That doesn't mean everyone needs to go vegan. It means shifting toward plant-heavy diets, treating meat as occasional rather than constant, valuing quality over quantity. Cultural resistance to this is real. Food is identity, tradition, comfort. But cultures evolve. Diets have changed throughout history. They can change again. Waste is another frontier. Linear economy models, take, make, dispose, are fundamentally flawed. Resources extracted, products made, waste generated, repeat. That's not sustainable with finite resources and limited disposal options. Circular economy principles, designed for durability, repairability, recyclability, close the loop. Products become resources for new products. Waste is minimized. This requires rethinking manufacturing, incentivizing longevity over obsolescence, creating systems for collection and reprocessing. Some companies are moving this direction. Not many, not fast enough, but it's starting. Consumer demand can accelerate it. Regulations can mandate it. Technology will play a role, but it's not a magic bullet. Carbon capture, geoengineering, fusion power, these are often presented as future solutions that will fix everything. Maybe they will. Maybe they won't. Banking on unproven technologies while delaying action on proven solutions is reckless. We need to deploy what works now while continuing to innovate. Solar and wind are proven. Batteries are improving rapidly. Electric vehicles are viable. Efficient buildings are standard practice in some places. These aren't waiting for breakthroughs. They're waiting for adoption. Finance is crucial. Climate action requires investment. Trillions, not billions. That sounds impossible until you consider how much is already spent on fossil fuel subsidies, military budgets, bank bailouts. It's not about finding new money. It's about redirecting existing flows. Subsidizing clean energy instead of coal. Investing in public transit instead of highways. funding efficiency retrofits instead of new power plants. The money exists. The question is priorities. International cooperation is essential. Climate change doesn't respect borders. Emissions anywhere affect everywhere. Wealthy nations, which industrialized first and contributed most to historical emissions, have a responsibility to lead and support developing nations in transitioning sustainably. That means technology transfer, financial assistance, capacity building. Not charity. Justice. The global north profited from fossil fuels. The global south shouldn't have to choose between development and climate stability. Green technology should be accessible, not locked behind patents and profit margins. Policy mechanisms matter. Carbon pricing, cap and trade, regulations, subsidies, these aren't abstract economic theories. They're tools that change behavior at scale. Make pollution expensive, clean alternatives cheap, and markets respond. This isn't about controlling every aspect of life. It's about correcting market failures, internalizing costs that have been externalized onto the environment and future generations. Social equity can't be ignored. Climate impacts hit the poorest hardest. They have the least resources to adapt, the least responsibility for emissions, the most to lose. Climate action that ignores this isn't just unfair. It's unstable. Transitions need to be just, supporting workers and communities dependent on fossil fuel industries, ensuring benefits are widely shared, not concentrated among the already privileged. Education and communication are foundational. Understanding climate science, recognizing misinformation, evaluating solutions, these skills matter. A population that understands the stakes and the options can demand better from leaders and corporations. Misinformation is pervasive, well-funded, deliberately confusing. Countering it requires clarity, patience, credibility. Science communication isn't about dumbing down. It's about translating complexity without losing accuracy. Political engagement is non-negotiable. Voting, advocacy, activism, these drive policy. Elected officials respond to pressure. Corporations respond to regulation and consumer demand. Change at scale requires political power, and political power comes from organized, persistent effort. Cynicism is a luxury we can't afford. Systems feel immovable until they move. History is full of rapid transformations that seemed impossible until they happened. Individual actions still matter, not because they'll solve the crisis alone, but because they reinforce commitment, build habits, create culture. Choosing public transit, reducing consumption, supporting sustainable businesses, these aren't futile gestures. They're part of a broader shift. Culture changes when enough people change. Norms shift. What was unusual becomes common. What was accepted becomes unacceptable. The path forward isn't linear or easy. There will be setbacks, resistance, failures. Progress is messy. But the alternative, continuing as we are, isn't an option. The climate is changing regardless of what we do now. The question is how much, How fast, how catastrophically. Every fraction of a degree matters. Every ton of emissions avoided matters. Every policy implemented, every technology deployed, every behavior shifted, they add up. This isn't about returning to some imagined past. Pre-industrial life wasn't idyllic. It was hard, short, limited. Progress is real. Technology improves lives. The goal isn't reversal. It's redirection. Using our capabilities wisely, building systems that work long-term, creating prosperity that doesn't come at the expense of future generations. That's not naive optimism. It's pragmatic survival. We've been here before, facing existential threats that seemed insurmountable. Ozone depletion, acid rain, lead poisoning. CFCs were banned. Emissions were regulated. Leaded gasoline was phased out. These weren't easy wins. They required science, advocacy, international cooperation, political courage. But they happened. The ozone layer is recovering. Lakes are healing. Air is cleaner. These victories prove that large-scale environmental problems can be solved when there's will to act. Climate change is bigger, more complex, more entrenched in global systems. But the principles remain. Identify the problem. Understand the solutions. Build political will. Implement policy. Adapt as you learn. It's not hopeless. It's hard. There's a difference. The future being decided now isn't predetermined. It's being shaped by choices made today, tomorrow, next year. By governments, corporations, communities, individuals. Every decision point is an opportunity. Every setback is temporary unless we surrender. The question isn't whether we can avoid all impacts. We can't. Some are already locked in. The question is whether we limit them, adapt to them, build resilience against them. Whether we create a world that's livable, stable, just. That's the path worth taking. Not because it's easy or guaranteed, but because it's necessary and possible. The courage required isn't superhuman. It's simply human. The willingness to face hard truths, make difficult changes, work towards something larger than immediate comfort. That's always been how progress happens. This time is no different. Except the stakes are everything. The Triassic, Jurassic, and Cretaceous weren't just chapters in a textbook. They were experiments. Tests of what's possible when life is given time, pressure, and an unstable planet to work with. Dinosaurs dominated for 165 million years. Humans have been around for maybe 300,000. We're not the pinnacle. We're just the latest iteration. And if the past teaches anything, it's that dominance is temporary. Every extinction event, every climate shift, every asteroid impact, they all reset the board. What survives isn't always the strongest or the smartest. It's the most adaptable. The ones that can shift when the world shifts. Dinosaurs thrived until they couldn't. Mammals waited in the margins until their moment came. The lesson isn't that we're special. It's that nothing is permanent. Right now, we're living through a transition as significant as any in Earth's history. Not because of volcanoes or asteroids, but because of us. We've become a geological force. Our impact is measurable in ice cores, ocean chemistry, atmospheric composition. Future geologists will. 41 light-years from Earth, there's a world where rocks don't just melt, they vaporize. Where the surface glows brighter than molten steel. Where an entire year passes in less time than it takes you to sleep through the night. This is 55 Cancri, and according to everything we thought we knew about planetary science, it shouldn't have an atmosphere. It shouldn't be able to hold on to gases at all. Yet somehow, against every prediction, it does. The discovery announced in May 2024 changed the game completely. Let's start with something that sounds impossible. Imagine a planet twice the size of Earth, but 8 times heavier. Now place it so close to its star that it completes an orbit in just 17.7 hours. The planet's surface temperature reaches 3,770 Kelvin on the side facing the star. That's 6,330 degrees Fahrenheit. Hot enough to turn silicon, iron, aluminum, and calcium into vapor. The night side, perpetually locked in darkness, still glows at temperatures exceeding 2,000 degrees Fahrenheit. This isn't science fiction. This is 55 Cancri, officially named Janssen, and it represents one of the most extreme environments ever confirmed to exist. The planet orbits a Sun-like star designated 55 Cancri A, located in the constellation Cancer. When astronomers first detected it using data from 2003 and 2004, they had no idea what they'd found. At the time of its announcement in 2004, Janssen became the first super-Earth ever discovered around a main sequence star. Nothing in our solar system prepared us for this. We have rocky planets like Earth and Mars. We have gas giants like Jupiter and Saturn. But we have nothing that bridges the gap quite like this, a world that defies our categories and challenges our models of how planets form and survive. The numbers tell a story of extremes that push physics to its limits. Janssen orbits at just 1.4 million miles from its host star. To put that in perspective, Mercury, the closest planet to our Sun, orbits at roughly 36 million miles. Janssen is 25 times closer to its star than Mercury is to ours. At this distance, the gravitational forces and radiation levels would absolutely devastate any world in our solar system. What happens to a planet in such proximity? It becomes tidally locked. One hemisphere eternally faces the star, baking under relentless radiation. The other faces the void of space, never seeing direct starlight. This creates a planetary environment unlike anything we experience on Earth, a world split between fire and relative cold, though even that cold side maintains temperatures that would instantly incinerate any known form of life. Early observations using the Spitzer Space Telescope between June and July of 2013 revealed something strange. The hottest spot on the planet wasn't where it should be. On a tidally locked world with no atmosphere, you'd expect the point directly facing the star, the substellar point, to be the hottest location. But measurements showed the peak temperature shifted 30 to 41 degrees eastward from where physics said it should be. Something was moving heat around. But what? Scientists initially proposed two possibilities. Either the planet had an atmosphere capable of redistributing thermal energy through winds, or something else entirely was at work, perhaps exotic rotational dynamics or internal heat transport through the planet's presumed magma ocean. For years, the debate remained unresolved. Spitzer's instruments, though revolutionary for their time, couldn't provide the spectral resolution needed to definitively answer the question. Then came the James Webb Space Telescope. Between its near-infrared camera and mid-infrared instrument, Webb possessed capabilities that transformed exoplanet science. In observations that each lasted about 8 hours, the telescope measured subtle changes in infrared light as Janssen orbited its star. The technique, called secondary eclipse spectroscopy, works by capturing the combined light of the star and planet, then subtracting out the star's light alone when the planet passes behind it. What remains is the planet's own thermal emission, its heat signature, carrying information about atmospheric composition encoded in specific wavelengths. The precision required for these measurements is staggering. Janssen's thermal emission is utterly dwarfed by the brightness of its host star. Isolating that faint planetary signal demands not just sensitive instruments, but sophisticated data analysis techniques that can tease apart overlapping spectral features. Multiple observations were necessary to build sufficient signal-to-noise ratios and check for consistency. When the team analyzed the data, they found patterns that shouldn't exist. Between 4 and 5 microns in the infrared spectrum, less light reached the telescope than expected. This dip, this absorption feature, pointed to something specific: molecules in the planet's atmosphere absorbing those particular wavelengths. The spectral signature matched carbon dioxide or carbon monoxide. Not vaporized rock, which would show a completely different pattern, but actual volatile gases. The kind of atmosphere you'd associate with volcanic outgassing, not a bare molten surface. This was the moment everything changed. For decades, atmospheric scientists operated under a firm assumption: rocky planets orbiting this close to their stars simply cannot maintain atmospheres. The physics seemed straightforward. Intense stellar radiation should strip away gases through atmospheric escape, where high-energy photons give molecules enough kinetic energy to overcome the planet's gravity and flee into space. At Janssen's orbital distance, this process should be devastating and continuous. Yet here was evidence, the strongest to date, that a rocky exoplanet beyond our solar system possesses a genuine atmosphere. Not rock vapor. Not a tenuous envelope of evaporated minerals. An actual secondary atmosphere, likely rich in carbon-bearing molecules, persisting despite conditions that should obliterate it. The discovery paper, published in Nature in May 2024, was unequivocal. The measurements ruled out the hypothesis that Janssen is simply a lava world shrouded in vaporized rock. Instead, the data indicated what researchers call the bona fide volatile atmosphere, one that's continuously replenished by outgassing from below. This is where the magma ocean hypothesis enters the picture. Scientists believe Janssen's interior remains so hot that vast portions of its mantle exist in a molten state. Temperatures and pressures keep enormous quantities of rock liquefied. As this magma ocean churns through convection, driven by the extreme temperature gradient between day and night hemispheres, dissolved gases bubble up and escape through volcanic activity. Think of it like champagne releasing carbon dioxide, but on a planetary scale with molten rock instead of wine. The outgassing rate apparently matches or exceeds the rate of atmospheric loss to space, creating a dynamic equilibrium. Gases escape. More gases bubble up. The atmosphere persists not because it's stable, but because it's continuously renewed, a planetary system maintaining itself against impossible odds through sheer volcanic vigor. Renyu Hu, a planetary scientist at the California Institute of Technology, pointed out something profound about this discovery. By observing this extrasolar example of atmosphere-magma interaction, we gain insights into how the early solar system worked. Earth itself, during the first 100 million years after formation, would have been hot enough to maintain widespread magma oceans. Venus likely experienced similar conditions. Mars too. Studying Janssen gives us a window into processes that shaped our own world billions of years ago, except we're watching them unfold in real time rather than trying to reconstruct them from ancient geological records. The implications extend far beyond one peculiar planet. If rocky worlds can maintain atmospheres under such extreme conditions, what does that mean for our understanding of planetary habitability? What does it tell us about the diversity of rocky planet evolution? The conventional wisdom just took a serious hit, and scientists are racing to understand the mechanisms that make this possible. But there's more to this story. The controversy surrounding Janssen's very existence reveals how challenging exoplanet science can be, and how easily initial observations can mislead us. When astronomers first analyzed the radial velocity data that revealed Janssen's presence, they thought they'd found a planet with a 2.8-day orbital period. This measurement stood for years, shaping early models of the 55 Cancri system. Then in 2005, researcher Jack Wisdom questioned the planet's existence entirely, suggesting the signal was an alias, a false pattern created by the way the data was sampled. The debate intensified. Some analyses seemed to confirm the 2.8-day planet. Others cast doubt. Finally, in 2010, researchers Dawson and Fabrici demonstrated conclusively that the true orbital period was 0.7365 days. Not 2.8 days. Less than 18 hours. The planet was real, but it was far closer to its star than anyone had imagined. This correction wasn't just a minor adjustment. It fundamentally transformed our understanding of Janssen's environment, moving it from merely very close to extraordinarily close, from extreme to apocalyptic. When the planet's transit across its host star was finally observed and confirmed in April 2011 using the MOST Space Telescope, it vindicated Dawson and Fabrici's work and opened the door to direct characterization of the planet's properties. Transit observations are crucial because they let astronomers measure a planet's radius directly by watching how much starlight it blocks. Combined with mass measurements from radial velocity data, this enables calculation of density, a fundamental clue about internal composition. For Janssen, the density measurements revealed a world unlike anything in our solar system, setting the stage for decades of follow-up observations that would culminate in the James Webb Space Telescope's groundbreaking atmospheric detection. Now we understand that Janssen represents something extraordinary, a natural laboratory where planetary science meets its most extreme test case. The discovery of its atmosphere forces us to reconsider fundamental assumptions about what's possible in the universe. And the story of how we came to understand this world reveals the messy, contentious, ultimately triumphant process of scientific discovery itself. What we're learning is that the universe doesn't care about our assumptions. It will create worlds we never imagined, operating under conditions we thought impossible. Janssen is just the beginning. The temperature measurements tell a story that defies intuition. Janssen's dayside reaches 3700 Kelvin according to the latest Spitzer data reanalysis from 2022. That's 6300 degrees Fahrenheit. Hot enough to vaporize calcium. Silicon boils at these temperatures. Iron exists as vapor, not metal. We're not talking about a place where rocks melt, we're describing conditions where the distinction between solid, liquid, and gas becomes almost meaningless for materials we think of as permanent. The night side presents its own puzzle. Even though this hemisphere never sees direct starlight, it maintains temperatures around 1400 Kelvin. That's 2000 degrees Fahrenheit. Glowing red-hot in perpetual darkness. Something is redistributing heat across this world with remarkable efficiency, and for years scientists couldn't agree on what that something was. Here's where things get genuinely strange. When the Spitzer Space Telescope mapped Jansen's thermal emissions between June and July 2013, astronomers expected the hottest spot to align with the substellar point, the location directly facing the star. Basic physics suggested that's where maximum heating should occur. Instead, they found the temperature peak offset by 30 to 41 degrees eastward. 30 degrees doesn't sound dramatic until you realize what it implies. That offset means heat is being transported across the planet's surface through some active mechanism. Atmospheric winds could explain this. But so could more exotic phenomena involving the planet's rotation or internal dynamics. The offset is too large to dismiss as measurement error, yet too consistent to be random variation. Think about what this redistribution requires. You need energy transport powerful enough to shift the thermal maximum across hundreds of kilometers of surface. On Earth, our atmosphere and oceans accomplish this through convection and circulation patterns. But Jansen's environment is so extreme that conventional atmospheric models struggle to explain how gases could survive long enough to establish stable circulation. The debate raged for years. One camp argued the planet must have an atmosphere despite the hostile conditions. How else could you explain the heat distribution? The offset hotspot? The surprisingly moderate nightside temperatures? Another group countered that we were simply seeing vaporized rock, a tenuous shroud of silicon, iron, aluminum, and calcium boiled directly off the surface. At Jansen's temperatures, rocks don't just melt. They evaporate. This rock vapor could create something atmosphere-like without being a true secondary atmosphere. Distinguishing between these scenarios became crucial. A rock vapor envelope would form from the planet's own surface material, constantly replenished as long as temperatures stayed extreme. It's not really an atmosphere in the traditional sense, more like the haze above a boiling pot. A true secondary atmosphere would require ongoing volcanic outgassing from the interior, implying active geological processes and a fundamentally different planetary state. The Spitzer observations provided tantalizing clues but lacked the spectral resolution to definitively settle the question. Infrared brightness measurements showed patterns inconsistent with a bare rock surface, suggesting some kind of gaseous envelope. Yet the data couldn't identify specific molecular signatures that would prove the presence of volatile compounds like carbon dioxide or carbon monoxide. Scientists needed better instruments. They needed precision spectroscopy capable of detecting absorption features from specific molecules. They needed observations that could distinguish between the spectral signature of vaporized rock elements and actual atmospheric gases. Enter the James Webb Space Telescope. Webb's near-infrared camera and mid-infrared instrument can measure thermal emission spectra with unprecedented detail. The observing strategy was elegant. Watch Jansen complete multiple orbits, capturing data when the planet is visible beside its star and when it disappears behind the star during secondary eclipse. During eclipse, you're seeing only starlight. Before and after eclipse, you're seeing starlight plus the planet's own thermal glow. Subtract one from the other, and you isolate the planet's emission spectrum. Each observation session lasted about 8 hours, covering nearly half of Jansen's 17.7-hour orbital period. The precision required is extraordinary. The planet's thermal emission is utterly dwarfed by the star's brightness, like trying to detect a candle next to a searchlight. Multiple observations were necessary to build sufficient signal-to-noise ratio and verify consistency across different orbital phases. When the team analyzed Webb's NIRCan data in 2024, they saw something unmistakable. A dip in the spectrum between 4 and 5 microns. Less light reaching the telescope at these specific wavelengths. This wasn't random noise or instrumental artifact. This was absorption. Something in the planet's atmosphere was absorbing infrared light at wavelengths characteristic of carbon-bearing molecules. Aaron Bellerouf from JPL explained the significance. That spectral dip suggests carbon monoxide or carbon dioxide, both of which absorb strongly in this wavelength range. The MIRI data extending from 5 to 12 microns confirmed the pattern. This wasn't vaporized rock. Silicon, iron, aluminum, and calcium would produce completely different spectral signatures. What Webb detected pointed unambiguously toward volatile compounds, gases you'd expect from volcanic emissions, not from evaporated surface material. The implications hit immediately. Janssen has a bona fide atmosphere. Not rock vapor. Not a temporary artifact of extreme heating. An actual secondary atmosphere likely rich in carbon dioxide or carbon monoxide, probably both. Gases that had to come from somewhere, that had to be continuously replenished against the relentless stripping force of stellar radiation. This shouldn't work. Conventional planetary science said rocky planets this close to their stars couldn't maintain atmospheres. The radiation environment is too hostile. High-energy photons should give atmospheric molecules enough kinetic energy to escape the planet's gravity entirely. Atmospheric escape should strip away any gases within geologically short timescales. Yet here's Janssen, maintaining an atmosphere despite conditions that should make retention impossible. The answer lies beneath the surface. Renyu Hu from Caltech explained the likely mechanism. The atmosphere isn't primordial, it's a secondary atmosphere, constantly regenerated by outgassing from a magma ocean. Imagine the entire planetary mantle in a molten state. Temperatures and pressures high enough to keep vast quantities of rock liquid. As this magma churns and convects, dissolved gases bubble out, similar to carbon dioxide escaping from champagne. This outgassing process creates a dynamic equilibrium. Yes, the stellar wind strips atmosphere away. But volcanic emissions from the magma ocean replenish it at rates matching or exceeding the loss. It's not a stable atmosphere in the sense of Earth's, it's a constantly refreshed envelope of gas maintained by ongoing geological activity. The magma ocean model explains multiple observations simultaneously. The heat redistribution. Convection in the molten mantle transports thermal energy. The offset hotspot. Preferential outgassing on the dayside creates atmospheric circulation patterns. The nightside warmth. Heat from the interior prevents complete cooling even in permanent darkness. Computer simulations of Janssen's interior dynamics reveal fascinating complexity. Using surface temperature contrasts as boundary conditions, researchers modeled two-dimensional mantle convection under different climate scenarios. If the dayside hosts a full magma ocean while the nightside remains solid or only partially molten, large superplumes form on the day hemisphere. Hot material rises in massive upwellings. Cold material descends on the nightside, though without forming strong downwelling structures. In some simulations, the superplume shifts tens of degrees toward the terminator, the boundary between day and night. This asymmetric convection could drive preferential outgassing on one hemisphere, potentially creating atmospheric composition gradients between dayside and nightside. Different gases on different hemispheres. Chemical stratification driven by the extreme temperature gradient. What makes this discovery genuinely revolutionary isn't just confirming the atmosphere's existence. It's demonstrating that our understanding of planetary atmospheres was too narrow. We built theories based on solar system examples: Earth, Venus, Mars, the gas giants. None of those worlds experience conditions remotely like Janssen's. We assumed extrapolation would work. The universe just proved otherwise. Diana Dragomir from the University of New Mexico, who contributed to discovering Jansen's transits during her doctoral work, emphasized the broader implications. This challenges fundamental assumptions about what's possible. If rocky planets can maintain atmospheres under such punishment, what does that mean for planetary habitability elsewhere? What does it reveal about the diversity of rocky planet evolution? The magma-ocean mechanism opens new questions. How common are lava worlds in the galaxy? Do other ultra-hot rocky planets maintain similar atmospheres? Could there be a whole class of worlds we've completely overlooked because we assumed atmospheric retention was impossible under extreme stellar radiation? Jansen gives us a window into processes that shaped Earth billions of years ago. Our planet spent its first 100 million years hot enough to maintain widespread magma oceans. Venus likely went through similar phases. Mars too. But we can't observe those ancient conditions directly, we're stuck reconstructing them from geological traces. Jansen lets us watch in real time, studying atmosphere-magma interactions as they happen rather than inferring them from billion-year-old rocks. The implications extend beyond theoretical interest in planetary science. Understanding how rocky planets retain atmospheres under extreme radiation could reshape our approach to finding habitable worlds. Current habitability models focus on moderate environments, Earth-like distances from Sun-like stars. But what if that framework is too conservative? Consider red dwarf stars. They make up roughly 70% of all stars in the galaxy. Most known exoplanets orbit red dwarfs. And red dwarfs present a problem. Their habitable zones, where liquid water could exist, sit uncomfortably close to the star. Close enough that stellar flares and radiation would seemingly strip away atmospheres. Conventional wisdom suggested rocky planets around red dwarfs couldn't maintain the atmospheric protection necessary for life. Jansen changes that calculation. If a world can hold on to an atmosphere while orbiting at 1/25 Mercury's distance from a Sun-like star, while enduring temperatures that vaporize rock, then maybe our assumptions about red dwarf habitability need revision. The mechanisms keeping Jansen's atmosphere intact might operate elsewhere. Different scales, different temperatures, but the same fundamental principle: continuous replenishment overcoming atmospheric loss. This doesn't make Jansen habitable. Nothing lives at 3,700 Kelvin. But it proves atmospheric retention works under conditions we thought impossible. And that matters when searching for life beyond Earth. The detection methods used for Jansen also demonstrate how far exoplanet characterization has advanced. Webb's instruments measured infrared light in the 4 to 12 micron range. Each 8-hour observation captured nearly half the planet's orbital period. The planet completes a full orbit in under 18 hours. That rapid orbit initially seemed like a disadvantage, less time for detailed observation. But it actually helps. Multiple orbits can be observed in a single observing session, allowing astronomers to build up signal strength and check for consistency. The secondary eclipse method Webb employed is deceptively simple in concept. Measure the combined light from star and planet. Wait until the planet passes behind the star. Measure just the star. Subtract. What remains is the planet's thermal emission. Simple in theory. Extraordinarily difficult in practice. The planet's contribution to total system brightness is minuscule. Like trying to detect a candle next to a searchlight from 41 light-years away. And not just detect it, measure its color spectrum precisely enough to identify specific molecules. Aaron Belorov from JPL pointed out the telltale signature, a dip in the spectrum between 4 and 5 microns. That's where carbon monoxide and carbon dioxide absorb infrared light. If the planet were surrounded by vaporized rock, silicon and iron compounds would create completely different absorption features. The spectrum doesn't match rock vapor. It matches volatile gases. This distinction matters because it confirms the magma ocean model over alternatives. Some researchers have proposed that Janssen might be a bare rock world with a thin envelope of evaporated surface material. Under that scenario, the planet would essentially be sweating rock vapor. Silicon, iron, aluminum, the elements that make up planetary crust, would evaporate from the day side and circulate before condensing on the night side. That could explain some observations but struggle to account for the heat redistribution patterns and the stability of the thermal emission over time. The volatile atmosphere model fits better. Carbon dioxide or carbon monoxide released from interior outgassing creates a genuine atmosphere, not just surface evaporation. This atmosphere can transport heat through winds and circulation patterns. It can maintain relatively stable composition despite continuous loss to space because volcanic activity keeps replenishing it. And it explains why the planet's thermal emission shows less variability than expected for a bare rock surface. But questions remain. The atmosphere's exact composition remains uncertain. Is it primarily carbon dioxide? Carbon monoxide? Some mixture? Do other gases contribute significantly? Nitrogen, sulfur compounds, even water vapor from the magma ocean? Webb's current observations can't fully resolve this. Future observations with longer integration times and coverage of additional wavelengths could narrow the possibilities. The planet's internal structure also invites speculation. Standard rocky planet models don't apply straightforwardly. At the temperatures and pressures inside Janssen, rock doesn't behave like rock on Earth. Phase diagrams, the charts showing which states of matter exist under different conditions, become exotic at these extremes. Materials that normally form solid minerals might exist as superionic phases, where some atoms remain locked in crystal lattices while others flow freely like liquids. Bizarre states of matter that laboratories can barely reproduce. Some research suggests Janssen might have a carbon-rich composition rather than the silicon and oxygen-dominated chemistry of Earth-like planets. The host star, 55 Cancri A, shows elevated carbon abundance in its spectrum. If the protoplanetary disk that formed the system was similarly carbon-rich, planets might have incorporated more carbon than typical solar system bodies. Under the extreme pressures in Janssen's interior, that carbon could crystallize into diamond. This sparked the diamond planet hypothesis, the idea that Janssen's mantle might contain diamond layers hundreds of kilometers thick. It's a tantalizing possibility. The temperatures and pressures are certainly sufficient. Pure carbon at those conditions would form diamond. Whether Janssen actually contains enough carbon, and whether it's distributed in ways that allow large-scale diamond formation, remains speculative. But the chemistry isn't impossible. Density measurements provide some constraints. Janssen is roughly 8 times Earth's mass and twice Earth's radius. That gives a density of about 7 grams per cubic centimeter, higher than Earth's average density of 5.5 grams per cubic centimeter. Higher density suggests either more iron in the core or a compressed structure from the planet's gravity. Or both. It doesn't definitively prove or disprove the diamond hypothesis, but it's consistent with various compositional models. The planet's thermal variability adds another layer of mystery. Observations show the planet's brightness changes over time, not just the expected variations as it orbits, but longer-term fluctuations that suggest surface conditions aren't static. One explanation invokes massive volcanic eruptions. Picture Mount St. Helens scaled up by factors of thousands. Eruptions violent enough to inject vast dust clouds into the atmosphere, temporarily blocking thermal emission and changing the planet's apparent brightness. When the dust settles or gets swept away by atmospheric winds, brightness returns to baseline. Alternatively, the variability might come from a gas torus co-orbiting with the planet. Similar to Jupiter's Io plasma torus, a donut-shaped cloud of charged particles surrounding Jupiter in Io's orbit. Io's intense volcanic activity feeds this torus. If Janssen experiences similarly vigorous outgassing, it could create a surrounding cloud of material that periodically obscures or enhances the planet's thermal signature as viewed from Earth. Both explanations require extreme levels of geological activity. But Janssen is extreme in every measurable way, so neither scenario seems implausible. Scientists have also searched for electromagnetic interactions between Janssen and its host star. The planet orbits so close that it sits deep within the star's magnetic field. Jupiter's moon Io creates a magnetic footprint on Jupiter through electromagnetic coupling. Charged particles from Io's volcanoes interact with Jupiter's magnetic field, generating radio emissions. Similar interactions might occur between Janssen and 55 Cancri. Radio observations in 2011 looked for these signals. Nothing detected. Either the interactions don't occur at detectable strength, or the observation methods weren't sensitive enough. The null result also suggests Janssen might lack a strong intrinsic magnetic field. Earth's magnetic field is generated by convection in its liquid iron core. Janssen's interior temperatures might prevent the kind of convection needed for dynamo action. Or perhaps the magma ocean itself disrupts magnetic field generation. Without a protective magnetosphere, atmospheric loss to stellar wind should be even more severe. Yet the atmosphere persists. That persistence keeps circling back as the central puzzle. Everything about Janssen's environment should doom any atmosphere. The stellar radiation. The lack of magnetic protection. The intense gravitational forces from tidal locking. The evaporation driven by surface temperatures exceeding 3000 Kelvin. Yet there it is, carbon-bearing gases surrounding a world that shouldn't have them. The magma ocean mechanism explains how, but raises its own questions. How deep is the magma ocean? Does it cover the entire planet or just the day side? What's the composition of the molten material? Is it similar to Earth's mantle composition, or something more exotic? How efficiently does convection operate under these extreme conditions? And most intriguingly, does the night side have fundamentally different conditions that might create chemical gradients in the atmosphere? That last question touches on something particularly fascinating about tidally locked worlds. The permanent day and night hemispheres create environments so different they might as well be separate planets. One side continuously blasted by stellar radiation, the other side in eternal darkness. The atmospheric dynamics between these two faces would be extraordinary. If an atmosphere exists, and we now know it does, winds must connect the hemispheres. Heat from the day side gets transported toward the night side through atmospheric circulation. But how efficiently? That depends on wind speeds, atmospheric density, and the atmosphere's chemical makeup. Computer models of tidally locked planets suggest wind patterns unlike anything on Earth. Instead of the Coriolis-driven circulation cells we're familiar with, tidally locked worlds develop what's called a superrotating jet, a continuous high-altitude wind stream that flows eastward around the planet at tremendous speed. This jet would redistribute heat, carrying energy from the scorching day side toward the cooler night side. On Janssen, these winds might reach hundreds or even thousands of meters per second. Hypersonic winds sculpting temperature gradients that would be lethal in either direction. Standing on the day side would be like facing a blast furnace. Standing on the night side would still be hot enough to melt lead, but relatively speaking, comparatively mild. The terminator, the boundary between day and night, becomes the most interesting region. Here, conditions transition from one extreme to another. Temperature gradients drive powerful convection. Rising air from the day side meets descending air from the night side. Turbulence would be constant and violent. If life were ever to exist on such a world, and it can't on Janssen, but theoretically on cooler tidally locked planets, the terminator would be the only survivable zone. Not too hot, not too cold. Though on Janssen, even the terminator remains far above the boiling point of water. Computer simulations of Janssen's interior reveal mantle dynamics that would reshape our understanding of planetary geology. The extreme temperature difference between hemispheres creates asymmetric convection patterns. Hot magma rises on the day side, forming massive plumes. These aren't small volcanic features, they're continent-sized upwellings of molten rock pushing toward the surface. On the night side, cooler material descends. Though cooler is relative, it's still thousands of degrees. These descending flows complete the convection cell, driving circulation through the planet's mantle. The entire planet becomes a heat engine, powered by the temperature differential its tidal locking creates. The dayside plumes can shift position. In some models, they migrate tens of degrees toward the terminator. This movement would create varying volcanic activity across the dayside, with hotspots appearing and disappearing over time. If volcanic outgassing is concentrated in these plume regions, atmospheric composition might vary geographically. The atmosphere near the strongest plume would be richer in freshly outgassed volatiles. Regions away from active plumes would have older, more processed atmospheric chemistry. This brings up something fascinating about Janssen's atmosphere. It's not static, it's being constantly renewed. Every second, stellar radiation strips away gases on the day side. High-energy photons and stellar wind particles collide with atmospheric molecules, giving them enough velocity to escape Janssen's gravity. The atmosphere bleeds into space continuously, yet it persists. The magma ocean replenishes what's lost. Dissolved gases in the molten rock bubble to the surface through volcanic vents. The same process that created Earth's early atmosphere 4 billion years ago continues on Janssen today. It's a dynamic equilibrium, loss balanced by supply. Remove either factor and the atmosphere would either grow indefinitely or disappear completely. This equilibrium is delicate. Small changes in volcanic activity or stellar radiation could tip the balance. If volcanic outgassing slows, atmospheric loss would gradually thin the atmosphere. If stellar activity increases during a flare, temporary atmospheric stripping could occur before volcanic replenishment catches up. The atmosphere's composition reflects this balance. Carbon dioxide and carbon monoxide dominate because they're stable enough to survive in this environment and abundant in volcanic emissions. Other gases present in smaller quantities might include sulfur dioxide, water vapor, and various rock-derived species. But the carbon-bearing molecules dominate the spectral signature Webb detected. Water deserves special attention. Earth's magma contains dissolved water that outgasses during eruptions. Janssen's magma ocean likely contains water too. But at dayside surface temperatures, water can't exist as liquid. It would immediately vaporize. Even on the night side, temperatures remain too high for liquid water. Any water in Janssen's atmosphere exists as superheated steam. This steam contributes to the greenhouse effect. Water vapor is an excellent absorber of infrared radiation. Even in small quantities, it would trap heat, contributing to the night side surprisingly high temperatures. The night side doesn't cool as much as bare rock calculations would suggest, partly because atmospheric circulation brings heat from the day side, and partly because greenhouse gases trap what little heat remains. The vertical structure of Jansen's atmosphere adds another layer of complexity. Near the surface, the atmosphere is dense and hot. Pressure increases with depth into the magma ocean until there's no clear boundary between atmosphere and planet, just a gradual transition from gas to liquid to solid as you descend. Higher up, the atmosphere thins. Temperature remains high due to stellar radiation, but pressure drops. At some altitude, the atmosphere becomes thin enough that molecules can escape to space. This exosphere marks the fuzzy edge of Jansen's atmosphere, where the planet ends and space begins. Comparing Jansen to early Earth reveals profound connections. When Earth formed 4.5 billion years ago, the entire surface was molten. Impacts during planetary formation delivered enough energy to melt rock globally. The early Earth was a magma ocean world, probably tidally locked to the moon before tidal forces gradually slowed Earth's rotation. During this period, Earth's atmosphere came from volcanic outgassing. Carbon dioxide, water vapor, nitrogen, and other volcanic gases accumulated. The atmosphere was thick, hot, and utterly hostile to modern life. But it was the starting point for everything that followed. As Earth cooled, the magma ocean solidified. Water vapor condensed into oceans. Chemistry became more complex. Studying Jansen gives us a laboratory for understanding that crucial phase. We can't travel back 4 billion years, but we can observe a world currently in a state Earth once occupied. The processes happening on Jansen right now happened on Earth long ago. Magma ocean dynamics. Atmospheric outgassing. The balance between atmospheric creation and loss. Venus offers another comparison. Modern Venus has a crushing carbon dioxide atmosphere that creates a runaway greenhouse effect. Surface temperatures reach 750 Kelvin. But early Venus, like early Earth, was likely covered by magma oceans. Venus's atmosphere today is a product of billions of years of evolution, outgassing, atmospheric loss, and chemical reactions that eventually created the hellscape we observe now. Jansen represents an arrested state. Its proximity to its star prevents cooling. The magma ocean never solidifies. The planet remains locked in the early phase that Earth and Venus passed through. It's a living fossil of planetary evolution, preserved by extreme conditions that prevent further development. Mars provides a contrasting example. Mars once had a thicker atmosphere, probably sustained by volcanic activity. But Mars is small. Its interior cooled relatively quickly. Volcanic activity slowed and eventually stopped. Without replenishment, atmospheric loss gradually stripped away most of Mars's atmosphere. Solar wind and lack of a protective magnetic field accelerated the process. Jansen's size, 8 Earth masses, means its interior remains hot through radioactive decay and tidal heating. Volcanic activity will continue for billions of years. Unlike Mars, Jansen won't cool enough for atmospheric loss to win. The magma ocean persists, and with it, the atmospheric replenishment mechanism. These comparisons highlight how planetary outcomes depend on multiple factors. Size determines how long internal heat lasts. Distance from the star determines surface temperature and atmospheric loss rates. Rotation state affects heat distribution. Magnetic fields protect atmospheres from stellar wind. Chemical composition influences what gases are available for outgassing. Change any of these variables and you get a different world. Put Janssen farther from its star and it becomes a super-Earth with a solid surface and potentially habitable conditions. Shrink it to Mars size and it cools quickly, losing its atmosphere despite volcanic activity. Remove the magma ocean and the atmosphere disappears within thousands of years. Janssen occupies a precise point in this parameter space where extreme conditions create an unlikely equilibrium. The planet is large enough to stay geologically active, close enough to its star to maintain surface melting, tidally locked in a way that creates extreme hemispheric differences, and it has exactly the right composition to supply carbon-bearing gases through outgassing. Shift any factor slightly and Janssen would be something else entirely. It sits on a knife's edge between multiple possible states, maintained by the exact conditions it experiences. That precarious balance makes it scientifically invaluable. Understanding why Janssen's atmosphere survives teaches us about the boundaries of planetary habitability and the conditions necessary for atmospheres to persist. But there's something else Janssen reveals, something about the diversity of planetary outcomes in the universe. Before exoplanet discoveries began in the 1990s, our only examples were solar system worlds. We assumed other planetary systems would look similar. Rocky planets close to their stars. Gas giants farther out. Ice worlds at the edges. Janssen shatters that assumption. Super-Earths don't exist in our solar system. Tidally locked lava worlds weren't predicted by planetary formation models. The idea that a rocky planet could maintain an atmosphere while orbiting so close to its star contradicted theoretical expectations. Yet here it is. Real. Observed. Challenging us to expand our understanding of what planets can be. Every exoplanet discovery expands the catalog of known worlds, but some discoveries do more. They force us to reconsider fundamental assumptions about how planetary systems work. Janssen belongs to this second category. The 55 Cancri system contains multiple planets. Janssen orbits closest to the star, completing its circuit in less than 18 hours. Farther out are other worlds, Galileo, Brahe, Harriet, each occupying different orbital distances and exhibiting different characteristics. The system also includes a companion red dwarf star, 55 Cancri b, which hosts its own planets. This makes 55 Cancri one of the most populated planetary systems known outside our own. The architecture differs dramatically from our solar system. We have small rocky planets near the Sun, gas giants in the middle regions, and ice worlds at the outer edges. A clear pattern emerged from millions of years of gravitational sorting. 55 Cancri follows different rules. A super-Earth orbits where no planet should survive. Gas giants occupy unexpected positions. The whole arrangement challenges formation models based on solar system observations. Janssen's host star, 55 Cancri a, is a K-type star slightly cooler and smaller than our Sun. It's classified as Copernicus in the system's naming scheme, which honors historical astronomers and telescope pioneers. The star sits 41 light-years away in the constellation Cancer. Close enough that we can study it in detail. Far enough that we'll never visit. The star's composition matters for understanding Janssen. Spectroscopic analysis shows 55 Cancri a is relatively rich in heavy elements, particularly carbon. This chemical signature suggests the protoplanetary disk that formed the system contained higher proportions of carbon compounds than the disk that formed our solar system. That excess carbon might explain some of Janssen's unusual properties, including the diamond planet hypothesis. Several years ago, researchers proposed that Janssen might contain vast quantities of crystallized carbon in its interior. The idea emerged from density calculations and the star's carbon-rich composition. If true, Jansen's mantle could contain diamond layers hundreds of kilometers thick. Pressures and temperatures at those depths would force carbon into its densest crystalline form. The planet would literally be made partially of diamond. The hypothesis captured public imagination. Media reports dubbed it the Diamond Planet. But the reality is more complex and less certain. Recent observations suggest the magma ocean model better explains Jansen's observed properties. A diamond-rich interior remains possible but hasn't been confirmed. The planet's true composition likely lies somewhere between pure diamond and pure silicate rock, with carbon playing a significant but not dominant role. What we know for certain is that Jansen's discovery path was messy. The planet was first detected using radial velocity measurements, which tracked the star's subtle motion caused by orbiting planets. Early analysis suggested a planet with a 2.8-day orbital period. For several years, astronomers accepted this interpretation. Then Jack Wisdom reanalyzed the data in 2005. He argued the 2.8-day signal was an alias, a mathematical artifact created by combining the true orbital period with the observing schedule. He suggested the real period might be different. Other researchers published analyses supporting the 2.8-day planet. The debate continued. In 2010, Rebecca Dawson and Daniel Fabrici solved the puzzle. They demonstrated conclusively that the true orbital period was 0.7365 days, less than 18 hours. The 2.8-day signal was indeed an alias. This correction fundamentally changed our understanding of the planet. It moved Jansen from very close to extraordinarily close. The difference matters enormously when considering surface conditions and atmospheric survival. The transit discovery in 2011 confirmed the corrected orbital period. The MOST Space Telescope monitored 55 Cancri continuously for 2 weeks, capturing multiple transits exactly when Dawson and Fabrici's analysis predicted. Transit observations measure a planet's size by recording how much starlight it blocks. Combined with mass from radial velocity, this gives density. Density reveals composition. Jansen's density indicates it's rocky, not gaseous. But the exact internal structure remains debated. Is there a diamond layer? How thick is the magma ocean? Does a solid core exist beneath the molten mantle? These questions await better data. Temperature measurements added another layer of mystery. Spitzer Space Telescope observations in 2013 mapped Jansen's thermal emission using infrared light. The results showed something unexpected. The hottest point on the planet's day side was offset from the substellar point, the location directly facing the star. Instead of maximum temperature at the center of the day side, the hottest spot was shifted about 30 to 40 degrees eastward. Why? Something must be transporting heat across the surface. On a tidally locked world with no atmosphere, the hottest point should be directly under the star. The offset indicates active heat redistribution. Atmospheric winds could explain it. But at the time, scientists weren't sure Jansen had an atmosphere. Another possibility involved the planet's rotation. Tidal locking isn't always perfect. Some planets maintain slight rotational drift, which could shift the hottest spot. Or perhaps internal convection creates asymmetric heat flow that affects surface temperatures. The puzzle deepened when observations showed temporal variability. Jansen's thermal emission changed between different observing sessions. Sometimes it appeared brighter, sometimes dimmer. The variations were too large to be measurement noise. Something on or around the planet was changing. One explanation involves massive volcanic eruptions. If Janssen experiences supervolcanism, eruptions that dwarf anything on Earth, they could inject enormous dust clouds into the atmosphere. These clouds would temporarily block thermal emission, making the planet appear cooler. As the dust settled or dispersed, brightness would return to normal. Repeated eruptions would create the observed variability. Another hypothesis suggests a gas torus co-orbiting with Janssen. Picture a donut-shaped cloud of material surrounding the planet's orbit. Similar structures exist in our solar system. Jupiter's moon Io produces a plasma torus from its volcanic emissions. If Janssen continuously vents gas from its surface, some might remain in orbit around the star, creating a variable cloud that occasionally obscures the planet. These mysteries motivated the James Webb Space Telescope observations. Webb's unprecedented sensitivity and spectral resolution offered a chance to settle fundamental questions. Does Janssen have a real atmosphere? What is it made of? How does it survive? The observing campaign required meticulous planning. Webb observed the system from multiple complete orbits. Each observation lasted about 8 hours, nearly half of Janssen's orbital period. The telescope captured infrared light from the system both when the planet was visible beside the star and when it passed behind the star during secondary eclipse. Secondary eclipse occurs when the planet moves behind the star from our perspective. During eclipse, we see only starlight. Before and after eclipse, we see the combined light from both star and planet. Subtracting the eclipse measurement from the combined measurement isolates the planet's thermal emission. This technique is called secondary eclipse spectroscopy. The precision required is extraordinary. Janssen's thermal emission is thousands of times fainter than the star. Measuring it means detecting a tiny brightness change against an overwhelming background. Webb's instruments, NIRCam and MIRI, work at different infrared wavelengths. NIRCam covers 4 to 5 microns. MIRI extends from 5 to 12 microns. Together they provide a continuous spectrum showing how much light the planet emits at each wavelength. That spectrum reveals composition. Different molecules absorb and emit light at characteristic wavelengths. Carbon dioxide has a distinctive absorption feature around 4 to 5 microns. Carbon monoxide shows different patterns. Vaporized rock elements like silicon and iron would create yet another spectral signature. When the team analyzed Webb's data, they saw clear evidence for carbon-bearing gases. The spectrum showed reduced brightness between 4 and 5 microns, exactly where carbon dioxide and carbon monoxide absorb light. The signature didn't match vaporized rock. It matched volatile gases. This was the breakthrough. After years of debate, Webb provided definitive evidence that Janssen has a real atmosphere composed of actual gases, not just rock vapor. The atmosphere is likely dominated by carbon dioxide or carbon monoxide, probably both. These gases are continuously supplied by volcanic outgassing from the magma ocean below. The discovery settles one question but raises others. How thick is this atmosphere? How does its pressure compare to Earth's or Venus's? Does composition vary between dayside and nightside? Are there other gases present in smaller quantities? What about clouds or haze? Some answers will come from additional Webb observations. Others require different techniques. Future missions might directly image the planet, separating its light from the stars without relying on eclipses. Spectroscopy at higher resolution could detect trace gases and measure isotope ratios, revealing details about the atmosphere's chemistry and evolution. But the fundamental mystery is solved. Jansen has an atmosphere against all expectations. It survives in conditions that should strip it away within thousands of years. The magma ocean continuously replenishes lost gases, maintaining equilibrium between outgassing and escape. This mechanism allows the atmosphere to persist for billions of years despite hostile conditions. The implications extend far beyond one planet. If atmospheres can survive on worlds as extreme as Jansen, where else might they persist? What about planets slightly farther from their stars, where conditions are less hostile? Could super-Earths in intermediate environments maintain thick atmospheres for geological timescales? What does this mean for habitability across the galaxy? The discovery opens doors to understanding atmospheric evolution across the galaxy. Rocky planets exist in every configuration imaginable. Some orbit close like Jansen. Others circle at comfortable distances. Many fall somewhere between. Each environment tests different survival mechanisms. Jansen proves that extreme proximity doesn't automatically mean atmospheric death. The magma ocean mechanism works. It maintains equilibrium between loss and replenishment. But does this mechanism scale? Could slightly cooler worlds with less volcanic activity still maintain atmospheres through similar processes? What about planets around different types of stars? Red dwarfs are smaller and cooler than our Sun, but they emit powerful stellar flares that could strip atmospheres more efficiently than steady radiation. Do magma ocean planets around red dwarfs survive or succumb? These questions matter because red dwarfs make up roughly 70% of all stars in the galaxy. If their planets can't maintain atmospheres, that dramatically narrows the search for habitable worlds. Conversely, if Jansen's mechanism works around red dwarfs too, billions of additional worlds might retain atmospheres despite hostile conditions. The connection to Earth's past runs deeper than surface similarities. 4 billion years ago, our planet was a hellscape. Continuous asteroid bombardment kept the surface molten. The atmosphere was thick with carbon dioxide, water vapor, and other volcanic gases. No oxygen existed. No ozone layer protected the surface from radiation. Life had not yet emerged, or if it had, it clung to the most extreme refuges imaginable. That early Earth resembled Jansen in many ways. Not in temperature, Earth was cooler. But in the fundamental process of atmosphere formation through volcanic outgassing from a magma-covered world. Studying Jansen lets us observe this process happening now, 41 light-years away, rather than trying to reconstruct it from geological clues billions of years old. The insights apply to Venus too. Our sister planet may have started with oceans and a temperate climate. Runaway greenhouse warming turned it into an inferno with surface temperatures exceeding 860 degrees Fahrenheit. Venus today has a crushing carbon dioxide atmosphere 90 times thicker than Earth's. That atmosphere likely formed through volcanic outgassing, similar to the mechanism sustaining Jansen. Understanding how magma ocean worlds generate and maintain atmospheres helps explain Venus's transformation. It might even reveal whether Venus could have remained habitable if certain conditions had been different. Mars presents a contrasting case. The red planet once had a thicker atmosphere and liquid water on its surface. Rivers carved channels. Lakes filled impact craters. The atmosphere was dense enough to support a water cycle. Then Mars lost most of its atmosphere to space. Without a strong magnetic field to deflect the solar wind, atmospheric gases were gradually stripped away over hundreds of millions of years. Today Mars has only a thin carbon dioxide atmosphere, about 1% the density of Earth's. Jansen's survival mechanism, continuous volcanic replenishment, is precisely what Mars lacked. Once Martian volcanism declined, the atmosphere couldn't be replenished fast enough to compensate for losses. The planet dried out and froze. Comparing these worlds reveals the delicate balance required for atmospheric persistence. Too little volcanic activity means gradual loss. Too much stellar radiation accelerates escape. A magnetic field helps but isn't always necessary if replenishment rates are high enough. Janssen demonstrates that extreme volcanism can compensate for extreme radiation, maintaining atmosphere despite lacking magnetic protection. The search for habitable worlds depends on understanding these boundaries. The habitable zone around a star is traditionally defined as the region where liquid water can exist on a planet's surface. Too close and water boils away. Too far and it freezes. But habitability requires more than temperature. It demands atmospheric stability over geological timescales. A planet in a habitable zone means nothing if it can't hold on to its atmosphere. Janssen teaches us that atmosphere retention is complex. It's not just about distance from the star or planetary mass. Volcanic activity, stellar radiation, magnetic fields, and internal heat all interact. Some planets in the habitable zone might lose their atmospheres. Others outside it might keep theirs through vigorous outgassing. The traditional habitable zone concept may be too simplistic. We need a more nuanced understanding that accounts for atmospheric dynamics, not just surface temperature. Future observations will refine our knowledge of Janssen's atmosphere. Webb can observe the planet again, measuring how its spectrum changes over time. Variability would indicate weather patterns, volcanic events, or atmospheric circulation. Long-term monitoring could reveal seasonal changes if the planet's orbit is slightly elliptical, though current evidence suggests it's nearly circular. Other instruments could contribute different perspectives. Radio telescopes might detect emissions from atmospheric chemistry. Optical telescopes could measure reflected starlight, revealing cloud properties or atmospheric hazes. Each observation adds another piece to the puzzle. The goal is building a complete atmospheric model: temperature structure, pressure profile, chemical composition, circulation patterns. That model would be the first comprehensive picture of a rocky exoplanet atmosphere. Beyond Janssen, dozens of other rocky exoplanets await similar scrutiny. Many orbit closer to their stars than Mercury does to our Sun. Some are larger than Earth but smaller than Neptune, occupying a size range with no solar system equivalent. These super-Earths and mini-Neptunes are common in the galaxy, yet we understand them poorly because we lack local examples. Do they have atmospheres? What are those atmospheres made of? How thick are they? Can they support liquid water despite high temperatures? Janssen provides a template for answering these questions. The techniques developed to study it, secondary eclipse spectroscopy, thermal phase curves, long-term monitoring, apply to other worlds. Each new observation expands our catalog of atmospheric types. Rocky planets with hydrogen atmospheres. Worlds with water vapor envelopes. Planets surrounded by carbon monoxide. The diversity is likely enormous, limited only by the laws of chemistry and physics. The technology enabling these discoveries barely existed a decade ago. Webb launched in late 2021. Its predecessors, Hubble, Spitzer, Kepler, laid groundwork but lacked the sensitivity and spectral resolution for rocky planet atmospheres. Webb's mirror is nearly 3 times wider than Hubble's, collecting much more light. Its infrared instruments operate at wavelengths ideal for thermal emission spectroscopy. And its position at the second Lagrange point, 1 million miles from Earth, provides a stable environment free from atmospheric interference. These advantages combine to make observations like Jansen's possible. Without Webb, we'd still be debating whether rocky exoplanet atmospheres could be detected at all. Now we know they can. The question shifts from whether to how many and what types. Next-generation instruments will push further. Ground-based telescopes with adaptive optic systems that compensate for atmospheric distortion are reaching unprecedented precision. Space missions under development target rocky planets specifically. Some will use star shades, giant structures flying separately from telescopes to block starlight, making planets visible. Others will employ coronagraphs, internal masks that achieve similar blocking. These techniques enable direct imaging rather than relying on transits or eclipses. Direct imaging reveals more detail, including atmospheric composition, cloud patterns, and surface features if resolution permits. The ultimate goal is finding another Earth. A rocky planet in a habitable zone with an atmosphere containing oxygen, water vapor, and other biosignatures. Life as we know it requires liquid water and produces oxygen through photosynthesis. Detecting both in an exoplanet atmosphere would strongly suggest biology. Jansen isn't that world. It's too hot, too hostile, too extreme. But every planet we study teaches us something about planetary diversity and atmospheric resilience. Jansen proves that atmospheres can survive in conditions once thought impossible. That expands the parameter space where we might find habitable worlds. If atmospheres persist around planets as extreme as Jansen, they might exist in many environments we haven't fully considered. The galaxy may be richer in atmospheric diversity than we imagined, with implications for where life might arise and endure. Standing back, the Jansen story reflects humanity's expanding vision. 40 years ago, we didn't know whether planets existed around other stars. The first exoplanet discovery came in 1992, orbiting a pulsar. The first around a Sun-like star came in 1995. Now we know thousands of exoplanets, with more discovered every year. We've progressed from merely finding planets to characterizing their masses, sizes, orbits, and now atmospheres. Each advance reveals the universe in greater detail. Jansen represents the cutting edge of this progression, a world so alien yet so important for understanding how planets work. Its magma oceans, carbon-rich atmosphere, and extreme temperatures challenge our assumptions and expand our knowledge. In 41 years, light from Jansen reaches Earth, carrying information about a world that shouldn't exist by old rules but does by new understanding. That light, captured by our most sophisticated instruments, tells a story of resilience, complexity, and the endless capacity of nature to surprise us. The Jansen discovery arrives at a turning point in our understanding of what planets can be. For centuries, we built theories from 8 local examples. Mercury through Neptune. A handful of moons. 1 asteroid belt. Limited data breeding limited imagination. Then exoplanets shattered those constraints, revealing worlds that defy every category we'd constructed. Hot Jupiters orbiting closer than Mercury. Super-Earths with no solar system equivalent. Planets around binary stars, around pulsars, in configurations our models never predicted. Jansen sits at the extreme end of this spectrum. A world where rock boils, where atmospheres persist through mechanisms we're only beginning to grasp, where every measurement contradicts what textbooks said was possible. It's not just another data point. It's a fundamental challenge to planetary science orthodoxy. The implications ripple outward in unexpected directions. Consider the habitable zone concept. We've spent decades refining estimates of where liquid water can exist around different stellar types. But if atmospheric retention depends on volcanic vigor as much as stellar distance, those calculations need revision. A planet outside the habitable zone might maintain temperate surface conditions through internal heat and thick atmosphere. One inside might lose its air despite comfortable temperatures. Janssen proves the old boundaries were too rigid. Atmospheres survive where theory said they couldn't. Magma oceans sustain themselves for billions of years through tidal heating. Carbon dioxide and carbon monoxide circulate in environments hot enough to vaporize iron. The universe operates by different rules than we assumed, and each discovery reveals another layer of complexity we'd missed. The technological achievement deserves recognition too. Webb's instruments detected molecular absorption features in thermal emission from a rocky planet smaller than Neptune, orbiting a sun-like star 41 light-years away. The planet's contribution to total system brightness is infinitesimal. Yet Webb teased apart that faint signal, measured it across multiple wavelengths, and identified specific chemicals in an alien atmosphere. 20 years ago, this would have seemed impossible. 10 years ago, it was theoretical. Now it's routine. That progress accelerates. Webb will observe more rocky exoplanets, building a catalog of atmospheric types. Ground telescopes with 30-meter mirrors are under construction, capable of even finer measurements. Space missions in planning stages will directly image Earth-sized worlds around nearby stars. Within the next decade or two, we'll have spectroscopic data from dozens of rocky planets across a range of environments. Janssen is the first clear detection, but it won't be the last. Each atmosphere tells a story about planetary evolution. How did this world form? What was its early environment? Has its atmosphere changed over time? Is volcanic activity increasing or declining? These questions connect to the broader narrative of how planetary systems develop from protoplanetary disks into mature configurations. Janssen's carbon-rich atmosphere might reflect the unusual composition of its parent disk. Other planets will show different chemistries, revealing different formation histories. The connection to Earth's past grows stronger as we learn more. Our planet spent hundreds of millions of years as a magma ocean world. That phase determined what atmosphere we started with, which influenced how the surface eventually solidified and cooled. Water vapor condensing into oceans. Carbon dioxide dissolving into seawater. Nitrogen accumulating because it's chemically inert. These processes set the stage for everything that followed, including the emergence of life. We can't observe Earth 4 billion years ago. Those rocks are gone, subducted or eroded beyond recognition. But we can observe Janssen now, watching processes that mirror Earth's infancy. The magma ocean convection. The volcanic outgassing. The atmospheric chemistry under extreme conditions. It's a living laboratory for planetary formation, preserved by circumstances that prevent it from moving to the next evolutionary stage. Venus offers another parallel. The runaway greenhouse effect that created its hellish surface may have started from conditions similar to early Earth. Small differences in initial water content, volcanic activity, or atmospheric composition could determine whether a planet becomes habitable Earth or scorched Venus. Understanding how atmospheres form and persist on magma ocean worlds helps identify which factors matter most. That knowledge applies to every rocky planet in every system. Mars shows the opposite extreme. A world that lost its atmosphere because volcanic replenishment couldn't match escape rates. Janssen demonstrates that vigorous outgassing can maintain atmosphere despite extreme radiation. Mars lacked that vigor. Its smaller size meant faster interior cooling. Volcanism declined. The atmosphere thinned. Today we see the end result, a frozen desert with only wisps of air remaining. These comparisons reveal that atmospheric evolution isn't deterministic. Similar planets can follow divergent paths depending on subtle variations in initial conditions and subsequent history. Some retain thick atmospheres for billions of years. Others lose them within hundreds of millions. The galaxy likely contains examples of every intermediate state, each frozen at a different point in the progression from formation to final configuration. Finding habitable worlds requires understanding these pathways. We need to identify which planets can maintain atmospheres long enough for life to emerge and evolve. That means looking beyond simple temperature calculations. Volcanic activity matters. Stellar radiation matters. Planetary mass and composition matter. Magnetic fields help but aren't always necessary. The interactions between these factors create outcomes we're only beginning to map. Jansen expands that map into territory we'd previously marked as impossible. Atmospheres in extreme radiation environments. Magma ocean worlds maintaining volatile envelopes through continuous outgassing. Carbon-bearing gases surviving at temperatures that vaporize rock. Each observation adds nuance to our understanding of what's possible, pushing the boundaries of known atmospheric physics. The search continues with renewed purpose. Thousands of exoplanets await detailed characterization. Many are rocky. Many orbit in or near habitable zones. Some may harbor atmospheres with biosignatures, oxygen, methane, combinations of gases that suggest biological activity. Finding those signatures requires the techniques pioneered on worlds like Jansen. Secondary eclipse spectroscopy. Thermal phase curves. Long-term monitoring for variability. Future discoveries will surprise us. They always do. Each planet studied reveals unexpected features, challenges assumptions, forces theoretical revisions. Jansen challenged the assumption that rocky planets this close to their stars can't have atmospheres. What will the next discovery challenge? Perhaps we'll find atmospheric oxygen on a lifeless world, produced through non-biological chemistry. Or detect complex organic molecules in places we thought too extreme for chemistry to occur. Or discover that magnetic fields play different roles than we believed. The universe doesn't care what we think is possible. It operates according to physical laws, and those laws permit configurations we haven't imagined yet. Our job is observation, measurement, analysis. Build instruments sensitive enough to detect faint signals. Develop techniques clever enough to extract information from noise. Construct models flexible enough to accommodate new data without breaking. Jansen succeeds because it exists in a narrow parameter space where multiple extreme conditions align. Large enough to stay geologically active. Close enough to maintain surface melting. Tidally locked to create hemispheric extremes. Compositionally suited to supply carbon gases through outgassing. Change any variable and you get a different outcome. But in this exact configuration, the result is a magma ocean world with a carbon-rich atmosphere surviving against impossible odds. That survival teaches humility. Our theories predicted atmospheric loss would dominate. They were wrong. Nature found a mechanism we'd underestimated, continuous volcanic replenishment maintaining equilibrium with escape processes. The mechanism was there all along, operating on early Earth, on early Venus, on countless worlds across the galaxy. We just needed precise enough observations to confirm it. The James Webb Space Telescope provided those observations. Its infrared capabilities, its spectral resolution, its exquisite sensitivity combined to detect molecular absorption features in a rocky exoplanet atmosphere. The first clear detection of its kind. A milestone in exoplanet science. Proof that we can characterize rocky planet atmospheres despite their faintness and their distance. More milestones await. Direct imaging of Earth-sized worlds. Detection of water vapor on temperate planets. Identification of biosignatures in exoplanet atmospheres. Each achievement builds on previous ones, using techniques refined through observations like Janssen. The progression continues, limited mainly by technology and funding. As instruments improve, so does our ability to study ever more challenging targets. 41 light-years separates us from Janssen. Light traveling at 186,000 miles per second takes 41 years to cross that gulf. The photons Webb detected left Janssen in 1983, carrying information encoded in their wavelengths about a world that defies expectations. Those photons journeyed through interstellar space, arrived at our solar system, and entered Webb's optics to be recorded and analyzed. The information they carried changed our understanding of planetary atmospheres. Not through dramatic revelation, but through precise measurement of subtle spectral features. Science advances through exactly this process. Careful observation. Rigorous analysis. Gradual accumulation of evidence. Occasional surprises that force theoretical revisions. Janssen delivered one of those surprises. A rocky planet with an atmosphere in conditions that shouldn't permit one. The discovery proves that atmospheric science still has fundamental lessons to learn. Our models are incomplete. Our assumptions sometimes wrong. The universe more diverse than our limited sample suggested. That diversity is what makes exoplanet science compelling. Every world is an experiment in planetary physics. Different initial conditions. Different evolutionary paths. Different outcomes. Some produce Earths, temperate, wet, potentially habitable. Others become Venuses, scorched, hostile, shrouded in crushing atmospheres. Still others turn into Mars analogs, cold, dry, stripped of most air. And some become Janssens, extreme, unexpected, challenging everything we thought we knew. The galaxy contains hundreds of billions of stars. Most have planets. Rocky worlds number in the billions. Each one represents a unique combination of formation history, composition, stellar environment, and evolutionary trajectory. We've characterized perhaps a few dozen in detail. The sample is tiny. The lessons preliminary. But each observation adds to our knowledge, building toward comprehensive understanding of how planets work. Janssen's contribution to that understanding is clear. Atmospheres can survive extreme radiation through continuous volcanic replenishment. Magma ocean worlds maintain carbon-rich envelopes despite surface temperatures exceeding 6,000 degrees Fahrenheit. Tidally locked planets redistribute heat through atmospheric circulation even when that atmosphere shouldn't exist according to old theory. These aren't minor details, they're fundamental insights about planetary atmospheric physics. The knowledge applies beyond Janssen. Every ultra-hot rocky planet. Every tidally locked world. Every planet with active volcanism and strong stellar radiation. The mechanisms we've identified operate wherever similar conditions exist. That means potentially thousands of worlds across the galaxy, each maintaining atmospheres through processes we're only now beginning to understand. Looking forward, the questions multiply faster than answers. How common are magma ocean planets? Do they exist around different stellar types? Can slightly cooler versions maintain atmospheres through similar mechanisms? What about planets with different compositions, more water, less carbon, varying amounts of metals? How do magnetic fields influence atmospheric retention when volcanic activity is vigorous? Do some planets transition from magma ocean states to solid surfaces, and if so, how does that affect their atmospheres? Each question requires observations. More Webb time. Future missions. Continued monitoring of known worlds and characterization of newly discovered ones. The work spans decades, involves hundreds of scientists, demands billions in funding. But the payoff is understanding our place in the universe. Learning how common Earth-like worlds are. Discovering whether life exists elsewhere. Finding out if our planet's history is typical or exceptional. Jansen moves us one step closer to those answers. Not through being Earth-like, it's about as far from Earth as a rocky planet can get. But through demonstrating that planets operate under a wider range of conditions than we'd believed possible. If atmospheres survive at Jansen's orbital distance, they might persist in many environments we'd written off as too hostile. That expands the search space for habitable worlds and increases the odds that we'll eventually find one. The universe is vast. The number of planets staggering. Most will remain forever beyond our ability to study in detail. But the ones we can observe teach us principles that apply to all the others. Physical laws operate the same everywhere. The chemistry of planetary formation follows universal rules. Atmospheric physics doesn't change based on location. So every planet we characterize tells us something about countless others we'll never see. Jansen tells us that nature is more resourceful than our models predicted. That equilibrium can exist between opposing processes even under extreme conditions. That volcanic vigor can maintain atmospheres despite powerful escape mechanisms. These lessons apply to exoplanets we'll discover next year, next decade, next century. They become part of the framework we use to understand all rocky worlds. 41 light-years away, Jansen continues its 18-hour orbit. The magma ocean churns. Volcanic gases bubble to the surface. Stellar radiation strips away atmosphere as fast as outgassing replenishes it. The process has continued for billions of years and will continue for billions more. We've observed it for a few years at most. But those observations revealed something we'd never have predicted from theory alone. A world that shouldn't exist by old rules but does according to new understanding. That's how science progresses, one impossible planet at a time.